case, we have seen that the influence coefficient changes with speed, especially when we are operating at different modes, the influence coefficient changes. For this case, we need to calculate the influence coefficient for all the speed of the range in which we want to balance the rotor. And we saw that this influence coefficient can be estimated purely based on the measurement. Only thing, we need to keep the trial masses in various balancing planes which we have chosen, and from that and without trial mass responses, if we take the difference of these two, with that we could able to estimate the influence coefficient, and then these influence coefficient can be used to obtain the residual balances in the discrete planes. So in this we illustrated the method with two case study. In one case study, we chose two balancing plane and only discrete residual unbalance we kept, and we could able to balance the rotor perfectly in this particular case. Second case, we consider not only the discrete residual unbalance but also distributed residual unbalance in the shaft, and in this we focused on balancing second mode up to second mode, and we saw that other modes were not balanced because of the distributed eccentricity in the shaft. So this is very important observation, that if we have discrete residual unbalance, then we can able to balance all the modes of the shaft. But if we have distributed unbalance, then we could able to balance up to the finite number of modes up to which we are trying to balance the rotor. In subsequent class, we will see some other kind of fault apart from the unbalance, how they can be identified and how they can be corrected. In most common fault is unbalance, but we will see other kind of faults are difficult to remove. It's not like unbalance in which we could able to balance the rotor. So that we will see in the next class.
Hi, my name is Ch-27 and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other. Correct? So when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.
Swayam Prabha, Digital India, Educated India.
Welcome to lecture number 15. In this lecture, we are going to see the methods, different methods to improve the efficiency of the Rankine cycle without adding any additional device like a reheating process or a regeneration process. So, we are going to discuss the methods of improving the Rankine cycle efficiency. Before going into the contents of this lecture, let us have a quick recap of what we have discussed in the previous lecture number 14. We have made a comparison between an ideal Rankine cycle and the actual Rankine cycle. The actual Rankine cycle deviates from the ideal Rankine cycle in a few aspects, like there are pressure drops in the line which connects the boiler and the turbine. There is a pressure drop between the turbine and the condenser. So, the pressure drop in the condenser is small compared to the pressure drop in the boiler turbine line. And irreversibilities are associated in the pumping process and the isentropic expansion process. So, because of these factors, the actual efficiency of the actual cycle is less than the ideal case. Initially, we have discussed the Carnot cycle also, but if you want to model the Carnot cycle as an ideal cycle, there are a lot of unrealistic things are there. So, because of which a modified form of the Carnot cycle has been used as the ideal case for the ideal Rankine cycle. Then we have solved a numerical question in which we found the enthalpy at state point 1, 2, 3, 4. Just to emphasize once again, if the pressure and temperature of the steam are given, using the pressure we have to find out the saturation temperature. Compare the saturation temperature with the given temperature of the steam. If the given temperature is more than the saturation temperature, then the condition of the steam is superheated. We have seen in the vapor dome where the dryness fraction lies between 0 and 1. If dryness fraction is equal to 0, the condition of the steam is saturated liquid. If the dryness fraction is 1, x is equal to 1, then the condition of the steam is saturated vapor. Region lying between x is equal to 0 and x is equal to 1 is two-phase region, which is a mixture of combination of liquid and vapor. Region which is lying to the left of the saturated liquid line is called subcooled region, and the region which is lying to the right side of the saturated vapor curve is the superheated region. So, we have also seen the term specific steam consumption, that is how much kg of steam is consumed to produce 1 kilowatt hour of energy. So, now let us discuss the methods of improving the efficiency of the ideal Rankine cycle without adding the components. So, the first method is the decreasing the condenser pressure. Next one is increasing the boiler pressure. So, we know the Rankine cycle, ideal Rankine cycle operates on two pressure, the boiler at the high pressure and the condenser at the low pressure. To recollect the processes, 1 to 2 is isentropic expansion of the steam in the steam turbine. So the difference between the enthalpy H1 and H2 gives the work done by the turbine, WT. And then we have the constant pressure heat rejection process 2 to 3, where the steam in vapor state is converted into liquid water. The heat is removed during the condensation process by a cooling medium, that is water, which is normally circulated with the help of the pump from a cooling tower in the thermal power station or the steam power plant. Then process 3 to 4 is the pumping process, where the feed water is supplied back to the boiler with the help of the pump. So that is similar to the compression process in air standard cycle. Then from 4 to 1, it is constant pressure heat addition process. Constant pressure heat addition process. So when we say the constant heat addition, the temperature also remains constant, because that is a phase change process, especially the condensation and the evaporation are phase change process, where the property temperature remains constant. So the third method of superheating is steam superheating, and we will solve a numerical example. At the end of this lecture, we will appreciate the efficiency improvement. What is the efficiency improvement due to the incorporation of method number 1? The first one is reducing the condensing pressure, next one increasing the boiler pressure, then superheating. So I will be comparing these efficiencies, the efficiency improvement, with the same example which we have discussed in the previous lecture, where we have found the thermal efficiency of the Rankine cycle. Let me recollect. There are two methods by which the efficiency of the Rankine cycle can be found. One is by finding the net work done in the cycle, that is the difference between turbine work and pump work, to the ratio of heat supplied, that is QS. So that the QS is the difference in the enthalpy between H1 and H4. Another method is find the heat supplied and find the heat rejected. The difference, that is the net work, divided by the heat supplied will give the efficiency. Ultimately, whichever method we employ, the final answer will be the same. The answer will be the same. So what we are doing in the first method is decreasing the condenser pressure. Okay. So see here, 1 to 2 is isentropic expansion of steam in the turbine. So this is the turbine work, and this is the pumping process, this is pump work. Okay. So 2 to 3 is constant pressure heat rejection, and 4 to 1 is constant pressure heat addition, and 3 to 4 is pumping. So when I reduce the condenser pressure, the temperature also comes down, because we know that temperature and pressure are directly proportional. So when I reduce the pressure, so this is the reduced condenser pressure line is shown in dotted. The solid line represents the pressure with which the condenser is operated. If you take the numerical question which we discussed in the previous class, it is 0.74 bar. 0.74 bar. Suppose if I am reducing the pressure further, less than 0.74 bar, so I am representing that one with the dotted line. So we will see how the reduction in the condenser pressure, how it increases the net work done in the cycle. So if you see here, without reduction in the pressure, the enthalpy of the steam leaving the turbine is H2, and this one, or if you see, let us see this one, 3 to 4. So here initially it is from 3 to 4, so there is a difference between delta T, difference in enthalpy from 3 to 4 and from 3 dash to 4 dash. Similarly, there is a difference in enthalpy, there is a difference in the delta H value. If you take the enthalpy difference, this one and this one, both are not same. So ultimately it results in the increase in the net work done. We will see how much is the turbine work, how much it has changed, how much is the pump work has changed. But the difference between the net turbine work and the net pump work, that is W net is equal to WT minus WP. This is WP, this is WP. So this is a power producing device, that is a power absorbing device, consuming device. So the difference is the net work. So there is an increase in the net work done in the cycle. Now increase in the boiler pressure, increase in the boiler pressure. So I am increasing the boiler pressure. Okay, so 1 to 2 is isentropic expansion of steam, 2 to 3 constant. So this is the heat, let me mark the arrows, this is heat rejection, this is QS. So here also we can mark, this is QR, this is QS. So I am increasing the boiler pressure from this solid line to the dotted line. The dotted line refers to the boiler pressure after it is increased. So here if you see this, okay, the area under this curve, this one, here this portion there is increase in W net, but here there is decrease in W net, there is a decrease in W net. So the other processes remains the same. Steam superheating, this is state point 1 is also in superheated condition, 1 dash is also in superheated condition. So increase the superheating, that is the degree of superheat. Degree of superheat is the difference between the temperature superheating and the temperature in the saturated vapor line. So that is delta T is, that delta T, that temperature difference is the degree of superheat. So when we increase the superheating from 1 to 1 dash, we infer that there is an increase in the net work done. How this is increasing? See, when we increase the delta H, H1 minus H2 difference is less than H1 dash minus H2 dash difference. H1 dash minus H2 difference. So you will understand better when we solve the numerical question. And finally, I have given a comparison of all the efficiencies. The first, the base efficiency is the efficiency which we solved in the previous lecture. Then case 1 or the first case is how the decrease in the condenser pressure changes the efficiency, how the increase in the boiler pressure increases the efficiency, and how the superheating changes the efficiency. So to make these concepts, to explain the concepts better and to make the students to understand easily, so I will be explaining all this process with the help of a numerical question. Consider a steam power plant operating on the ideal Rankine cycle. So there is steam enters the turbine at 3 megapascal. So that is 30 bar. I have taken the previous example only few data will be different. So the pressure 3 megapascal 30 bar, temperature also remains the same, because my aim is to make a comparison on the improvement in the efficiency. What happens when the condenser pressure is reduced or when the boiler pressure is increased. So if you want to make a comparison, the base data should be the same and is condensed in the condenser at a pressure of, now I am changing the condenser pressure to 10 kilopascal. Earlier it was 74 kilopascal, that is 0.74 bar. Now the condenser pressure is decreased from 0.74 bar to 0.1 bar. Okay. So determine the thermal efficiency of the steam power plant. The thermal efficiency of the steam, if the steam is superheated, to 600 degree centigrade instead of 350 degree centigrade. Okay, instead of 350 degree centigrade. So thermal efficiency, so the steam is superheated to 600. Third case is thermal efficiency if the boiler pressure is raised to 15 megapascal. So from 3 megapascal, so if you see the methods, first case I am decreasing the condenser pressure from 74 kilopascal to 10 kilopascal. Next I am increasing the boiler pressure from 3 megapascal to 15 megapascal. Then I am increasing the superheating temperature up to 600 instead of up to 350. Okay. So in all these three cases we have to find out the efficiency, the net work done, the heat supplied, then only we can find out the efficiency of the cycle, and finally we can make a comparison of how much the efficiency has varied in each case. So this is the case A. There is a wherever that there is a change, I will highlight with the pen. So the boiler pressure remains the same, high pressure there is no change for the first. This is case A, where the boiler pressure is reduced, the condenser pressure is reduced, decrease in condenser pressure. Let me write it, decrease in condenser pressure from 0.74 bar to 0.10 bar. So, this is very important. So, instead of the lower pressure 0.74 bar, I am having 0.1 bar. So, the properties corresponding to 0.1 bar will change, the steam properties from the steam table. Whatever the properties which we have taken corresponding to 30 bar and the steam temperature is 350, that will remain same, So, 3 megapascal is 30 bar, there is a change in the condenser pressure, so which I am highlighting with pen. Steam temperature remains the same. So, from steam table, okay, so the usual procedure from steam table corresponding to 30 bar, okay. Let me explain again. 30 bar, find out the saturation temperature. So, this is 233.8. So, at 30 bar, table 2, let me emphasize again, when pressure is given you have to refer table 2, okay. So, this is table 2, this is table 2, okay, table 2, and this is pressure value is given. I am finding the T sat. So, same value, that is 233.8, okay. T sat is equal to, saturation temperature is equal to 233.8 degrees centigrade. Compare this temperature with the temperature of the steam. So, this is less than T, or the given temperature of the steam is greater than T sat. Therefore, the condition of the steam is in superheated state. Therefore, steam is in superheated condition. Superheated condition. Okay. So, whatever the properties we have taken, H1, H2, H1 enthalpy of superheated steam and entropy of superheated steam will not change when we compare these values with the previous, in the example which we solved in the previous lecture. So, H1 and HS1 will remain the same. Okay. So, if this is the specific enthalpy of superheated steam, table number 4, table 4. So, corresponding to 30 bar, 3117.5, and this is table 5, where we have to take this entropy value corresponding to 30 bar, 6.747. So, there is no change, and corresponding to this temperature, okay, corresponding to this, because the temperature of the given temperature of the steam is 350. Only the condenser pressure is decreased from 74 kilopascal or 0.74 bar to a pressure of 10 kilopascal or 0.1 bar. So, H1 is 3117.5, no change. H1 is equal to 3117.5 kilojoule per kg. This is from table 4. This is at 30 bar, 350 degrees centigrade from superheated steam table, and similarly entropy is equal to 6.747 kilojoule per kg Kelvin. I am writing again, though it is the procedure is same, especially the values are same, so that the students will have better clarity. Table 5. Okay, so that's what I have written here. Properties are taken from this one. Now, as we know, we need to find 4 enthalpy, H1, H2, H3 and H4. Okay, H1, H2, H3 and H4. So, I have found enthalpy at 1. Now, I am going to find 2, enthalpy at 2, then 3 and 4. If you see the enthalpy at 2, okay, enthalpy at 2, actually this line will be, it is not saturated vapor line, okay. So, the state point, it will be slightly inside. Let me change it, because unless we find the dryness fraction, we will not know whether it is saturated vapor or in two-phase region. So, when depending upon the value, if you see, let me change the diagram after we find the dryness fraction. Now the usual procedure, process 1 to 2 is isentropic, 1 to 2 is isentropic process. So S1 is equal to S2. S1 we have found from the superheated entropy table, so 6.747, and S2 can be written as SF2 plus X2 into SFG2. If we get X2 is equal to 1, then 0.2 will lie on the saturated vapor line. If X2 is less than 1, that means 0.2 will be lying on in the two-phase region. Assuming that it may be saturated vapor, so I have marked 0.2 here time being, but I will be changing this one depending upon the value which we are getting. So now go to the low pressure value, okay, low pressure value. The low pressure is, again this is also table 2, okay, 0.1 bar or 10 kilopascal. I am going to read out SF value, SFG2 value, SF 0.649 and 7.502. So this is at 0.10 bar. Read out SF2. SF2 is 0.649, 0.649 kilojoule per kg Kelvin, and SFG2 is equal to, okay, and SFG2 is this value. So you have to read this value, this value. Later I will refer HF and HFG, and I will refer specific volume also. Specific volume value is required to calculate the pump work. So SFG is 7.502, 7.502. So this is table number 2, kilojoule per kg Kelvin. Substitute these values, substitute these values here, and you will get the only unknown is dryness fraction. So dryness fraction, if you calculate, we are getting 0.813. That means 81.3% vapor, and the remaining quantity is liquid. Remaining quantity is liquid, 18.7%. So 0.813. This is the dryness fraction. This is the dryness fraction. Now I can find H enthalpy at state point 2, HF2 plus X2 into HFG2. These two values are to be found at 0.10 bar pressure from table 2. So directly you can read HF2 value and HFG2 value. See here, HF2 is 191.8, and HFG is 2392.9. So 191.8 kilojoule per kg. Let me write this value, 2392.9, 2392.9 kilojoule per kg. So these two values substitute it here and find out the enthalpy of the steam at the outlet of the turbine, So we get the value as 2137.2, 2137.2 kilojoule per kg. Before that, I am going to modify the state 2 on the TS diagram, because we have not got the calculated X2 value is not equal to 1. So state point 2 cannot be in saturated vapor curve. Okay, so let me modify the curve. I will do it so that I have just initially done purposely, so that while explaining it will be easy for you why point number 2 is not in saturated vapor curve. So if you see this this curve, here it is point 2 is this one. So let me change this one. So this point will be, okay, so let us move this one here, and this I will move it here, okay, and this point 3 will be slightly here because point 2 is shifted. So, this is point number 2, this is point number 2, and this is okay, this one. So, let me move this point. So, this is point 2 and little bit move this line. So, now the state point 2 is in two phase region, state point 2 is in two phase region. Okay. So, let me save this one, and similarly I will extend this line also, because this is from this. Okay. So, this is the value of pressure. Let me erase this one. Okay. So, then I will move this pressure value. So, the condenser pressure is changed to from 0.74 bar to 0.1 bar. Okay. So, this is the 0.1 bar. So, now the state point 2, this is in liquid plus vapor, liquid plus vapor, it is not in saturated vapor curve, and this is the difference in pressure. Okay. Now, let us go to this problem. So, we have found the enthalpy at state point 2, enthalpy at state point 2. Now, we are going to find out the enthalpy at state 3. So, that is point 3 is on saturated liquid line, point 3 is on saturated liquid line, there is no change in that. So, H3 is equal to liquid enthalpy corresponding to 0.1 bar pressure. At 0.10 bar, that is table 2, enthalpy at 3 is equal to, that is liquid enthalpy. Let me emphasize this one. See, H3 is equal to, suppose if you write HF3 plus dryness fraction into HFG3, if it is saturated liquid, X is equal to 0, X is equal to 0. So, this term will be 0. So, H3 will be equal to HF3, H3 will be equal to HF3. So, this is nothing but corresponding to 0.1 bar, this is corresponding to 0.1 bar. So, the value is 190, if you see this value, it is 191.8, the same value which we used for the previous calculation, 191, say this is the value, 191.8 kilojoule per kg. Now, we have found H3. Now, in order to find H4, state 4 enthalpy, H4 we know that it is pump work plus H3, H3 we have found. So, we need to find pump work. Pump work is equal to, pumping is process 3 to 4, pumping is process 3 to 4, the specific volume at this point into the pressure difference, into the pressure difference. So, specific volume at 3, that is VF3, okay, VF3 into, let me write this one, specific volume at 3 into delta P, this is equal to VF3 into delta P. The pressure difference is 30 bar. So, this should be substituted into kilopascal, 3000 kilopascal minus 0.1 bar. Okay. So, I think 0.1 bar. So, that is 10 kilopascal, 10 kilopascal, and this VF3 I will be taking from the table, from table number 2, this is the specific volume, liquid specific volume corresponding to 0.1 bar, 0.001010. So, this value is VF3 should be taken at 0.1 bar. So, which is equal to 0.001010 meter cube per kg. So, when you substitute this value here, the pump work you will get us 3 kilojoule per kg. Pump work is 3 kilojoule per kg. And use this pump work and substitute here, you will get H4 is equal to H3 plus 3, 191.8 plus 3, 194.8 kilojoule per kg. So, I have found all the 4 enthalpies. 194.8 kilojoules. Now this difference between enthalpy H1 and H2 will give turbine work. Heat supplied is H1 minus H4. Okay. This difference will give the turbine work H1 minus H2. This difference will give the heat supplied. This is heat supplied. This is heat supplied. This is heat rejected. Okay. Okay. So that substitute the values, find out turbine work, net work we can find, pump work already we have found 3 kilojoule per kg. So heat supplied, the efficiency comes around 33.4%. So if you compare with the previous problem, let me go to the last table. See here, this is the previous one, the problem which we discussed in the previous lecture, efficiency of 26.1 or 26%. Now there is an increase in the efficiency of from 26 to 33.4% when the condenser pressure is reduced 0.1 bar, 0.1 bar. Now case number 2, so it's quite a lengthier problem, but you will appreciate at the end of this lecture how the efficiency, thermal efficiency of the Rankine cycle varies when we change the condenser pressure or boiler pressure or superheating temperature. Now for the second case, what is the second case? If you see the second case, thermal efficiency of the steam is superheated to 600 degrees centigrade instead of 350. So the temperature of the steam is 600 and not 350 in case number B. Okay, so there is a difference here. Temperature of the steam is heated to superheated condition up to 600 degrees centigrade instead of 350. So there is now, like the usual one, Tsat we have to find out. Okay, Tsat we have to find out corresponding to 30 bar. Find out the Tsat, that is 233.8 degrees centigrade. Compare the Tsat with the given temperature. Now for this case the temperature is changed to 600 degree centigrade. So let me plot in this diagram. Case B, superheating to 600 degree centigrade instead of 350 degree centigrade. Okay. So there is a difference in temperature of this one. There is a difference in temperature of. So there is a change in the steam temperature. Instead of 350, it is 600. It is 600. So here also this is heat supplied. This is heat rejected. The pressure remains the same. Boiler pressure is 30 bar and the condenser pressure is 0.1 bar, like case A. Only there is a difference in the temperature of the steam to which it is superheated. In earlier case it was 350 degrees centigrade. Now it is 600 degrees centigrade. So now it is 600 degree centigrade. So now the properties will change because earlier we were referring 30 bar and 350. Now it is 30 bar and 600 degree centigrade. Okay. So this is table number 2 as usual. Pressure, I am find out the saturation. There is no change in the saturation temperature because 30 bar remains the same. So pressure P1 is equal to 30 bar. So at 30 bar, table 2, find out Tsat. Tsat is equal to 233.8 degrees centigrade, which is less than temperature of the steam, which is equal to 600. So therefore T is greater than Tsat. Therefore the condition of the steam is superheated. So for this case B, I will be reading the enthalpy and entropy values corresponding to temperature 600 and not 350. So at 30 bar, 600 degrees centigrade, read out the enthalpy value and read out the entropy value, and entropy value from table. This is table number 4 and this is table number 5. This is very important. This is the change in temperature here. So I have taken the steam tables. This is table 4. Enthalpy of steam corresponding to 30 bar, no change in the pressure. The temperature of the steam is 600. This is the temperature. Initially it was 350. Now it is 600. So the H1 value is 3681 3681 kilojoule per kg. You can see the enthalpy value for corresponding to 600 is 3681, whereas the enthalpy corresponding to 350 is 3117. So there is an increase in the enthalpy when you heat the steam from 350 to 600 degrees centigrade, because enthalpy is a direct function of temperature. Obviously the values will be higher. Okay, and this is the enthalpy and this is the entropy, table number 5. For this temperature, for this pressure, it is 7.508. So this is the specific entropy, 7.508. So the entropy is also, in the previous case entropy, if you see, it is 6.747. Now it has increased to 7.5 kilojoule per kg Kelvin. So these two values have to be taken for 30 bar and 600 degrees centigrade. So using this enthalpy, now we know process 1 to 2 is isentropic, therefore S1 is equal to S2. Like the usual, follow the same procedure, find out dryness fraction. Dryness fraction, earlier it was around 81%, 0.81. Now it has increased to 0.914. The vapor percentage has increased. So remaining less than 10%, 9% is liquid. So X2 is equal to, so using the formula, this is S1. S1 is 7.508. So S2 can be written as SF2 plus X2 into SFG2. Remember, SF2 and SF2, SFG2 are to be evaluated at low pressure. There is no change in the low pressure. What are the values which we have found here? See here, what are the values we have found here? Let me take these values. These values SF2, SFG2, HF2, HFG2 will remain the same because the condenser pressure is same for this case. So all these values to be taken from 0.1 bar, 0.1 bar. Similarly, so we can find out the enthalpy of the steam. Enthalpy of the steam I have found here. Enthalpy of steam I have found here. HF2 values and HFG2 values to be taken corresponding the previous case A values only. There is no change. So similarly HF2, HFG2 to be taken at 0.10 bar. Okay, 0.10 bar. Now you use H2, use this formula, H2 is equal to HF2 plus X2 into HFG2. And this point also will be lying, it will not be lying in the saturated vapor curve, it will be lying in the little bit lower. Okay, so let me change it, otherwise it will be confusing. Okay, so initially I fix it at saturated vapor curve. Suppose if we don't get X2 as 1, dryness fraction as 1, then we have to modify the diagram. So let me use this one. So let me change this one, and this point also will be tilted, this line will be tilted. Okay, so to initially I have done it purposefully so that while explaining I will use this one. Okay, so this is state point 2, and let me save this one. Let me extend this line also. So let me erase this and rewrite it again. So this will be, let me save it, otherwise the previous one changes, whatever we have made it will go. Okay, so this is a QR, this is QR, okay, this is QS. So now this point, it is not, the dryness fraction is, the calculated dryness fraction is 0.914 in this case. So if it is 1, it will be touching the saturated vapor line. Now repeat the procedure, find out enthalpy at 3, What is enthalpy at 3? Enthalpy at 3 is liquid enthalpy at 0.10 bar, the same value which we have used. Then how to find H4? Pump work plus H3, pump work plus H3. So substitute all the values, find out the efficiency W net, and how to find pump work? Pump work specific volume at 3 into delta P into delta P. So the efficiency is W net by heat supplied. W net is W turbine work minus pump work by heat supplied. To remind you again, the turbine work is H1 minus H2. Pump work already we have calculated. Pump work is H4 minus H3. So this will give the W net. Heat supplied is equal to H1 minus H4, and heat rejected will be equal to H2 minus H3. So we can use this formula, or heat supplied minus heat rejected divided by heat supplied. The efficiency in this case has increased from 33% to 37.3%. 37.3%. See here, it has increased from, again increased. Here what I have done is I have increased the temperature of the steam from 350 to 600. 350 to 600. Now the last case is there. Case C. What is the third one? The third one is boiler pressure is increased to 15 megapascal. From 3 megapascal to 15 megapascal. That is 150 bar. From 30 bar to 150 bar, which is 5 times. So let me write it here so that when you refer it will be easy. Boiler pressure is increased from 30 bar to 150 bar. Okay. So here also we will find the same thing. There is a pressure 1 changes. So there will be difference in Tsat. So given P1 is 150 bar. So from table 2, find out the Tsat at 150 bar. So let us quickly do it. 150 bar, the saturation temperature is 342. The saturation temperature is 342.1. This is table 2. This is the pressure value. This is the temperature. 342.1 degrees centigrade. Initially the saturation temperature was 233 degrees centigrade. So now it is, because the pressure is increased, so the temperature also increased. Given temperature is 600 degrees centigrade. Given temperature, so T1 is greater than T1, or T temperature of the steam is greater than Tsat. Therefore, superheated condition. So find out the enthalpy from the superheated steam table. So at 150 bar, there is no change in the steam temperature compared to case B. Find out H1 and S1. Okay, for these two conditions, let us find out that one. See, this is specific enthalpy, table number 4. Table 4 corresponding to 150 bar. Now the pressure is changed from 30 bar to 150 bar. So ensure that you take the properties corresponding to 150 bar and 600 degrees centigrade. 600 degrees centigrade. This is the temperature. So the value is 3579.8. 3579.8. 3579.8 kilojoule per kg. Similarly, take the entropy value from table number 5. Table number 5, entropy value corresponding to 150 bar, 6.676 kilojoule per kg Kelvin. 6.676 kilojoule per kg Kelvin. Now as usual, how to find the enthalpy at state point 2? Process 1 to 2 is isentropic. So S1 is equal to S2. S2 can be written as SF2 plus X2 into SFG2. Okay. So S1 is 6.676. Let me write it again, SF2 plus X2 into SFG2. So this value we know, SF2, SFG2 to be taken from the low pressure one. So here, see here, there is no, because the low pressure is 0.1 bar. So whatever the values which you have taken from previous one, like 0.649, 7.502, it will be the same. Okay, so let me write SF1, SF2, then HF2, HFG2, all these values to be taken from corresponding to 0.1 bar, 0.1 bar, and find out the dryness fraction using this formula, dryness fraction. Here the dryness fraction, if you see, in this case it has decreased from 0.91 to 0.803, 0.803. Now again I will modify the curve. Okay, I will modify the curve here because it is in saturated vapor curve. So let me modify it. Okay, so let me modify it, let me ungroup it and modify it. So here again the point will move, and this is this one. Let me move this one. So 1 to 2 is, the point number 2 is not in this one. Okay, so let us move this one. Point, this is point number 2. Because of time constraint I have just moved little bit only. This is this one, and this line also, this line will be saturated liquid, and this line will be point number 3 to 4. Okay, so let me save this one, and so here also if you see, this is the heat rejected and this is the heat supplied. Okay, this is the heat supplied, and again, so now we have got the dryness fraction. Accordingly I have modified the temperature entropy diagram. So we have got 80% vapor and 20% liquid is there. Now usual one, state 3 as usual we have to find out H3 is equal to HF3 at 0.1 bar. H4 we can find from state 4. The procedure is same, so I am just quickly running through it. H4 is equal, enthalpy at 4 is equal to enthalpy at 3 plus pump work, and this pump work is nothing but VF3 into delta P. VF, where VF3 we have to find out at 0.1 bar. Okay, so substitute the values we have got. So when you substitute this value you will get H4. Once you know the enthalpy H1, H2, H3 and H4, we can find W net, heat supplied, heat rejected. Okay, of course to find W net we should know turbine work and pump work. So when you calculate, when you substitute the values, turbine work is this one, 1466.6, heat supplied is this value, thermal efficiency it has increased from 37% from the previous case.
Swayam Prabha. Digital India. Educated India.
Okay, welcome back, and let's continue the discussion on
different reacting system or combustion system. So, what we have been talking right now, looking at different kind of combustion system. So, broadly they can be categorized in two different category, like internal system and the external combustion system. Most of the practical applications you find in the internal combustion system, and then also the internal combustion system you can also look into different aspect of it, whether it's a steady or unsteady or charge. These are the things that we have already discussed, and then we looked at different kind of combustor like can combustor. These are gas turbine applications, can combustors, can annular combustors. So, now we will continue the discussion from there, and then today we will look at the things, other aspect of these things. So, just to summarize the whole thing, this is where we yesterday talked about mostly, is that these are all your internal combustion system. So, as I said, there are two categories of the combustion system that you can broadly do. One is internal, one is the external, and this is pretty much that internal combustion system that we have talked about. Now, the internal system also you can put in two segment. One could be steady flow segment, another could be unsteady flow segment. So, this particular table actually summarizes everything for the internal system. So, in the steady flow you have gas turbine, you have ramjet, chemical rockets, these are the things. Under gas turbine you could have turbojet. So, this is in jet applications, and the work which is produced by the turbine, it is primarily used to drive the compressor. And then you look at the turbofan or turboprop. Turbofan, there is slightly difference from the turbojet. There is a peak fan sitting in front of the engine, which actually sucks the air to the engine. One component goes to core, another component bypassed. So, that is why it says partly jet, and the shaft work is drive the fan, and the popular if it is turboprop. Then you look at the turbo shaft engine, where all the shaft work to drive the propeller, generator or the rotor. Now, when you come down to scramjet or ramjet or scramjet, these are mostly for your space applications and all this. There is no compressor or turbine. So, that means one of the difference from this gas turbine to ramjet or scramjet, they here no rotating component. So, if you are free from compressor or turbine, there is no rotating component, which actually gives you lot of advantage, because these rotating components are always an issue, because then your dynamical system, the behavior of the dynamical system, they create a lot of problem for this kind of GT engines. So, here but the compression is required. So, you get the compression done through the ram effect. Now, the another category is the chemical rockets, where you could have another two subsection, either solid fuel or liquid fuel. So, the solid fuel and oxidant, they are premixed and placed in the chamber, whereas for the liquid fuel you see the fuel and oxidant, they are separated and pumped separately. Now, that is all comes under your steady. When you come to the unsteady, you have a premixed charge, non-premixed charge, stratified charge. If it is premixed charge, you have either gasoline engine or gas engine, which is homogeneous charge spark ignition engine. ACCI engine, this is also homogeneous charge compression ignition engine. So, there is a slight difference between these two. One is the spark ignition engine, another is the compression ignition engine. Now, when you have the non-premixed charge, there it is important to note here that air is only compressed, and then this is like your essentially in your diesel engine. What happens? Air is compressed and then you inject the fuel, and then because of this compression ignition, so the ignition takes place. Now, the stratified charge, you have a partially premixed charge, equivalent ratios charge, these are the systems. So, that is pretty much of your internal system. You can classify and look at these things what in practically you see in daily applications. So, now also we talked about some combustors, basically especially which is used in your GT applications, and these combustors are of like one could be can type, one could be annular type, turboannular type, and this is another schematic of your multiple can. Here you see 1, 2, 3, 4, 5, these are multiple can operation. So, they do take part in the power generation or the thrust generation process. Now, this is another schematic or cut section of the engine with afterburner. So, this is a turbojet engine with afterburner. So, there you see the difference here. You have typically air comes through diffuser, then compressor, then goes through the combustion chamber or the burner, then you pass through the turbine where the expansion takes place, and then after that you have afterburner, which is second level of combustor which is there, where you add more fuel there. So, once you add more fuel there, actually you have an extra burning taking place to generate more power, and then finally you pass through the nozzle, so that this area reduction and all these things produces the high exit velocity. This is quite high, so which is essentially contribute towards the thrust production, towards thrust generation. So, that is how it works. These are the things, some of them already we have discussed, just to show you in a schematically how they look like. Now, once you put down the combustion in gas turbine, you can have other aspect of it, like you have, let us say, spray combustion, because your fuel is liquid. So, this is for liquid fuel, spray combustion. Then you have ignition. So, you can have ignition also, which is another important aspect of it, because without the ignition fuel will not ignite. So, one more important thing is that stability, that is your flame stability. This is quite important when you look at the gas turbine engine, especially in the aircraft application, because flame stability is something which is very, very important. You cannot at given point of time cannot allow to shut off your flame, because then engine will get off and then there would be a huge problem. So, to avoid that issue in any this aircraft applications, there is a pilot flame sitting there, which acts as an igniter. Now, this is for combustion noise. Now, then you have flame propagation, and obviously there are issues like emission. So, pollutant formation, which are CO, UHC, NOx, soot, etc., etc. So, these are obvious choice because we have done quite a bit of discussion on this, because you are burning some liquid fuel which are of CXHY kind of category, hydrocarbon fuel. So, once you burn hydrocarbon fuels, the soot, UHC, CO, these are obvious. Then heat transfer is another important aspect of it, because all your combustor valves, they are exposed to high temperature. So, there will be huge thermal loading along with the liners. So, the heat transfer and then cooling. So, cooling of not only the combustor only, but cooling of the turbine blade also. So, this is another aspect. So, it is both combustor and turbine. So, we need to look at the cooling aspect, because turbine blade cooling is an important area of work which people have been working for few decades, and they come up with a new suggestion or design how one can improve the cooling, and this cooling has a lot of effectiveness in the durability of these blades and all these things. So, without cooling, the blades will fail very quickly, which one cannot afford to do that, because the turbine is one of the key component of this whole business, because the turbine generates the power, but this will dictate the design for both upstream and downstream, because turbine will dictate the maximum temperature here, T max. So, that will dictate your combustion chamber design. Then combustion chamber, there would be not only pressure, temperature, also delta P across that, which will dictate, allow your compressor design, how much delta P I will get across this. So, these are, and also the turbine will power the compressor, and if there is a fan sitting there, and then these exhaust things pass through the nozzle and to produce the. So, this is in GT application, this is one of the very key component which do take part in the design process actively, because it allows this side of the design, this also dictate the downstream of the design. So, there is so this is one has to look at, and that is why now this T max in the turbine, the T max in the turbine is controlled by the blade, the essentially the turbine blade, because this has a some material which has a limit for T max, what it can withstand and what it cannot. So, this T max will actually control, then this is coming from the material perspective, and that is why one has to cool down that material so that the failure does not occur. So, once that is dictated, so you can see that, I mean, in a bigger picture how that dictates the whole business. Now, some problems in GT application, So, some of them are still an existing problem, some of them are quite a bit of handled. So, for example, if you look at NOx control, this is still a problem, one has to actively look at it, and rather the GT industry they look at it, but obviously NOx is not something which is decoupled from another issue is the CO or UHC, because the behavior of CO and UHC is slightly different compared to your NOx, and that is why some level of trade off is required, because NOx primarily, if it is not fuel bound, because of the temperature in the post flame region, the thermal NOx formation is quite active, and that is what dominates. But then at the same time, if your temperature is high, CO completely gets oxidized, so that helps. But if you go to low temperature, NOx could be low, but at the same time CO could be quite high. So, it is basically a win-win situation where one hand this goes up, this comes down, the other hand it goes down, it goes up. So, it is a balancing act between these two. Then your combustion noise, or sometimes people call it hooting. So, this is again an instability, but this has been kind of addressed by lot of GT manufacturer, but still it is not 100% perfect, because some level of noise still comes in. But all said and done, this is something which is actively pursued, and people have come up with some control mechanism so that you can reduce the combustion noise. Then the bigger issue is the soot formation. So, this is something one has to work on, because this is a serious problem even today, because any of these gas turbine, when they are flying, if you look at it, or any automobile engines and all this in the back side of it, this is one thing people have to seriously work on this, because one of the major issue is that these are so small, the soot particles. So capturing soot particles is not that's an easy task. Now, through experiments or rather testing, it is also becoming quite difficult, because the cost involved, manpower involved, fabrications and all these things, and also the equipment which is so sensitive to capture these things. Then the option which is required is the simulations or high fidelity simulation, but in that case also, so that is the other point, that fidelity of CFD code for combustion. This is another area. So, but even then you have capability, the mechanism or the governing equations and the models which are available even today, they are not that I would say high fidelity model that can capture. So, no highly accurate model which can capture. There are models which does predict things correctly, but then when you take it to the real applications, they are so expensive that one cannot afford to do that, and there are simple models, but they are not accurate enough. So, it is again a balancing problem, because some models which can capture it to some extent accurately or reasonable enough accuracy, it can provide you, but problem is that they are highly expensive. So, for realistic applications at that level of turbulence or the flow, it is becoming quite difficult. So, this is another area where the even CFD is an sort of reached a certain matured state, but for the combustion application still it is requires lot of essentially the fidelity part, it has to be looked at. Now, some development has also, these are some of the problems, few of them are addressed and few of them are still being addressed. Now, the developments also there, so we can look at those in gas turbine applications. For example, one try to do that lean premixed combustion. So, the lean premixed combustion which will control obviously NOx, some level of soot, these things would be controlled, but again lean premix means it can goes to some or rather instability. So, you can see there, to control these two parameter, you have a solution where you people can go to the lean premixed, but then you come back with this problem, the instability. So, this is an always, as I said, it is a balancing act between one with the other. So, one you can control, the second one will create trouble, or second one you try to control, the other one will be a problem. Then which is another is that you do some sort of an hydrogen doping, which will sort of increase your some sort of an efficiency, control the NOx. So, some advantage it will provide. And the other thing is that higher pressure ratio, and obviously combustor design change. So you can use some sort of an combined combustor things, whether it's a sort of like annular or cannular tubular, they can be used in that way combiningly, and that can give you better situation. Now when you go to ramjet kind of situation, it's simple and rather simplest of air breathing system, air breathing engine. Now only thing it contains some diffuser, that is one thing, CC combustion chamber, and nozzle, exhaust nozzle. So these are the component it has, but the application is sort of more suitable for high speed, or rather supersonic speed, where Mach number is greater than 1, because the compressibility or compression is done. So compression is achieved by ram effect only. So it does not have any rotating component like compressor or turbine or fan or anything such that. On one hand, that is an advantage, because one can avoid these rotating machineries or turbo machineries, because turbo machineries give you a different kind of challenge altogether. So another obvious is that the fuel injection into compressed flow. So the flame holders is used to stabilize the flame, and then finally hot product or hot gas expands in nozzle. So that's how it works. Basically it gives you an idea about the working principle of this ramjet system, and this is what it is. You can look at this schematic and find out. So this is the diffusion portion. This protruded portion creates, and because it's a high speed case, so because of this the diffusion takes place, and then there are flame holders where fuel is injected. This is your combustion chamber. So it's more like an it's not typically what you see in a gas turbine application. There are can, tube, annular or some kind of a combustor. It's more like an very simple shape, annular kind of shape what the nacelle which has, and there are these are the flame holders. These are flame holders actually. So one obvious issue which becomes bit critical here is the flame stabilization behind these flame holders, because the airspeed is too high, and due to diffusion it does not come to a level where the flame stabilization becomes. So that is one of the again challenging area for this kind of application or the ramjet application, because flame stabilization, and then you have also sort of a limitation of the fuel. It's all the fuels, each fuel has its own or different calorific value. So that will tell you what kind of fuel one can use at this speed that the flame stabilization is very effective. So that's an area which requires lot of attention. Then finally it passes through the nozzle to get the these things. Now, when you come to the rocket application, or rather I would say chemical rockets, what you have two categories of that. One is the liquid fuel rocket. Here we have already told that fuel and oxidizer, they are stored separately and they are stored in a thin wall tanks at low pressure. So, your fuel and oxidizer, they are stored in a thin walled low pressure tank. Okay. So, they are through the turbines, they are pumped into the turbine, basically the turbine driven pump, they actually pump the thing to the combustion chamber, and there the burning takes place at high pressure. So, that is how it works. Then other one is the solid fuel system, where your entire block of the propellant, that is both fuel and oxidizer. So, they are stored, entire block of the propellant stored within the combustion chamber. So, now combustion actually proceeds from the surface of the propellant. So, from the surface of the propellant grain. So, one can note that combustion proceeds from the surface of the propellant grain. So, that at a given rate depends on pressure and temperature. So, and also this combustion rate, so this will have an impact from the pressure, temperature and also the geometry of the grain. Now, this is just to give you an idea what kind of schematic it has, but they are much more complicated than what you see here. These are very simple schematic diagram to just give you an idea how things are. So, this is a liquid rocket where there is a pump sitting there, you have oxidizer, you have fuel. So, these pumps are actually injecting this into the engine. So, this is the engine, and then finally it passes through this nozzle where it generates that huge amount of thrust. And when you look at the solid, this is the propellant block, this is the total propellant block where fuel plus oxidizer, they are already premixed. Now, they are sitting within the combustion chamber and the reaction starts from this surface, and the rate is obviously this reaction rate is depends on pressure and temperature and specifically the geometry of grain, that is a propellant grain, because the geometry has a huge impact, this grain, the propellant grain, how this combustion will proceed and what will be the rate. And but again that is here the issue is that the solid propellant, the control of these things is not very easy, because they are already within the combustion chamber, and once it ignites, the control of the propellant is not that easy. But whereas when you look at this liquid one, and when the fuel and oxidizer, they are injected separately to the system through the pump, turbine driven pump mechanism, to some extent you can control the flow of these liquids or the fuel or oxidizer, but here there is no such mechanism which exists in the solid case. Once it is ignited, that is a sort of an self driven system or self sustaining system which will keep on burning this propellant. So, the control of these things are not that easy, and then top of that, when that happens, it is quite, I mean, lead to instability. So, combustion instability in the solid propellant rocket are quite common, that because the things are not that controlled. So, okay, we will stop here today and continue the discussion in the subsequent lecture.
Swayam Prabha. Digital India. Educated India.
Welcome back, and let us continue the discussion on this internal reacting system. So, we have already discussed the different aspect of the gas turbine engines, and then we looked at the chemical rockets and also the ramjet kind of engines in a brief. Now, we will continue from here the discussion. This is where we stopped the chemical rockets. Now, we will look at the non-equilibrium expansion. So, how that impact. So, non-equilibrium expansion. So, equilibrium composition, essentially composition which is equilibrium compositions, it depends on pressure and temperature for a given fuel and equivalence ratio, and also it may possible that it may include large quantities of dissociated material. Okay. Now, when you go to the exhaust nozzle, the dissociated compounds tend to recombine because of temperature drop. So, in nozzle, the dissociated compounds tend to recombine due to temperature drop. Now, what happens, this exothermic recombination reactions may act as a heat source in the flow. So, these are this recombination process, the recombination is exothermic. So, they can act as heat source in flow. Now, we can see how this dissociation energy is before and after the equilibrium expansion for a. So, we take an example of, let us say, H2O2 mixture and see how that actually affects. Let us say we put a diagram here, and some axis could be 20, let us say 40, 60, 80, 100. So, this is your energy percentage. And we get some, let us say, block here, and so there would be 1, so this could be 1, this could be 1, so this is what it is. So, this is for combustion chamber at 40 atm and 3500 degree Kelvin. So, this is your electronic energy 0.1%. So, this could be 26.6%, this is vibrational, so which could be 16.6, rotation which could be 19, this is primarily translation which is 37.8, roughly like that. Now, we can look at the nozzle exit and get a block like that. This is nozzle exit which is 1 atm and 2500 degree Kelvin. So, somewhere this is here, then this is here, this is here. So, this is 46.4, this is my translation which is 22, rotation 12.7, vibration 9.2, and this is 9.7%. So, this guy and here and this guy here, this is the dissociation energy. Okay. And this electronic energy would be here for small percentage, and this is the kinetic energy. So, you can see the differences here. This will illustrate the relative importance of these dissociation energies before and after an equilibrium expansion. See, this H2O2 mixture is stoichiometric. So, this is an H2O2 mixture, this example, and they are at stoichiometric. Now, if you have a product to maintain the equilibrium composition while expanding, recombination reaction should be fast enough to keep pace with rapid expansion. Okay. Now, the expansion process is rapid. So, expansion process is rapid. So, that is why this condition is not always met. Now, in a limiting case, one can have tau of recombination which is greater than the expansion. So, this is your exactly frozen flow condition. These things are happening inside the rocket engine. Now, there is a difference between equilibrium and frozen flow for different propellants. So, that is there. Now, the problems in the rocket engines, there are some problems in rocket engines. One of the issues is that instability, as I mentioned there. I mean, obviously this exists both in liquid and solid case, but solid case it is more compared to liquid case. Then you have low frequency oscillations, which is roughly 100 Hz, due to the coupling between combustion and the feed system. Obviously, you will have high frequency oscillation too. High frequency oscillations. This is something called thermoacoustics, or coupling between combustions and the acoustics and flow field, something like that. Then you have some things very specific to the solid propellant rockets, which is like in solid propellant, burning rate is very sensitive. Burning rate is very sensitive to pressure and velocity. Then you have energy release and propellant velocity, or the pressure pattern that causes non-homeotic and interact to the produce sustained oscillation also. So there could be oscillation from other sources, and this comes from that energy release, and that coupled with the propellant velocity and or the pressure pattern that develops inside the chamber. Now these oscillations lead to high rates of erosive burning, and that could also, so this could lead to erosive burning, and that may change the chamber geometry to stable burning or may lead to engine failure. So this has both the aspect. It could lead to stable burning or engine failure. So both are possible. Then the problem is, as I mentioned, the burning rate of solid propellant. So this is not very controlled. This is not controlled or not easy to control. And in liquid case, obviously one of the issue which is very well known and well common is that atomization or mixing. So these are some of the issues which actually exist even today. I mean, and it requires a lot of attention to control this kind of issues. Now we will move to, so this is our steady flow pattern of the, I mean basically the engines which comes under the steady flow conditions. Now in the unsteady there are, we can look at this SI and CI engines, which are compression ignitions and spark ignition engines. So they are also internal combustion system. They are also internal combustion system, but unsteady flow. Now SI engine has a cycle which is known as Otto cycle, which is or this is basically for your gasoline engine, petrol engines, and CI engine is basically your compression ignition engine. This is for diesel engine cycle or HCCI engine cycles. So they have these things, and one can see schematically how these two things are different. So let us say you have a spark plug sitting there which comes through, then you can define your combustion chamber like this, where you have a piston head and this is the piston movement which happens, and this portion is your the flame. And the other case you can have this is my piston head. So here these are my this is spark plug. This is my CI engine or gasoline engine. This is SI engine. This is spark ignition engine. This is compression engine. So this would be your gasoline. This is diesel. So this is your P mixed charge and this is non premixed charge, and this could be your flame surface. So that's my flame front. This is spark plug, and inside that you have fuel plus air mixture. Here it is air only. This is my fuel spray flame, and that's the fuel injector. So there is a difference you can see inside that. There is a fuel and air which is already premixed, they are sitting there, and this case it is only air which is compressed. So the working principle is quite different, and that is why the problems which will arise in each of these cases, they are also quite different, because this particular case in the SI engine or the gasoline engine, there is a chance of auto ignition or knocking or something like that because of your fuel air premixed, but in the diesel engine you do not have the possibility of knocking or all this, but emission level is quite high. So one can look at some schematic of this 4-stroke SI engine. This is our 4-stroke SI engine operating cycle. Now this is first is the intake stroke, that means it comes down, so air comes in, this valve opens, air comes in, so the volume increases here. Basically the rather it's a mixture comes in, then compressor, it is compressed, and towards the end of this compression you actually ignite that through the spark. Then when the combustion takes place, it actually allows this piston to move, so the expansion takes place, and then finally exhaust stroke, these valves open and things go out. That's a simple operating principle, and this you can typically see in your 4-wheeler car which are on road. Even today they operate in this kind of cycle. There is a in-cylinder combustion which is going on, and this happens so quick, probably you will not be able to understand how quickly it operates, and but you get the acceleration, because people only do accelerate by pressing that accelerator, but this is what goes on. More you accelerate, that means these revolutions becoming faster, it generates the power quickly. So this most of the reciprocating engines, they are operate on this 4-stroke cycle. So each stroke essentially, or rather each cylinder, it requires 4 strokes of its piston. So, that means 2 revolutions of the crankshaft. So, that is required to complete the sequence of events which produces 1 power stroke. So, this is required to produce 1 power stroke. Okay. Now, both CI and SI engines use this kind of cycles, and as we have seen, there are 4 strokes. One is intake, compression, power, exhaust. So, these are my essentially 4 strokes that is required. Now, what happens in each stroke? Actually, if we first take the intake stroke, so it starts at top center or top dead center TDC and ends with BDC or BC, bottom center. So, which allows a fresh mixture into the cylinder. So, that means fresh mixture enters there. Now, to increase the mass inducted, inlet valve opens shortly before stroke starts and close after it ends. Now, similarly, we can see what happens in the compression strokes. Now, your both valves are closed at this state, okay, and the mixture is now compressed. So, the mixture which is within the cylinder, it is now compressed through the piston movement. Now, toward the end of the compression stroke of this process, ignition takes place. So, that is the through spark plug. So, that means the combustion is immediately initiated and the cylinder pressure increases quickly. That means the rapidly the pressure increases. So, then as soon as that happened, what happened in the power stroke or expansion stroke? So, there the piston starts at again top center and ends at bottom center. So, now since the combustion got initiated inside the cylinder, you have high pressure, high temperature gas which will, so this high PT gas push the piston down and it force the crank to rotate. So, one can think about around 5 times as much work is done on the piston during the power stroke as the piston had to do during compression. Now, the piston approaches towards BC. So, towards BC the exhaust valve opens, okay, and then the exhaust pressure actually drops down to close to the the cylinder pressure is dropped down to close to the exhaust pressure, and in the last stroke or the exhaust stroke, since the cylinder is higher than the exhaust pressure, so it allows pushing those gas back towards the top center. So the piston moves towards TC. So as this is approaches towards the TC and towards the end, that valve closes and the cycle starts again. So this is how one go about it. So now there could be, this is 4-stroke cycle where you have, now if you go to 2-stroke compared to 4-stroke, 2-stroke SI. So in 4-stroke you require 4 engine cylinder and 2 crankshaft revolution. So in 4 strokes requirement was 4 cylinder, 4 cycles, then 2 crankshaft revolution for 1 power stroke. Now to obtain higher output for a given engine size is simpler valve design 2-stroke cycle that uses. So 2-stroke has simple valve to obtain higher output. So this is also applicable in both SI and CI engines. So it has only 2 stroke, one is compression stroke and second is the power stroke or expansion stroke. So the 2 stroke will have only, so one can see this is a 2-stroke engine operating cycle. So what happens here? Here this is the revolution, you require only that, this is the compression process. So it starts by closing the inlet. So this inlet is closed and the process starts and the exhaust port opens. Then the compression, the cylinder contents and draws phase charge into the crankcase as the piston approaches towards the top center. Okay. And the combustion is also initiated by the spark plug. And then in this stroke, so this is combustion, expansion, ports closed. So this is basically in the 2 process where you can see. Now this is the exhaust or the rather the expansion and the power stroke, where similar to that in power cycle. So unless the piston reaches the BC, when the first exhaust port open and this happens. So essentially it is happening in 2-stroke cycle. We will actually complete this discussion in the subsequent lecture and we will stop here today.
Swayam Prabha. Digital India. Educated India.
Today we will see analysis of structures part 2, which is lecture number 6 in module 3 of engineering mechanics course. Today our topic of discussion will be to determine the internal forces that are developed in a member when it is subjected to some external force. In the preceding discussions, we have dealt with determining the external forces that occur in a member or the forces that occur in the joints in case of connected rigid bodies. In the preceding lectures, we saw some examples of connected rigid bodies like trusses, frames and machines, and we saw procedures to determine the forces that hold them together or the forces that occur in the joints. Today's interest will be to determine the internal forces that occur in a rigid body when external forces are applied. These forces are nothing but the interatomic or intermolecular forces that hold together the various parts of a member from deformation or failure when subjected to external loads. We have seen that in structures predominantly we have two force members and multi-force members. So, we will see how to determine the internal forces for the two force members and then the multi-force members. And the interest in determining these forces lies in analyzing the internal forces for predominantly two types of structures that we use in our civil construction or for other mechanical constructions. They are the beams, which are usually long, straight and prismatic members with supports and which carry loads, either distributed or concentrated loads. The other kind of structures are cables, which are used to tie, say, the electric poles or the cables that are used to carry winches. So, these members have predominantly the tensile forces. So, we will see first how to determine the internal forces in a two force member. Let us consider first a straight two force member AB, which is subjected to the force F at A and an equal and opposite force at B. If we are interested to know what kind of forces are set up at a section, say C, then let us create a virtual section at C and create the free body diagram of one of the portions, say AC. Let us draw the free body diagram of the portion AC. We have the external force F acting at A, and at C the various parts of these members develop internal forces that hold them together with the parts or portion of CB. So, these forces can be represented by these quantities. These are nothing but the various internal forces that hold the portion AC with the portion CB at this section C. These forces are the interatomic forces or intermolecular forces. Now, if we consider the equilibrium of this portion, that is the portion AC of this two force member, then for equilibrium to exist, the sum of all the forces should be 0 and sum of the moments has to be 0. And it becomes apparent that if we consider the axis of this member, and if we sum all these forces at this section C, they have to be equal and opposite to this force, because this portion is again a two force member. So, we have the resultant of all these forces as F, which is equal and opposite to the applied force. Let us now consider a two force member which is not straight and try to determine the internal force that is developed in a non-straight two force member. So, here you see a member ABC which is bent, but it is a two force member because loads are applied at 2 points, at A and at C. We have these loads P that are being applied to this member. For equilibrium to exist, we know that these two forces has to be collinear. So, let us take a section D and draw the free body diagram of this portion AD. We consider this portion AD. We have the external force P that acts at A, and at D we have these internal forces that hold together this portion, that is AD, with the remaining portion DBC. For this portion AD to be in equilibrium, the sum of the forces and sum of the moments has to be 0. That means the resultant of these forces should balance the force as well as the moment due to this force P. So, let us draw the resultant of these internal forces at D. At A we have the external force P, and at D the resultant of all these forces is equal to a force F and a moment M. How do we say that this is the resultant of these forces? If we consider this free body diagram, for the portion to be in equilibrium, the sum of these two forces has to be 0, and the moment of this force P about this point should be equal to this anticlockwise moment m that we have marked at D. So, for a two force member which is not straight, the internal forces reduce to a force and a couple. This force F can be represented by its two components, one along the axis and one transverse to the axis. So, this represents the resultant of the internal forces at D for this two force member. We have designated the axial force and the transverse force as F and V and the moment as M. Let us now see how to determine these internal forces for a multi-force member. So, here we see a multi-force member A, B, C, D, and let us say we are interested to find the internal forces at this section J. So, let us consider the free body diagram of the portion dj, and we know that the resultant of all these internal forces will be a force and a couple, and that is the force is represented by its two components V, which is transverse to the section, and F, which is perpendicular to the section, and the moment is M. This force V tends to shear this member at this section J, and so it is known as the shearing force or the shear force, and this moment M tries to bend the member at this section, and so it is known as the bending moment, and this axial force F tends to compress or extend the member, and so it is an axial force, either tensile or compressive in nature. Let us see how to determine this shear force and bending moment for a, let us say, a three-dimensional structure or a three-dimensional beam. Let us consider an arbitrary structure in space and consider a section say D in this member A, B. Let this member be subjected to some forces, say F1, F2, and maybe some moments M1 and so forth. For the equilibrium of this member, the internal forces that will be developed at this section D can be represented by all these forces. all these forces are three dimensional, they can have any orientation. So, let us consider this section. The resultant of all these forces at this section D, if let us say these are the local coordinates of this section, let me call this as small x, this as small y, and this as the z axis. So, the resultant of all these forces will be a force and a moment. So, these are the internal forces at this section D. If we take the components of this force, so we have a component along x, we have a component along y, and we have a component along z. So, let me designate these as Vy, Vx and Vz. The force Vx is along the instantaneous axis of this section, or which is perpendicular to this section, and thus causes a tensile or a compressive force on the member. These two forces, that is Vz and Vy, which lie in the plane of this section, tends to shear this structure in the plane zy. The force Vz tends to shear the structure along the z direction, and the force Vy tends to shear the structure along the y direction. So, these forces are the shearing forces. Let us similarly consider the components of this moment. So, we will have a moment component mx, a moment component mz, and a moment component my along the x, y and z direction. This moment, that is mx, tends to twist the member at this section D. So, this is known as the twisting moment. This moment mz and the moment my along y and z directions, they tends to bend the member. So, the moment my bends the member in the plane xz, and the moment mz tends to bend the member in the yx plane. So, these two moments are the bending moments. So, we see that the resultant of the internal forces tend to twist, bend, or axially compress or extend, or shear the member at any given section. So, knowing the behavior of these internal forces, it is possible to now design the member to resist these forces. The aim of design of various members of, let us say, the trusses or any machine or beams is to select suitable material and the cross sections that can resist these internal forces. With this understanding, let us move to analyze beams for the internal forces that are developed in them, and then we can move on to design beams, which obviously is not covered in this engineering mechanics, but later on in your second course you will be studying the design of beams or design of various other structures. Here you see in the accompanying picture what we call as beams that are used to support the roof of this structure. So, beams are generally long straight members which are used to support loads in the transverse direction. So, here you see this beam supporting the slender beams, and these slender beams in turn are supporting the roof of the structure. The loads, as you see, are perpendicular to the axis of the beam. Like for this big beam, you see that the forces from the slender beam are perpendicular to the axis, and also for these slender beams you see the load from the roof comes in the transverse direction. And we have already seen that if we have only loads in the transverse direction, they will cause only shear and bending, and they will not cause any axial force if it is a straight member. The loads could be either concentrated, as you see for this big beam, where the slender beams apply the load at these points, or it could be a distributed load like you see for these slender beams, where the roof planks apply continuous loading all along the member. The beams can be supported by various ways. Here you see a beam that is being supported by a roller and a pin, or a beam could be supported by embedding it into a wall like this picture, as shown in this picture, or the beams could be overhanging, that means they extend beyond the support. In order that we are able to determine the internal forces, the supports should be statically determinate. So, let us see the kinds of supports that result in statically determinate reactions for beams. First, let us consider this simply supported beam. We have a pin connection at this end and a roller connection at this end, and if we draw the free body diagram of this beam as a complete structure. At A, since it is pinned, we have two components of reaction. Say if this point is A and this, let us call it as B, we have AY and AX, and at B we have a single component of reaction BY. And we know that for the equilibrium of this member, the sum of the forces and the moments have to be 0, and in plane this results in 3 equations from which we can determine the 3 unknowns, say AX, AY and BY. So, this combination of support is a statically determinate support reaction. Here we see what we call as cantilevered beams, or beams which are embedded into walls at one of their ends. So, let us draw the free body diagram for this beam. Let us designate this point as A. At A, since all degrees of freedom are arrested, we have the two components of force AY and AX, and as well as there is a moment reaction. From the equilibrium of this member, we have 3 equations which can be used to determine these 3 unknowns, namely AY, AX and M. So, cantilevered beams are also statically determinate. This kind of support configuration leads to what we call as continuous beams. Let us designate this point as A, B and C. Here we see 2 beams are pinned at B, and this beam is supported BC, the beam BC is supported by a roller at C, and the beam AB is cantilevered at A, that means fixed at A. So, let us draw the free body diagram, and in order to develop the equilibrium equations, we have to dismember it as 2 members AB and BC, because we have already discussed that if we remove a structure from its supports, if it collapses, then we cannot consider the free body diagram of the complete structure. So, in this case, if we remove this structure ABC from its support, obviously it collapses. That means the beam can rotate about this point B. So, we consider the free body diagram of the dismembered beam. So, first let us consider the beam AB, and at A, since it is fixed, we have the 2 components of reaction and the moment reaction, and at B, since it is pin connected, we have 2 joint forces, say By and Bx. Since the beam BC can rotate freely about this point B, there is no moment force at this joint. Let us consider the free body diagram of the beam BC. At B, we have an equal and opposite joint force as shown in the free body diagram of AB. So, we have these forces Bx and By, and at C, since the beam is supported by a roller, we have a vertical component of reaction, say Cy. Now let us see how many unknowns we have. We have 3 unknowns at A and 2 unknowns at B, totaling to 5. And from this free body diagram, this Bx and By have already been accounted for in this free body diagram. They are only opposite in sign, so they do not constitute a new unknown, and we have one more unknown, that is Cy. So we have a total of 6 unknowns to be determined. For the equilibrium of this rigid body AB and rigid body BC, from the equations we get to know 3 unknowns for each free body diagram, and since we have 2 free body diagrams, so we get 6 equations, and since the number of equation and number of unknowns are equal, the problem is statically determinate. Let us consider another example of a continuous beam. Here we have a beam ABC which is pinned at A, supported by a roller at some point between AB and at C. Again we see that if we dismember or if we remove this beam from its support, it collapses. So we dismember and construct the free body diagram. Let us draw the free body diagram for the beam AB. At A we have 2 unknown reactions, AY and AX, and at the roller we have, let us say this point is D, we have a vertical component of reaction, and at B we have 2 joint forces, say By and Bx. For the next member, that is BC, we have these joint forces By and Bx, and at C we have the vertical component of the roller reaction. So let us count the unknowns that we need to determine and see whether we have sufficient equations to determine. So from this free body diagram, we see that we have to determine 2 plus 1 plus 2, a total of 5 reactions, and from this free body diagram only Cy is the additional unknown, since Bx and By have already been taken care of. So we have a total of 6 unknowns, and from the 2 free body diagrams we can write 6 equilibrium equations and all the 6 unknowns can be determined. So this is also a statically determinate support reaction. Beams can be subjected to point or distributed loads as shown in these figures. So here you see a point loading configuration, like a force of P1 acting at B and a force of P2 acting at C, and here you can see a distributed load, either uniform distributed load or a varying distributed load acting on this beam ABC. For all these configurations, if we have statically determinate support reactions, we can determine them, and thus it is possible to proceed to determine the internal forces. So the problem of beam design can be stated as that first we are interested in finding the internal forces that are caused because of the externally applied force. That is, we are interested to know the shearing forces and the bending moments. And once we have determined these internal forces, we now design the beam cross section and we select the beam material which can resist these forces under the applied load. Here you see some examples, like you see an I section beam which is made of aluminum. Here you see a hollow section beam, the material could be steel, or we have these wooden beams which are solid. So, in order to determine the shear force and bending moment, we consider the free body diagram of a portion of a beam and determine the unknown internal forces. So, let us see an example. Here you see a beam which is pinned at say A and has a roller support at B, and we are interested to find the shear force and bending moment at a section say C. We have some applied loads P and Q. So, first we determine the external reactions, and at B we have the vertical reaction By, and at A, since it is pinned, we have Ax and Ay. And we know that from the free body diagram and equilibrium equation, these three unknowns can be determined. Now, we consider a portion of the beam that is sectioned at C, either it could be the portion AC or the portion CB. Construct the free body diagram and determine these internal forces. So, here you see the free body diagram of the portion AC, and at section C we have the resultant of the internal forces having components V, which is the shear force transverse to the axis of the beam, and H, the axial force along the axis of the beam, and the moment M, which is the bending moment. And in the other free body diagram, that is the free body diagram of the portion CB, these forces are equal, but they are of opposite sense. Like here V is vertically upward, and then in the other free body diagram it is vertically downward. These directions that have been shown are taken as the positive convention, that is, the shear force marked vertically upward on the left hand portion, that is AC, is taken as the positive shear force, and the axial force is taken positive along the positive direction of x. If we designate these local coordinates x, y and z perpendicular to the plane of paper, and the moment m, which is the counterclockwise moment, is taken as the positive bending moment. The positive convention has been chosen from their effects. We have seen already that the shear force V tends to shear a beam, and the direction of the force V tends to shear the beam in this fashion. And let us consider this bending moment M. This tends to bend the beam in this fashion, and the axial force H tends to pull this member, thereby the member is subjected to tension. So, these effects are taken for the positive conventions. Let us consider a simple example problem. Let us consider a beam AB with a roller support at A and a pin support at B, and a concentrated load of 100 Newton, 1000 Newtons at C, and say a point moment of 500 Newton meter. The various dimensions. All dimensions are in meters. Let us say we are interested in finding the shear force at a distance x from the end A. How do we proceed? We first construct the free body diagram of the complete beam to determine the external reactions. So, let us draw the free body diagram. At A, we have a roller support. So, we have one component of unknown reaction, and at B, we have two components of unknown reaction, and we have the applied loads 1000 Newton and a point moment of 500 Newton meter at C and D. Now, from this free body diagram, we can write three equations which can be used to determine the three unknowns. So, let us write those equations. We can write the force summation equation for the vertical component. So, we have the force Ay, the force By, the two unknown vertical reactions, and the vertically applied load which is downwards equal to 0. Now, let us write a moment summation equation about A. We have the 1000 Newton force having a clockwise moment about A, so which is a negative moment. So, we have minus 1000 into 10, which is the momentum. At D, we have a clockwise moment of 500 Newton meter, so which is also a negative moment. And at B, we have two unknown reactions, that is Bx and By. The moment of Bx is 0 because it passes through A, but the moment of By is counterclockwise, so which is positive, and the moment arm is 40 meters. So, we have plus By times 40 equal to 0. Then let us write the force summation for the x axis. We have only one horizontal component of the force, that is Bx, and so it has to be 0. So from these three equations we can determine the three unknowns, that is Ay, Bx and By. We have already found that Bx is 0. By solving 1 and 2, we find By to be 262.5 newtons and Ay as 737.5 newtons. Now we can proceed to determine the internal forces, that is the shear force and bending moment. To determine the shear force and bending moment at this section C, or a section at a distance x from A, we consider the free body diagram of the section, which is at x meters from A. We have the applied load of 1000 Newton at C and the reaction Ay, which has been found to be 737.5 Newton. The resultant of the internal forces at this section will be the shear force. We can see that since there is no horizontal forces, the axial force is 0. Even if you will consider the axial force from the free body diagram, it will turn to be 0, and we consider the moment m. Both have been taken in the positive sense as discussed. Now from this free body diagram, let us write the equations. First, let us write the force summation equation, which gives that V plus Ay should be 0, because we have the vertical component of the force V and the vertical reaction Ay. Now let us take the moment summation about this point, that is a point on this section. Why we would like to take it? We can take it about any point, but since V is an unknown, we can avoid it in the moment equation if we take the moment summation about a point on that section of our interest. So let us take the moment and equate it to 0. So that states we have this force Ay, which causes a clockwise moment at this section. The moment arm is x meters. So we have Ay times x, which is a negative moment because this is a clockwise moment about this section, and we have the moment of this 1000 Newton force, which will be counterclockwise about this point. So we have plus 1000 times the moment arm will be x minus 10 meters, because this force of 1000 Newton is being applied at 10 meters from this end A. So we have the moment arm as x minus 10, and we have this moment m, which is a positive moment. Since we have already determined Ay, now we can find V as well as this m, and these two are the internal forces at this section. Similarly, we can consider any section along this beam and determine the shear force and bending moment at that section. Let us consider another example. Here we have a curved beam which is supported by a pin at say B and at A by a roller. This is a circular beam with radius equal to say 6 meters. There is a concentrated load of 100 newtons applied at the midsection of this circular arc beam. Let us say we are interested to find the shear force and bending moment that occur in this beam as a function of theta, where the theta is taken from the point A towards the point B. So, we are interested to find V, the shear force, and bending moment as a function of theta. So, how do we proceed? We first determine the external reactions and then we construct free body diagrams for portions of the beam and develop the equation. So, first let us consider the free body diagram of this complete beam. So, at A we have a roller support and at B we have a pin support and we have an externally applied load of 100 newtons. The radius is 6 meters. So, let us write the equations resulting from this free body diagram. If we sum the horizontal component of the forces, we find that we have only one horizontal force and that is Bx and it becomes 0. Let us take the force summation along y axis. We have this reaction By and the reaction Ay plus the externally applied force 100 newtons along the y direction. So, we have Ay plus By minus 100, the downward force equal to 0. Let us take a moment equation, and it is convenient to take the equation about B. Then we will be able to find this reaction AY and equate it to 0. So, the moment arm of this reaction AY is 6 meters, and this causes a clockwise moment about B. So, we have minus AY times 6, which is the moment arm. The 100 Newton force has a counterclockwise moment about B, so which is positive. So, we have plus 100 times the moment arm of this is, this load is applied at a radial angle of 45 degrees. So, we have the moment arm as 6 cos 45. So, from these two equations we can find AY and BY. Now, after we have found these external reactions, we can move on to determine the internal forces. So, let us consider a portion of the beam before the midsection. Let me call this as C and O. So, we are considering a section of this beam before the midsection C. So, at A we have the external reaction, and we have the shear force V transfers to the member, the axial force say H, and the moment M. So, this V, H and M are the resultant of the internal forces at this section. V is radial and H is along the tangent of the axis of the beam, because this is a circular arc, and M is the moment of all these internal forces. Now, from this free body diagram, let us write the equilibrium equations. If we sum the forces along the x direction, we have, these are the positive x and y directions, we have the component of this shear force in the negative x direction, which is minus V cos of theta, and we have the horizontal component of this axial force H, which is H sin theta, and this has to be 0. Now, summing the vertical components, we have V sin theta, which is positive, plus H cos theta, which is the component of this force in the vertical direction, plus AY equal to 0. Let us take the moment summation about, say, this point O, because this V, the shear force, is radial and passes through this point O, and it can be avoided in the equation, and is minus A y times 6, the clockwise moment of this reaction A, minus H times 6, because this force H is tangential at this point to this radial line. So, the moment arm of this force H is 6 meters again. This plus the moment m has to be 0. From these equations we can find the three unknowns, that is V, H and m. Now we can consider the free body diagram of a portion between C and B, and we can write the equations for shear force and axial force and bending moment. And now we have the shear force, axial force and bending moment as a function of theta as interested by us. We will continue with our discussions on determining the shear force and bending moment in beams in the next lecture.
Swayam Prabha. Digital India. Educated India.
Good morning. Let us take this example. Usually we have this 3 by 3 matrix A, for which we want to find out the eigenvalues and eigenvectors. Okay. So, this is our problem. So, first what we should do? We should find out the matrix lambda I minus A and set that equal to 0 to get the characteristic equation and then find its solutions, or you can say that we find the characteristic polynomial and try to find its roots, right. So, lambda I minus A, that matrix will be lambda minus 2, that is lambda plus 2, then lambda minus 4, then lambda minus 4, and on the off diagonal elements there will be no effect of this, these will just become negative. Like this, right. Now, the characteristic polynomial is the determinant of this matrix, right. So, you will Now, the characteristic polynomial will be the determinant of this matrix, right, which you can expand from here. That means, you will take lambda plus 2 into this minus this, right, lambda plus 2 into, from here you will get lambda square minus 8 lambda plus 12, then minus this minus 1, which will give you plus 1 into the determinant that you find from these 4 elements, right, that will give you 8 lambda minus 16 plus this minus 2 into the determinant that you get out of these, right. So, that you find as this. As you simplify this, you will get this. Now, this particular polynomial is very easy to factorize, because you can see that it is the exact cube of lambda minus 2. So, factorization in this case is actually very simple, which will not be so in the case of a general polynomial or general even cubic polynomial. And this tells you what? This tells that the characteristic polynomial p lambda has 3 roots, which it must have, but in this case all 3 roots are coincident. That is, there is a single eigenvalue and that eigenvalue is 2. That means, a single eigenvalue appearing thrice. So, you have got lambda 1, lambda 2, lambda 3 all equal to 2. This is a very special case. Now, we say that for this eigenvalue, then we would like to find out the eigenvectors. It would be nice if we can find 3 linearly independent eigenvectors, but it may be possible that we find only 2 or we find only 1. So, for doing that, then what we need to do? We need to write the full equation from here, lambda I minus a into the vector v equal to 0. So, as we do that, for finding eigenvectors, we will take lambda I minus a into v equal to 0, or that same lambda I minus a we can use by putting lambda equal to 2 here, right. So, that will give us 4, 8, 4, minus 1, 2 minus 4. That means, minus 2, minus 1, and finally, in the third column, minus 2, minus 4, and then 2 minus 4. That means, minus 2 into this eigenvector. Now, how to solve this? You will say that we will use the same old method, we will apply elementary row transformations, and in this case it is very easy, because it is found that the second row is exactly the same as the first row, but exactly the same as twice the first row, and the third row is same as the first row. That means, actually the second row and the third row through elementary row operation will immediately go out, and only the first is something which is of use, right. So, through an elementary row operation in the second and third rows we will get all zeros. So, they are anyway useless. It is only one equation which is of use. So, we take that equation and say that if we represent v as this vector, then that equation will mean 4 alpha minus beta minus 2 gamma equal to 0. Now, what alpha beta gamma will satisfy this? Any set of alpha beta gamma that satisfies this is an eigenvector. Now, we will say that the scale has no importance for an eigenvector. That is, if you have decided alpha beta gamma as some values, then making them twice or thrice or halving them will have no difference. That will not be reckoned as a different eigenvector. So, one of these three we can set. So, suppose we set gamma equal to 1. That will give us 4 alpha minus beta equal to 2. That means that still we can choose alpha and then we will get beta, right. So, different choice of alpha will give us different beta. So, for example, suppose we choose alpha to be 0. So, then we get one eigenvector in which alpha is 0 and beta will then turn out to be minus 2 and gamma is anyway chosen as 1. In another, suppose we choose alpha to be 1. If we choose alpha to be 1, then we will get beta as 2, right. Then we will have this satisfied. So, 1, 2 and gamma is already chosen as 1. So, these are the two linearly dependent eigenvectors, linearly independent eigenvectors. You can see that they are linearly independent. Okay. So, two linearly independent eigenvectors you have got and only 2 you will get, because no other independent choice is possible. Any third choice of alpha will give you something which will be only linearly dependent on these two. That is, it will be a linear combination of these two. So, in this case we have got only 2 eigenvectors, not a full set of 3 eigenvectors. That means that this particular matrix is not diagonalizable, it is defective. And since it has got 2 linearly independent eigenvectors, that means that it will have 2 Jordan blocks in its Jordan canonical form. One Jordan block will be a 1 by 1 Jordan block, which will have only 2 the eigenvalue, and the other Jordan block will be a 2 by 2 Jordan block of this kind. Okay. Now, in order to get up to that Jordan block, we will need to find out a generalized eigenvector apart from these 2 eigenvectors, right. So, this is what we expect to be the look of the Jordan blocks that we will get, right. But we will actually find that after we get the complete basis, that is other than the 2 eigenvectors, after we find out the generalized eigenvector also. So, to begin with, suppose we want this fellow to admit a generalized eigenvector and try to find out the generalized eigenvector. So, the generalized eigenvector W will satisfy this and A minus lambda I. So, whatever just now we wrote as lambda I minus A, this matrix is actually its negative. So, that negative matrix I am reproducing here. This. So, we are looking for the generalized eigenvector corresponding to this eigenvector V1, right. And then what we can do, again the same elementary row operations will mean that these 2 rows become completely 0. Let us apply those 2 elementary row operations, R2 minus twice R1 to be put in R2 and R3 minus R1 to be put in R3. So, that means from the second row we twice the first row. First row remains unchanged. From the second row, okay, on this side also, first row remains unchanged. From the second row, twice the first row is subtracted, 0, 0, 0, minus 2. From the third row, the first row is subtracted. So, 0, 0, 0, 1. Can you see that this system of equations is actually inconsistent? Because whatever is W, the second and third row will give you 0 on the left side, but non-zero numbers on the right side. That means this system of equations is actually inconsistent. That means that V1 does not admit a generalized eigenvector, right? That means the generalized eigenvector has to come from some other eigenvector. So, we try with V2. V2 1 2 1 like this. And when you do that in these row operations, as we subtract twice the first row from the second row and the first row from the third row, here from the second row twice the first row is to be subtracted, and here you get 0. And then when you subtract the first row from the third row also, here also you will get 1 minus 1, 0. Now, this is consistent. Sorry, the first row remains unchanged. First row remains unchanged. You get this. Okay. So, first row remains unchanged and the second and third rows get 0. Now, this is consistent. Okay. So, as this is consistent now, then you will find that W can be determined, okay, minus 4 first element of W into plus 1 into second element of W plus 2 into third element of W is 1. So, from there any W vector which satisfies that equation is a valid generalized eigenvector to be used with the second eigenvector. So, suppose we can take W to be 0 1 0. So, you see 0 1 0 will give you 0 plus 1 plus 0, which is satisfied. So, in the 3D plane, 3D space, this one single equation is actually acting like a plane. So, any vector which is from the origin to this plane defined by this first row is actually a valid generalized eigenvector in this case. Okay. Now, we address 2 points. One is that the similarity transformation matrix S that we get out of this whole thing will then be the first eigenvector, the second eigenvector, and this generalized eigenvector which is associated with the second eigenvector, and that is why it is placed after the second eigenvector. We find out its inverse and then try to calculate this, and I leave it for your verification to find out that the resulting matrix turns out to be this, which is the Jordan canonical form, in which there are 2 Jordan blocks, one is this, the other is this, and in this particular case both the Jordan blocks are corresponding to the same eigenvalue, which is repeated here 2. So, 2 has this Jordan block as well as this Jordan block. Both the Jordan blocks are actually corresponding to the same eigenvalue. In this particular kind of situations, the problem is actually a little more tricky than it seems till now. In this case, corresponding to this eigenvector, we tried for a generalized eigenvector, we failed. For the second eigenvector, we tried and we succeeded in finding a generalized eigenvector, but that was not necessary. We might not have succeeded. For example, when we chose alpha to be 0 and alpha to be 1, then we got these two eigenvectors. In another situation, we could have chosen a different value. If we had rather chosen V1 as 102 and V2 as this, we could have chosen that. You can verify two things. One is that these two are also bona fide eigenvectors for this matrix, and second is that if you take this and try to find W, you will fail. If you take this and try to find W, we have already failed, that we have seen. Then where do you get that generalized eigenvector W? For that, you can argue that these two eigenvectors belong to the eigenspace of eigenvalue 2. That means they are eigenvectors corresponding to the same eigenvalue. That means in that eigenspace, any linear combination of these two is also an eigenvector, and that eigenvector if we take in terms of AV1 plus AV2, then you can find out that for which value of A and B we get an eigenvector which admits an generalized eigenvector. I leave this for you as an exercise in which you can say that you want to solve the generalized eigenvector from this. Okay, this is basically AV1 plus BV2, a linear combination of these two eigenvectors. And if you try to do that, then you will find that only for a specific combination of values of A and B, you will find that a generalized eigenvector is admitted, and that turns out to give you this eigenvector. That means in the Jordan canonical form, in the basis matrix, this eigenvector must come. So this much I leave for you as an exercise, and right now we proceed with the next lesson in our study, which is the lesson based on plane rotations. As I told you in the previous lecture that in the next 4 lessons we will be studying 4 methods for finding suitable similarity transformation to bring about diagonalization of a matrix, and these are the different ways by which we work out suitable similarity transformation. So the first method to find suitable similarity transformation is based on rotations, plane rotations. And make note that now onwards most of our discussion will be focused on symmetric matrices, which have a lot of interesting properties which we have seen in the previous lecture. So in this topic we will first try to see the geometric implication of plane rotations and how they give us suitable basis change and suitable similarity transformation matrices, and then based on plane rotations we concentrate on 2 methods, Jacobi rotation method and Gibbons rotation method. First we study the plane rotation. In a simple 2D plane, xy plane, suppose we have got a point P with coordinates xy, and we want to make a basis change, that is we want to change the frames of reference through a pure rotation such that the x and y axes undergo a rotation of phi. So the new x axis is along x prime and the new y axis is along y prime through a rotation of angle phi. Now in the new x prime y prime axis, the new coordinates are x prime and y prime, that is OK and PK. Now if we want to express the old coordinates x and y in terms of these new coordinates x prime and y prime, then this x OM is a sum of OL plus LM, right. So, x is OL plus LM, and OL from this triangle OKL, you find that OL is x prime into cos phi, OL is x prime into cos phi, and this LM is same as the parallel Kn, which from this large triangle PNK, you find that Kn is the same as y prime into sin phi. So, you get this. Similarly, when you try to find out y, you find that y can be conveniently written as a difference of Pn and Mn. So, Pn minus Mn. So, Pn is y prime cos phi and Mn is the same, Mn is the same as Lk, which from this small triangle is given as x prime sin phi. So, you have got this. Now, this shows that the old coordinates can be easily expressed in terms of the linear combinations of the new coordinates, and the coefficients are cos phi, sin phi, minus sin phi, cos phi, coefficients of x prime, y prime in x and y. When we write this in terms of a matrix vector product in which the matrix houses these coefficients and the vector houses x prime and y prime, then we find x y vector as a matrix into the vector x prime y prime. The coefficients are put in the matrix. So, that matrix is this. This matrix will be represented as the rotation matrix and with this big R. So, the old coordinates R, old position vector R is found as this rotation matrix big R into the new position vector R prime, right. Now, when we want to find out the new position vector in terms of the old position vector, then what we need to do? We have to find out R prime is equal to R inverse into R, that is capital big R inverse into small r, and R inverse is same as R transpose. So, this matrix finally gives us the mapping from the old coordinates to the new coordinates. In 3-dimensional space, this particular matrix will be augmented with a 0 0 1 row in the bottom and 0 0 1 column in the right side, right. So, corresponding to this matrix in the xy plane, you will have this matrix in which the third column and the third row is the same as identity, which basically means that in this rotation in the xy plane, the z coordinate does not change and the z coordinate does not affect the x and y coordinates at all. So, that fact is obtained through this column, this row and this column. Similarly, a rotation in the xz plane will get represented like this, in which y axis, the second axis, will have a similar situation. So far, we are talking about ordinary physical space. Now, when we go to the algebraic conception of space, in which the dimension could be much larger, then the corresponding n dimensional analog of this kind of plane rotation matrices will have this kind of a structure, in which the PQ plane rotation will be represented like this with this large matrix, in which all the entries are the same as an identity matrix except for the PP, QQ, PQ and QP elements. Okay. So, this is the rotation matrix cos phi, sin phi, minus sin phi, cos phi, the same 4 elements which were appearing here, the same elements are appearing again here in those corner locations. Those 4 corners are the points, are the locations where there is any entry other than what is found in the identity matrix. All other entries with 1s and 0s are equivalent to the identity matrix. Now, this matrix P PQ is the plane rotation matrix in an n dimensional space representing a rotation in the plane of pth and qth axis. Now, when we apply this rotation on vectors, we get relationships like this, that is new coordinates to old coordinates by this transformation r equal to big R r prime, and the opposite, that is r equal r prime equal to r transpose small r. Okay. So, when we apply this basis change on a matrix on a linear transformation, then that will operate like this, that is the new representation of the same linear transformation, that is representation of A in the new basis will be A prime, which will be this basis matrix inverse A into this basis matrix, as we have been seeing all the time. And now, since this matrix is orthogonal, a fact which you can establish very easily, so you can replace this inverse with transpose, right. Now, consider this matrix A, which is symmetric. Out of symmetry, we are representing this as AP1, same as this, otherwise actually it is A1P, but because of symmetry we can represent it as AP1 itself. So, now onwards we will be discussing mostly symmetric matrices. Now, when a matrix of this kind is multiplied on the right side of A, then that AP, the product, will not change any element in this huge matrix A except for entries in the pth column and qth column, because only the pth column and qth column of this matrix has anything other than what is found in the identity matrix of this size. Similarly, when this matrix transpose is multiplied on the left side of A, then no element of A will change except for elements in the pth row and the qth row. That means, through this entire transformation, only those elements, only those members, entries of A get changed which fall either on the pth and qth rows or the pth and qth columns. So, these are the entries, these are the elements of A which are going to change through this entire transformation, right. Now, how they are changed? This is a matter of pure algebraic calculations, and if you conduct those small calculations, then you will find that the new elements of the matrix after transformation, that is elements of A prime, will have these expressions in terms of the old coordinates, old members, that is ARP, ARQ are the RP and RQ elements of the old matrix A, and corresponding APR prime is the APR element in the new PR element in the new matrix A prime. So, these are the changes in the pth row and column except the corner points. Similarly, the elements in the QR row or column, same, because it is symmetric, the transformation is symmetric, the original matrix A is symmetric, and you are multiplying P on the right side and P transpose on the left side. So, the resulting matrix is also symmetric. Now, the corner points change in a quadratic manner, not in the linear manner. Why? Because they get changed once as part of these two columns and then once again as part of these two rows. So, these cos phi sin phi elements enter into the mapping twice among these four corner entries, and these quadratic expressions in sin and cos turn out to be like this. Now, we say that if this is the transformation, then what gives us a method to find a suitable similarity transformation in order to reduce the off diagonal elements and at their cost consolidate the diagonal elements. That is what we want to do when we want to diagonalize the matrix, right. So, there are various choices here. One choice is very straightforward, that is try to make these two corner elements 0, and in that whatever is the consolidation of these corner elements is fine, is welcome. So, when you ask for this PQ term of the transformed matrix to be 0, then you are actually trying to apply what is known as Jacobi rotation. And here you can see that the PQ element of the new transformed matrix is given by this. If you want this to be 0, then you can transpose this on the other side of the equality, and then you can divide by twice sin cos. C here represents cos phi, S represents sin phi. Okay. So, then if you divide both sides by twice SC, then you get this equal to this fellow taken on the other side divided by APQ, twice APQ, because of this 2. And now note, what is this? This is cos square phi minus sin square phi, which is cos twice phi, and this is twice sin phi cos phi, which is sin 2 phi. So, this is cos 2 phi by sin 2 phi, that is cot 2 phi. So, cot 2 phi is equal to an expression of the old elements of A, which is known. So, that means we can solve for phi. Once phi is solved, we have got cos phi sin phi, and so we have got the complete rotation matrix in hand. And using that cos phi and sin phi here, we find out all the changes in the pth row, pth column, qth row and qth column. This will certainly turn out to be 0, because that is the condition which we have used in order to find out the angle phi. Through that, we would have set these two values as 0, and other values in the 2 rows and 2 columns would have appropriately and consistently changed. Now, what do we next? So, we choose PQ one by one in order to annihilate the entries which we want to be reduced to 0. Annihilate means kill, to reduce to 0. So, for that we take PQ first as 1 2. That will mean that we will be working with this corner, and that will mean that these two will turn out to be 0 through the process of P12. Next, we will apply P13 in order to make the 3 1 and 1 3 element 0, and so on. So, like that, as we go on applying the rotations P12, P13, P14, P15 up to P1n, that means one by one we will be trying to set this as 0, then this as 0, then this as 0 up to this, which due to symmetry at the same time we will set these as 0. Next, we move to the second column and second row, and below A22, below the diagonal entry, we will try to make these as 0 0 0 0 0 0. At the same time, these also will become 0 in turn. Okay. So, that means that if we continue like this, then we will have a complete sequence of operations P12 to P1n, then P23 to P2n, then P34 to P3n, and so on. Finally, Pn minus 1n, when we will be operating at this corner, will make this as 0, and that will mean that we have undergone the full sweep. The matrix has undergone through the full sweep of such Jacobi rotations. But then what does it mean? At the end of it, shall we get the matrix as diagonal? Because we set these as zeros one by one, then these as zeros one by one, and so on, and accordingly we have found the rotation matrices and applied those rotations. So, as a result, shall we get a complete diagonal matrix with all subdiagonal entries and all superdiagonal entries 0? That is not right. That will not happen. The resulting matrix in general is far from being diagonal. The reason is that after we have set this as 0 by applying P12 operating on this 4 as the corner points, after this has become 0. Next, when we apply P13 like this, apply using this as corner points, then that transformation will change these two columns, which will mean that it has the potential of changing these entries also, and in general it will change. That will mean that as we apply P13, P14, P15, the old ones, old zeros, that is in A21, A31 locations, they might get changed and stay no longer to be 0. Then the question arises that what was then the necessity of applying Jacobi rotations in a full sweep, or rather what is the advantage of doing it? If older zeros are spoiled in later operations, then what was the great advantage of setting the zeros in the first place? In order to notice that, we need to make a little calculations, and there we define this sum of the squares of all the off diagonal elements. Okay, off diagonal, that is why R is not equal to S, right. So sum of all these, when we try to find out, then that will mean that we take ARP square, that is R not equal to P, and then ARQ square, in which R is not equal to P, neither equal to Q, because the R equal to Q term has been already taken here. Okay. So what we are doing is that take this ARP square. So there you will get squares of these, except for this corner point, take these. Okay. And similarly take these and these. Now, but then when you take these, the same will be this, because of symmetry. That means this has been covered actually. Okay. So when you consider the rows, when you consider the columns, the twice of that will give you the sum total of columns as well as rows. So for P you have taken this and make it twice, so you get this also. That means this has been actually covered. Okay. Similarly, when you then consider Q, then you need to omit this. This omission is represented here. Okay. Now what this means? This means that sum up all those entries from here to here and below, and here to here and below, except these two corner points, and these identify it separately. So this is the complete sum of the off diagonal terms before the transformation and after the transformation. We have kept only the Pth and Qs term entries here, because others anyway do not undergo any change. Now when you try to calculate the same sum for the matrix A prime, then you get this. And now note that through this Jacobi rotation P PQ, you have actually set this as 0. Okay. So you can write simply this, right? This has been thrown out because this has been set 0 by this particular rotation. Now you compare these two and find out delta S. If you do that, then you will notice that this sum and this sum is actually same. This sum and this sum is actually same. That is very easy to notice, because it is this square plus this square, and these two actually do not change, because as you square these two terms and add, then you will find that with C square you will find ARP square plus ARQ square. With S square also you will find ARP square plus ARQ square, and C square plus S square is 1. So the square of this plus square of this plus square of this plus square of this is the same as ARP square plus ARQ square, and the 2AB term in the square here and 2AB term in the square here will cancel each other. So that means that ARP prime square plus ARQ prime square will turn out to be the same as ARP square plus ARQ square. So, that tells you that this sum and this sum remains same for every r, and this earlier was something which has been now set to be 0, and this much has been reduced. So, that means that even if old zeros are overwritten in the new Jacobi rotation transformations, yet at every Jacobi rotation transformation there is a net decrease in the sum of squares of off diagonal terms. That means over every Jacobi rotation the off diagonal terms go on becoming poorer and poorer in their magnitudes. And finally, after a large number of such rotations take place, this sum will converge to 0, but that may not happen in one sweep. So, therefore, there are several strategies to use Jacobi rotation method to diagonalize a symmetric matrix. One is that after one complete sweep you start all over again from this and complete another sweep, and then another sweep, and then another sweep. One strategy is to go on applying these sweeps in iteration. You see, it is not a fixed operations process, it is an iterative process. So, sweep after sweep you will be reducing the off diagonal entry magnitudes overall. This is one strategy. In another strategy, what people do is that after a few initial sweeps, then later at the time of writing the new entries, you can keep track of what is the largest magnitude entry, off diagonal entry in the matrix, and then if it turns out that the 4-7 entry turns out to be the largest magnitude after the completion of a sweep, then after that you can say that now onwards we will try to make this 0, and you apply P47 selectively. Next, if P59 turns out to be the largest magnitude entry, then you say we will apply P59, and so on. So, after a few initial sweeps, after reducing the off diagonal entries to some extent, then you can check for the largest magnitude entry, and that way you try to annihilate the largest positive entry first, and that way you can expedite the process, expedite the iterations and make the process faster. This is one way of applying plane rotations to diagonalize a matrix. There could be another choice, that is, rather than asking for the corner values to become 0 through the transformation, you could have chosen any other value, that is not necessarily this. You could have chosen some other entry to become 0. For example, while applying the rotation PQ, rather than asking for a PQ prime to be 0, you could have chosen a RQ prime to be equal to 0. That is, rather than this, you could have chosen this, whichever. Okay. Accordingly, it would mean one of these. Okay. So, you could have chosen that, and that if you say ARQ prime equal to 0 for any R you can choose in principle. Yes. So, ARQ or AQR is the same thing. Okay. So, one of these you want to be set equal to 0. That will mean that you want sine by cos is minus ARQ by ARP, that is tan phi. So, that will give you another value of phi, which will set your chosen element in this row and in this column to become 0 through the transformation. A particular choice gives you Given's rotation method, in which R is taken as P minus 1. That means you do not try to make this corner element 0, but you just want to make this element 0, just left of this corner and just above this corner. Okay. So, this choice of element for the annihilation process gives you the method known as the Given's rotation method, which means that a P minus 1 Q is annihilated, and the advantage of this particular annihilation is that in the subsequent rotation transformations this is never updated again, because if you then start the sweep, then you will not be starting the sweep from here, but you will be starting the sweep from here. So, you will apply the transformations in this order. First you apply a P23, that means you will be first operating on this corner, 4 corner blocks, and then you will not be trying to make this 0, but you will be trying to make this 0, okay, this and this. So, after that is accomplished, then you will ask for P24, that means with these 4 as the corner points, okay, in order to make this 0, and in that you will find that if you are applying P24, then only the second row and the 4th row will be updated, 3rd row will not be updated, and the 0 that we have set in the previous case is sitting actually in the 3rd row. That way the successive Givens rotation transformations will not at all update those locations which were set to be 0 in the previous Givens rotation, and this has an advantage. So, with these Givens rotations
P23, P24, etc.
we would have made all these zeros which will never be updated again. As you then go to the next Givens rotation, which is P34 to P3n, okay, then you completely move from here and operate here, okay. So, in that, in P34 to P3n you will be setting these as 0 and so on, and the symmetric nature will ensure that above the super diagonal similar zeros are getting established. So, at the end of a Givens rotation sweep, which is P23 to P2n, P34 to P3n, and finally Pn minus 1n at this end, okay, you will get all these zeros, because the old zeros will not be updated in the new Givens rotations, and the result of this whole thing is a symmetric tridiagonal matrix. And this sweep, this Givens rotation sweep, has to be applied only once, and after transforming the matrix into this form, no further Givens rotation will contribute anything. That is why the Givens rotation sweep is applied only once, not in iterations. Now, in this whole process, whether you apply Jacobi rotation or Givens rotation, how do the eigenvectors transform? As you know that in the new final matrix you have got all the transformations P1, P2, P3, etc., all those rotation transformations, those matrices, similarity transformation matrices sitting like this. Here the corresponding transposes, which are same as inverses. So, then in the entire product, if you consider P1 to Pn, all of them together as a big matrix P, then you will say that that matrix P gives you the basis through which the transformation has finally taken place. Okay, here the transpose of that entire thing is actually sitting right. Now, computationally, when you want to apply these transformations and you want to find out at the end of the process not only the eigenvalues but eigenvectors also, in those situations it is important to keep track of this. You do not want to save all these matrices. So, what you do in the beginning, you say that before we have applied any transformation, we will consider P as identity, and as a transformation has been applied, we will keep on multiplying the new transformation on this side. That will mean that in place of P, we will store the product. Whatever transformation has been taken place, whatever rotation has been applied, that rotation matrix will be multiplied to this. Okay. So, first time this initialization with identity is actually dummy, but next time the moment P1 has been multiplied on this side to it, in this we have P1. Next, when P2 is multiplied like this, we will have P1 P2 the product. Next P3, then we will have P1 P2 P3 and so on. So, the iteration will actually go like this. So, that means for k equal to 1, 2, 3, 4, as many rotation transformations are applied, all of those get multiplied from the right side, and finally you will have the P storing all the eigenvectors by the time the matrix has been diagonalized. If the matrix has been processed only up to symmetric tridiagonal form in the Gibbons rotation method, then that P matrix, resulting P matrix, will relate the eigenvectors of the original matrix and the matrix A prime which we have in our hand now, which can be processed further through some other method. Now a few questions arise, because based on plane rotations we have considered two methods. One is Gibbons rotation method and the other is Jacobi rotations method. These are the points of contrast which it would be interesting to summarize once. First question is, what happens to intermediate zeros? In the case of Jacobi rotations, they get spoiled. In the case of Gibbons rotation, they are preserved. Second question is, what do we get after a complete sweep? In the case of Jacobi rotation, we get another matrix which is also perhaps full matrix, but with the off diagonal terms a bit reduced in magnitude compared to the old matrix. In the case of Gibbons rotation, after a complete sweep we get a completely symmetric tridiagonal matrix, as long as the original matrix is symmetric. Third question is, how many sweeps are we supposed to apply? In the case of Jacobi rotations, we have to apply sweeps through iterations, several sweeps, till the off diagonal terms get reduced to sufficiently small magnitude. In the case of Gibbons rotation method, we have to apply only one sweep, resulting in one symmetric tridiagonal form, after which there will be no further advantage. What is the intended final form of the matrix? In the case of Jacobi rotation, after sweeps, after the necessary number of sweeps, whatever is required for convergence, the intended final form is actually diagonal. How many sweeps will be required for that? We do not know. In the case of Gibbons rotation method, actually halfway processing is intended, only halfway processing is intended. Further than that, Gibbons rotation method does not declare to go at all. Final question, which is of practical relevance, is how is the size of the matrix relevant in the choice of the method? Typically, for small matrices, say 5 to 7, a Jacobi rotation method is good enough, but for much larger matrices, 9 by 9 or 12 by 12, Jacobi rotation method may be computationally very expensive. So there the strategy should be to apply Gibbons rotation method and then reprocess the tridiagonal matrix through some other method. You will later find that Householder method, which we will consider in the next lecture, also accomplishes tridiagonalization a little more efficiently than Gibbons rotation method. However, for a half processed matrix, sometimes Gibbons rotation method turns out to be more efficient. We will come across one or two such situations in the exercises.
Swayam Prabha. Digital India. Educated India.
I welcome you all to the lecture number 16 in the course Thermodynamics and Thermal Engineering. Let us recollect what we have discussed in the previous lecture number 15. We have seen the methods to improve the efficiency of the ideal Rankine cycle. So we solved one numerical question, made a comparative analysis Initially, we solved the problem without reducing the condenser pressure or increasing the boiler pressure. So that was the base case, and three methods were employed. First one is reducing the condenser pressure. It improves the efficiency of the Rankine cycle, ideal Rankine cycle. We have seen there is a change in the dryness fraction of the steam also. That is state point number 2. In the second method, we have seen the superheating the steam from in the example which we have discussed, from instead of superheating the steam to 350 degrees centigrade, it was heated to 600 degrees centigrade without changing the other parameters. We found that there is a improvement in the ideal efficiency of the ideal Rankine cycle. And in the third case, we increase the boiler pressure. From 30 bar to 150 bar. 30 bar 3 to 15 megapascal, and in that method also there is a increase in the efficiency of the Rankine cycle. So in the second method, there was a reduction in the dryness fraction of the steam at the exit of the turbine. Otherwise, there was significant increase in the net work done. Net work done in the Rankine cycle is the difference between the work done by the turbine minus the work done on the pump, that is work done on the system. So that gives the net work done. When we divide the net work done by the heat supplied to the boiler, QS, we get the efficiency. There is another method by which we can find out the efficiency, heat supplied minus heat rejected, which is nothing but the net work done to the heat supplied in the boiler. So this is what we have discussed in the previous one. So now we are going to see the nozzle. What is the function of the nozzle, critical pressure ratio, and a few numerical questions. Let me go through the contents. Introduction, the types of nozzles, how to define the efficiency of the nozzle, critical pressure ratio, and few solved numericals. So to begin with, before seeing the function of the nozzle, all of us are familiar with the major components of a steam power plant or a thermal power plant: boiler, turbine, condenser, and pump. Normally the nozzle is not shown in the schematic. However, it is a very important device for enhancing the velocity of the fluid, the velocity of the steam. The steam which comes from the boiler is normally a high pressure, high temperature steam, mostly superheated condition. So before it is expanded in the nozzle, it is passed through a device that is called nozzle. Because the velocity of the steam at the exit of the boiler is not high, it is small. So in order to enhance the velocity of the steam, this nozzle is incorporated between the boiler and the turbine. Let us see in this session how the velocity of the working fluid, the stream which is passing through the nozzle, is increased at the exit of the nozzle. So nozzle is a device used to increase the velocity of the fluid. Basically, it is like a duct whose cross-sectional area varies. Cross-sectional area, the area of the nozzle does not remain constant. It is a varying one. Pressure drop takes place. How does this increase in kinetic energy takes place? The steam which is entering the nozzle, at the inlet of the nozzle, it is high pressure and high temperature, no doubt. But the velocity is small compared to the pressure and temperature. So as it passes through the nozzle, as it passes through the duct, pressure drop takes place in the duct, and the drop in pressure is converted into the enhance in the kinetic energy of the steam. Also, there are no moving parts in the nozzle. The nozzle does not contain any moving parts due to the varying cross-sectional area, due to the variation in the area. So the velocity of the fluid is increased at the expense of pressure. Some of the types of the nozzles are convergent nozzle, divergent nozzle, and a combination of these two. So this is the convergent nozzle. So here the steam is entering at the velocity, this is the inlet. Let us take the velocity at inlet velocity is V1. Inlet velocity of the steam at inlet is V1. Outlet velocity, let us take V2. Okay. Inlet pressure will be P1 and outlet pressure will be P2. Let us take. So we take the inlet as state point 1 and outlet as state point 2. So this is a convergent type of nozzle. You can see as we move from the left to right, so there is a varying in the area. Normally the steam nozzles are insulated. The insulated portion is not shown here. This is because we don't want the temperature to drop much, but however in actual case, even though the nozzles are insulated, there will be some heat loss, because we know the insulation cannot eliminate the heat loss completely, but it can minimize the heat loss. So normally we assume theoretically the temperature at the nozzle surface remains the same. So now this the steam is entering at an inlet velocity V1 and it is leaving at V2. So if you compare these two velocities, V2 will be greater than V1. If you compare V2, even V1 may be it is very, very small and it can be neglected. We will see in the steady flow energy equation, when we apply the steady flow energy equation for this nozzle, how the equation standard form of S of E is reduced. So V2 is greater than V1. Pressure at 2 will be less than pressure. So this is very, very important. So according to the Bernoulli, this one. So this, if the velocity of the steam is this one, so there is a decrease in the another property of the fluid. So in this case, it is the pressure. So the pressure at the inlet is very, very high compared to the pressure of the steam at the outlet of the nozzle. So here there is, as I said before, there are no parts, moving parts and all. There is one valve which is provided on the rear side to vary the back pressure, And this is the second schematic represents the divergent nozzle, just it is opposite to the convergent type. So in the converging type, as this fluid enters, the area is converging, the area of the duct or the nozzle is converging. So here it is diverging, so it is called a diverging nozzle. So the inlet velocity and the outlet velocity, there is a significant variation in case of a nozzle. This is the convergent divergent nozzle. Inlet, this one, this is the inlet, again this is the outlet. The area, the portion of the nozzle at which the area is constant, does not vary, that is this portion is called throat. This portion is called throat, nozzle throat. So let me mark with the red color this one. So this is the throat. So here you can see this is the converging part. So there is a reduction in the area. So here the area is minimum or least at this point where I have marked with the red color pen, and again it is the diverging part. The nozzle, this portion, the green color portion of the nozzle is the diverging part, and the blue color portion is the converging part. Okay, so this is called a CD nozzle or a convergent divergent nozzle. Let me define the efficiency of the nozzle. So if you see the enthalpy we can write H is equal to U plus PV. So there will be a drop in enthalpy of the working fluid from H1 to H2 as the fluid leaves the nozzle. So there will be reduction in enthalpy at the exit of the nozzle. So the enthalpy drop, the drop in enthalpy is equal to the gain in kinetic energy, because the velocity of the nozzle, velocity of the fluid in the nozzle is increasing. So we know kinetic energy is half mv square. If we assume 1 kg of the working fluid, so it is v square by 2. So the kinetic energy at the inlet is v1 square by 2, and the kinetic energy at the outlet is v2 square by 2. Of course, v2 is much higher than v1. So the drop in enthalpy of the steam is the gain in kinetic energy. So efficiency of the nozzle is the ratio of actual enthalpy drop. So here I have plotted the process on a enthalpy entropy diagram. So x-axis is entropy and y-axis is enthalpy, HS diagram. So these are constant pressure lines. So this is the inlet pressure, this is the inlet pressure, and this is the outlet pressure. Okay, P2 is less than P1. Okay, so here I have not shown the variation in the velocity because the inclined lines are the constant pressure line, y-axis is the enthalpy and x-axis is the entropy. Okay, so here this is the actual process. This is the actual process, and this is the ideal one. This is the ideal one. Ideal process. So in case of ideal process, we know it is perfect isentropic expansion. Isentropic expansion of steam. Isentropic expansion of steam. Okay. So in fact, the steam is expanded inside the nozzle. So there is a drop in enthalpy from H1. This is H1. Okay. So this is enthalpy of steam at the inlet, and this is enthalpy of steam at the outlet. So you can see there is a drop in enthalpy from H1 to H2. So H1 minus H2 is the actual enthalpy drop. Here I have taken the mass of the fluid as 1 kg. Otherwise, m into delta H. M into delta H. Anyway, the m term will get cancelled because the ratio is actual enthalpy drop by, this is actual enthalpy drop is H1 minus H2 dash. This is H1 minus H2 is, this is ideal enthalpy drop. So let me write, this is delta H. Okay, this is delta H for ideal or isentropic. Okay. Now if you compare the values of H2 and H2 dash, so this is somewhere else we will get, this is the enthalpy difference or drop in enthalpy for the isentropic process. But if you take the actual one, so the actual one, the outlet enthalpy is somewhere else here, which is H2 dash. So here you can see the difference between H1 and H2 is much more than the difference between the drop in enthalpy in the actual process. That is due to the losses due to heat loss, friction, irreversibilities during the expansion process. So H1 minus H2 dash is the actual enthalpy drop, which is in the numerator, divided by the isentropic. If point number 2 dash and 2 are same, that means the nozzle efficiency is 100%. So if H2 dash is equal to H2, that means numerator also will be H1 minus H2, denominator is H1 minus H2. So the efficiency, the ratio becomes 1, the efficiency of the nozzle is 100%. Okay. So when the nozzle is designed, carefully suppose if the design is a perfect efficient one, if it is a perfect one where the losses are minimized, losses are minimum, so this difference will come down, so the ratio will increase and the efficiency will be obviously. Now let us apply the steady flow energy equation to this device. So it is also a steady flow device. Already we have seen this equation in the previous lecture for a turbine, for a compressor, for a throttling device it is H1 is equal to H2 because there is just in the isenthalpic process in case of a throttling process. Now let us apply the SFEE to the nozzle. So we know the basic equation is H1 plus V1 square by 2 plus G into Z1 plus Q is equal to H2 plus V2 square by 2, instead of G into Z1, G into Z2, that is the potential energy plus the work done. So that is the basic equation. Let me write the basic equation. General steady flow energy equation is SFE. Here I have written directly. Let me explain how we are getting these terms, why some of the terms are not there. So it is H1 plus V1 square by 2 plus small q plus G into Z1 is equal to H2. This is for the inlet. This is at the inlet of the device. H2 plus V2 square by 2 plus W. Let me write the first potential energy and this one. Of course, we can write it in any order. Since I have written the kinetic energy term as the second term, let me write the potential energy term as the third one, G Z1, and here I will write Q plus G into Z2 plus small w. We know that Q is equal to, small q equal to capital Q by unit mass by M. So this is the right hand side of the steady flow energy equation. So as I explained before, these steam nozzles are insulated. So we assume there is no heat loss in ideal case. However, there may be little heat loss in the actual case. So there is Q term is 0. There is no work done by this one. So W is equal to 0. Assuming Z1 is equal to Z2, there is no changes in the potential. Changes in potential energy is equal to G into potential energy at inlet is 1, outlet is 2. So Z2 minus Z1, that is equal to 0. Change in kinetic energy. Kinetic energy is half mv square by 2. We have taken the one unit mass flow, unit mass. So per unit mass you are calculating. So v square by 2. At the inlet it is v1 square by 2. Outlet is v2 square by 2. So 1 by 2 into v2 square minus v1 square. Okay. This cannot be 0. Okay. Because the function of the nozzle is to increase the velocity. So v2 is much higher than v1. So this cannot be greater than 0. Of course, v2 is much higher than v1. So when this is 0, so this term also will get cancelled. This term also will get cancelled. So I am having h1 plus v1 square by 2. There are only two terms, h1 plus v1 square by 2 and equal to h2 plus v2 square by 2. So this is how the steady flow energy equation has reduced to this form in case of a nozzle. Now bring this, keep the enthalpy terms on one side and the velocity terms on the other side. So h2 will come that side, h1 minus h2 equal to v2 square minus v1 square by 2. This is for an isentropic case. For an actual case, if you refer the previous diagram, actual enthalpy drop is h1 minus h2 dash. h1 minus h2 dash. So instead of h2 I am putting h2 dash. Instead of v2 velocity I am putting v2 dash square minus v1 square. Okay. So if v1 is negligible, it doesn't mean that it is 0. It is compared to the exit velocity of the steam, the inlet velocity is very small. So if v1 is negligible, then the efficiency of the nozzle becomes v2 square by v2 dash square by v2 square. v2 dash square by v2 square. However, if we don't neglect this v1 and take the value as it is, even though it is small, then it is h1 minus h2 dash divided by h1 minus h2, or in other words, because h1 minus h2 is v2 square minus v1 square by 2, v2 square minus v1 square by 2, and the h1 minus h2 is h1 minus h2 dash is v2 dash square minus v1 square by 2. So that is the numerator divided by h1 minus h2 is that we have, I am substituting this one. I am substituting this one, V2 square minus V1 square by 2. 2 and 2 will get cancelled. So, the numerator, the efficiency of the nozzle is written as V2 dash square minus V1 square divided by V2 square minus V1 square. That is the change in the kinetic energy of the actual process divided by the change in the kinetic energy of the isentropic process. So, if we know the velocity V1, V2, we can find the efficiency. If you know the three terms, inlet velocity, exit velocity for the ideal cases, and the actual case. Similarly, if you know the inlet enthalpy, outlet enthalpy for the actual process and isentropic process, we can find out the efficiency of the nozzle. So, very important term, critical pressure ratio. So, here again I have shown this one. There is a graph plotted here. So, let me explain this graph, then we will define the critical pressure ratio. So, here I have taken the P2 by P1. Okay. P1 is sometimes called as, the inlet pressure is sometimes referred as stagnation pressure, and P2 is the back pressure. B2 is the back pressure. That is the fluid pressure at the exit, before it leaves the fluid is going to the turbine for further expansion. So, here I have taken the P2 by P1, that is the pressure at the exit divided by the pressure at the inlet. Okay. So, you can see up to a particular value, or we take this one. Here, if you take this one at this point, if you move from right to left, as I reduce this ratio, or if you move from left to right as I increase the ratio. Okay. Let me explain this curve from right to left. So, as the pressure ratio is decreased, the mass flow rate through is also this one. So, after a particular point, it is decreasing, or in other words, as the pressure ratio is increased, the mass flow rate of the working fluid, the stream through the nozzle is increasing up to a point, up to this point only, beyond which it remains constant. That means further increase in this ratio of back pressure to the inlet pressure does not increase the mass flow rate through the nozzle. So, the value of the pressure ratio at which the mass flow rate is maximum, mass flow rate through the nozzle is maximum, is called critical pressure ratio. The critical pressure ratio is represented by the symbol asterisk or a star. Okay. Pressure ratio is P2 by P1, asterisk or a star, that refers to the critical pressure ratio. So, here the mass flow rate is maximum and the corresponding x-axis is the critical pressure ratio. So, it is the pressure ratio at which the mass flow rate through the nozzle is maximum. Mass flow rate through the nozzle is maximum. So, there is a derivation which is not the focus of our this one. So, I have just given the final equation. The critical pressure ratio also we can find out for a saturated condition, if the condition is saturated or superheated. So, in terms of gamma, 2 divided by gamma plus 1 whole power gamma by gamma minus 1, So, if you substitute the value of gamma for a saturated one or a superheated condition, it is 1.3 and 1.135, 1.3 and 1.135. So, we get the maximum pressure, critical pressure ratio. So, there is a valve which is provided on the rear side of the nozzle. As we adjust that one, the P2 value or PB, sometimes back pressure is referred as PB, P2 or PB. In some textbook they will use PB, in some references they will use P2. So, we can follow any one notation uniformly. So, as the back pressure is reduced, so what happens as the back pressure is reduced? As the stream moving from inlet to exit, so there is a pressure drop significant pressure drop between the inlet of the nozzle and the exit portion. So that has been converted into increase in the kinetic energy or increase in the velocity. There are two terms in this perspective. One is over expansion, another one is under expansion. What is this over expansion and under expansion is? When the steam leaves the nozzle, so it suppose if the pressure at the exit is more than the outside pressure, ambient pressure or free stream pressure at the free stream condition, that is atmospheric condition, what happens is that is called an under expansion. If the pressure of the steam leaving the nozzle at the exit, it is less than the outside pressure or the ambient condition, it is called over expansion. So when these things normally these either the under expansion of the nozzle or the over expansion should not be there. However, if there is a drop in pressure, especially at higher altitudes, what happens when the outside pressure is less? So there are chances that the fluid leaving the nozzle at a higher altitude, the pressure at the exit will be more than the outside pressure. So with this background, let us solve some numerical questions. Here, apart from using the steam tables, I will be explaining the same problem to how to solve using Mollier chart. Okay. Steam at 100 bar and 500 degrees centigrade is expanded isentropically in a nozzle to a pressure of 0.15 bar. That means P1 is 100 bar, P2 is 0.5 bar. It is an isentropic process, so process 1 to 2 we can plot. P1 is 100 bar, that is the before the steam is expanded in the nozzle. Temperature of the steam is 500, and after expansion the pressure is, so you can see the significant drop in the pressure from 100 bar to 0.5 bar. It is much more than 100 times. It is more than 100 times. So P1 is equal to 100 bar, temperature of the steam is 500 degrees centigrade, and P2 is equal to 0.5 bar. This is the condition at inlet, and this is the condition at outlet. So since the pressure and temperature of the steam are given, like the previous numerical questions, first step is to check whether the steam is in superheated condition or not. So from table, since use this pressure, so at 100 bar, find out the saturation temperature from table number 2. Because I have told several times, if the pressure is given, we have to refer table number 2. If the temperature is given, we have to refer table number 1. If both pressure and temperature are given, first for checking whether the steam is in superheated condition or not, we have to use table number 2. So this is table number 2, table 2. This is pressure in the first column. So corresponding to 100 bar, this is the saturation temperature. So the temperature is 311 degrees centigrade. Okay. Tsat is equal to 311 degree centigrade. Now compare this temperature with the temperature of the steam. T1 is greater than Tsat. Therefore, steam is in superheated condition. Steam is in superheated condition. So that's what I have written here. From steam table it is this one. Now once we know the condition of the steam is in superheated condition, we know the pressure, that is 100 bar in this case, the temperature of the steam is 500. Using these two property we can find out enthalpy, specific enthalpy and specific entropy from the table. So directly I am going to specific enthalpy table for the superheated steam, which is table number 4. Table number 3 is specific volume. So this is table number 4, specific enthalpy of superheated steam. So corresponding to 100 bar, temperature of the steam is 500. So this is temperature given. So the enthalpy of the steam is 3374.6. So that's what I have written here, 3374.6 kilojoule per kg. So at 100 bar, 500 degrees centigrade, from table 4, okay, from table 4, we can find out the enthalpy as, let me write the value, 3374.6. 3374.6 kilojoule per kg, kilojoule per kg. 3374.6 kilojoule. I have given the table number also. Okay. Next, let us read the entropy value. Entropy, specific entropy of superheated steam. Do not refer the table number 1 or 2 when you take the enthalpy or entropy or specific volume for a steam which is in superheated condition. We have to refer table 3 for specific volume of superheated steam, table 4 for specific enthalpy and table 5 for specific entropy. So now the entropy, this is in table 5. Table 5. And all these values I have taken from steam tables by R.S. Kurmi. The steam tables by the author R.S. Kurmi, that is S. Chand publication. So now this is the pressure corresponding to 100 bar pressure. This is the temperature, given temperature. So the specific entropy of the steam is 6.6 or 6.599. So similarly, entropy is equal to 6.599 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. So that's what I have found here in this slide. So first I have checked the condition of the steam is superheated or not. Once I know that the steam is in superheated condition, take the enthalpy and entropy values. Now we know the process, this process 1 to 2 is isentropic expansion. 1 to 2 is isentropic expansion. So now we have to apply the basics. 1 to 2 is isentropic expansion process. Okay. So this is the, let me recollect this one. This is S, this is H, this is 1 to 2 and this is the actual process. This is the 2 dash and this is the pressure line P1 and this is the pressure line. Let me draw it neatly. Let me draw the pressure lines. This is high pressure P1, this is P2, this is isentropic expansion 1 to 2. Entropy at 1 is equal to entropy at 2. This is the enthalpy of steam at H1. This is the enthalpy of the steam H2. This is the isentropic process or the ideal, this one. Suppose if I want to represent the actual process, this is the actual process. This will be 2 dash. This will be 2 dash. Of course, here it is clearly given in the numerical question that the steam is expanded isentropically. So that means it is a reversible adiabatic process where entropy at 1 is equal to entropy at 2. The line is perpendicular to the x-axis, which is the entropy. Okay, now I am going to find the enthalpy at state point 1 and entropy at state point 1. So next I have to find out the enthalpy at state point 2. To find out the enthalpy at state point 2, okay, so mostly it will be in the two-phase region where we have to find out the dryness fraction at state point 2, that is x2. For that I have considered the process H1 is equal S1 is equal to S2. So entropy at 1 is equal to entropy at 2. Entropy at 2 can be written as SF2 plus X2 into SFG2. What is SFG2? Difference between SG2 minus SF2. Now, how to get this SFG2? SF2 and SFG2 have to be found from the pressure which is at the exit of the nozzle. What is the pressure at the exit of the nozzle? It is 0.5 bar. So at P2 is equal to 0.5 bar. Again pressure is given. So refer table 2 and read out SG value, SFG value. So SG2 is equal to see here, this is table 2, okay, and this is the pressure given 0.5 bar, and I am reading the SF and SFG2. Of course, in steam table we can give, they have given SG also. The difference between SG and SF or HG and HF will give you the HFG value or SFG value. So 1.091 and 6.504. So this is SF2. These values are from the table corresponding to the pressure of 0.5 bar. So SF2 is equal to, let me take this value, 1.091 kilojoule per kg Kelvin, and SFG2 is equal to 6.504 kilojoule per kg Kelvin. So substitute these values. We know S1. S1 is, we have read from the superheated table. This is S1. So substitute the values. You will get S1 is 6.599 is equal to SF2 is 1.091 plus dryness fraction into 6.504. So you will get the dryness fraction of the steam as 0.846. That means it contains about 15% water and 85% vapor. 0.846. Now for the same pressure 0.5 bar, we have to read out HF2 value and HFG2, because I will be using a similar equation for enthalpy. So how to find the enthalpy? At state point 2, H2 is equal to HF2 plus X2 into HFG2. So this formula and this formula are similar. This formula and this formula are similar. Only the first one is entropy, the second one is enthalpy. So HF2 and HFG2, so that we can find. So let me, this is SF2 value, this is SFG2, so which I have just taken and substituted. Now HF and HFG2 value have to be taken. So this is HF, this is HFG2. 340.6, 2305.4. 340.6 kilojoule per kg, and what is the other value? Let me, 2305.4. 2305.4 kilojoule per kg. All these values have to be taken at 0.5 bar from the table number 2. Now if you substitute, you will get H2 is equal to, because all the values are known, HF2 we have taken from the table, HFG2 we have taken from the table, X2 we have just calculated dryness fraction. So you will get the enthalpy at 2291 kilojoule per kg. So if you see H1 value which we have found 3374 kilojoule per kg, and the calculated enthalpy at state point 2 is 2291 kilojoule per kg. So this is the drop in enthalpy. This is the drop in enthalpy of the steam as it is expanded from the inlet to the exit of the nozzle, and obviously this has been converted into the increase in the kinetic energy. So these whatever the values which we have to take from the table, I have explained in a detailed manner. Now quickly let us complete this one. We have to find out the mass flow rate of the steam through the nozzle. So see, actually this is mass flow rate is m dot. There is some compatibility, so the dot is not visible, so I am just writing with pen. So now we have found the enthalpy. Okay. So now critical pressure, I have given the formula P2 by P1 star is equal to 2 by gamma minus 1. So find out the critical pressure. Okay. P2 by P1 the whole power star is equal to 2 by gamma by gamma plus 1. Okay. For a superheated condition, gamma value is 1.3. Okay. For a saturated, this one it will be 1.135. For the steam entering the nozzle, so gamma is equal to 1.3. So it's just mere calculation. 2 by 1.3. So in this P2 by P1 star. Okay. So I am finding the critical pressure. So if you see the diagram, this is the critical pressure. This is what I am finding. So for this I am using this formula P2 by P1 star is equal to 2 by gamma plus 1 whole power gamma by gamma minus 1, where gamma equal to 1.3 because the condition of the steam at the inlet is superheated. So if you substitute, you will get the critical pressure as, it will be more than 0.5 bar but less than 100 bar. Steam pressure at the inlet is 100, it is expanded up to 0.5 bar. So the critical pressure ratio lies somewhere else between this region. So it will be less than 100 and more than 0.5. So the critical pressure, it comes around 55 bar. Now I can find out the exit velocity. V2 is equal to square root of 2 into H1 minus H2. So this is how I got this equation. This is from the steady flow energy equation. If you see this equation, okay. So if you neglect the initial inlet velocity, so this V1 term will become 0. Okay. So H1 minus H2 equal to V1. So let me write it here. Okay, let me write it here. I am writing it here. H1 minus H2 is equal to V2 square minus V1 square divided by 2. So if V1 is negligible, therefore V2 square is equal to, you bring this term to the left hand side, 2 into H1 minus H2. Therefore V2 is equal to square root of H1 minus H2 multiplied by 2. So that's what I have written here. 2 into H1 minus H2 the whole power 5. So this is nothing but square root of 2 into H1 minus H2. Substitute the values. The exit velocity is close to 1500 meter per second. So the mass flow rate of the stream, I will be using the continuity equation m dot equal to rho AV, where rho is the density. Okay, V is the rho is the density, A is the area, that is pi by 4 d square, the cross sectional area of the device, pi by 4 d square, and V is the velocity. using the equation of continuity, m dot equal to rho AV. So, this is m dot density at exit into area into velocity. What is this density? Density is rho 2 is equal to 1 by specific volume. Let me repeat, capital V is the velocity, small v is the specific volume. Okay, let me write it here so that it will be easy. So, this is rho 2 equal to 1 by V2. Capital V2 is velocity at exit or outlet, and small v2 is specific volume at exit. So, because there are two V terms used, capital V and small v. Capital V is velocity. So, rho AV velocity we have calculated 1472.1, and this is equal to reciprocal of density is specific volume. So, rho 2 I am writing as 1 by small v2. So, A into V2 by small v2. So, if you calculate the mass flow rate comes to, for 1 second, around 7 kg of steam have to be circulated in order to attain the enthalpy drop is from 3374 to 2300, close to 300. So, 7.1 kg per second of steam is circulated for the data given in this problem. So, that is what we have to find out. Find the mass flow rate of the steam. So, let me quickly explain the Mollier diagram. The same enthalpy values directly we can find out from the Mollier diagram or Mollier chart. This is the Mollier diagram or Mollier chart. Okay, so this is Mollier diagram. So, this is also provided along with the steam table. Mostly it will be on the just before the back side cover page. This Mollier diagram will be there. It is in the form of like a A3 chart, X axis is entropy is x axis, y axis is enthalpy, y axis is enthalpy, and these values are pressure. See, there are 4 different types of lines in this chart: pressure lines, constant pressure lines, specific volume, dryness fraction and temperature. There are 4 lines are there. One is temperature, pressure, specific volume is small v, and dryness fraction x. These 4 lines you can find in the Mollier diagram. Apart from the x axis, which is entropy, and the y axis is the enthalpy. It is a HS diagram, HS enthalpy entropy diagram. For example, see here you can see this is the pressure. These are all pressure lines. These are all pressure lines. Okay, these are all pressure lines. These are all the pressure lines. And this is the temperature line is shown here. Temperature line is this lines. You find this is the pressure line, these are the pressure lines, and these are all the temperature lines. Temperature equal to 700, temperature equal to 650, and so on. Temperature equal to, and this is the temperature line, this is temperature, this is 250, 300. Maybe the letters are not visible, I am just reading. So, these are all the temperature lines. Then we have the dryness fraction. These are all the dryness fraction. Dryness fraction. The other name for dryness fraction is steam quality of steam. And the specific volume lines are also shown here. Okay, so maybe it is not, this is the saturation line, and again the pressure values are given here also. These are also the pressure values, and there is a specific volume line. These lines are called specific volume lines, which are not very clear. Of course, anyway, for this one let us see how to take the enthalpy value and entropy value. So, this is an alternate method to solve the problem. Instead of using the steam table, of course, the value which we take from the steam table will be accurate, because we know in terms of decimal also, like 340.6 HF value, whereas here you can take approximately, not so accurately. So, if you see this one, the given temperature, I think due to time constraint, I will continue this one in the next lecture. Let me come to the concluding remarks. But there is one more numerical question which I will discuss in between the next lecture, which is the propulsion system, because it's a very important thing. Due to time constraint, it is not possible to explain the procedure by steam table and Moliere chart. So, this portion I would be taking in the next lecture. So, to conclude, if you see the topics which we have discussed, we have seen a new device, especially though we have heard this device in the previous sessions also, nozzle. We have seen the function of the nozzle, how does the velocity enhancement or the enhancement in the kinetic energy takes place between the inlet and the outlet. It is primarily due to the pressure difference delta P between the inlet and the outlet. So, there is a term which is called the critical pressure ratio, that is the pressure ratio. As we change the pressure ratio, the mass flow rate increases. At a particular point, the further increase in the pressure ratio, does not increase the mass flow rate. The mass flow rate of the fluid passing through the nozzle remains constant, and that is called the pressure ratio at which the flow rate reaches the maximum value, that is called the maximum mass flow rate or the critical pressure ratio. So, the back pressure is also called as the exit pressure, the inlet pressure is also called as the stagnation pressure. Like how we solve the problems in the properties of steam, whenever the pressure and temperature of the steam is given, the first step is to find out the saturation temperature, check whether the steam is in superheated condition or not at the inlet. Most of the cases at the exit, it will be in two-phase region, where we may have to find out the dryness fraction of the steam at the exit, and I define the nozzle efficiency as the ratio of actual enthalpy drop, that is H1 minus H2 dash, divided by isentropic enthalpy drop, H1 minus H2. So, in case of a nozzle, the surfaces of the nozzle are insulated. So, for ideal condition, we assume there is no heat transfer, Q equal to 0, there are no moving parts, work is not done. So, W equal to 0. If you apply the steady flow energy equation, we will get H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, from which we can find out the exit velocity. Exit velocity is square root of 2 into H1 minus H2. If we take V1 is close to 0, because the inlet velocity is very, very small compared to the exit velocity of the steam in a nozzle. So, with this I conclude the lecture number 16. Thank you from my side.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. I'm here to tell you a little bit about how we can think about globalization in a sociological manner. Now, one of the important concepts in the field of globalization and particularly global studies is that of global flows. It's a term that was developed by the sociologist and anthropologist Arjun Appadurai. He said that as the world is becoming a more and more global place, you increasingly see the movement of different types of things, both tangible and non-tangible, across multiple national borders. To begin with, you can look at how your day proceeds. I often need a cup of tea to actually start my day. Now, if you think about it, tea that we drink is not something that is that originated in India. It's actually a drink that comes to us from quite far away in China. And this is something that has happened not immediately, but it has happened 400 or 500 years ago. So this kind of movement actually happened with the movement of people. Now, this kind of movement of people and goods is one category of flows that Appadurai talks about. A second category of flows could be financial flows. And a good way to think about this is the kind of volatility that you can see in economic markets today. For instance, in 2008, the whole world experienced a very serious economic jolt. Developments in the country of Iceland had a huge repercussion across many countries in the world. Now that gives you an indication of the kind of financial flows that are a part of globalization. So we're not only talking about money flowing from place to place, but also financial decisions made in one place having an impact on other parts of the world. Appadurai also argues that there is a third category of flows, which he refers to as the flow of images or media. Now, this is something that I'm sure you're quite used to. Much of the programming that you watch on television today, for instance, you may actually be watching channels that have originated or programming that's originated elsewhere. More than that, it could also be that the programming that you see today is influenced by shows that have originated abroad. Similarly, you can have content that was made in India, which makes its way to other places in the world. For instance, we know that Bollywood films are extremely popular in many countries across Africa. So this kind of movement of media is, Appadurai considers it to be an important part of globalization. The fourth category that he talks about is the movement of ideas. So this means that ideas that are popular in one part of the world are not restricted to that part alone, but they actually travel across borders. So for instance, something that you may read about in the papers would be, say, events such as gay pride events. Now, gay pride events have their origin in places like New York. But the idea that there should be equality between people, irrespective of what their sexual preference is, that is an idea that has now become popular across the world. And so that's the fourth category of flows that he referred to. The fifth category of flows that Appadurai talks about is that of technology. An easy way to think about this is, let's say tomorrow there is news announced that Apple is going to release iPhone 7. As you can anticipate, there is going to be a lot of excitement in many parts of the world, and people are going to start queuing up, waiting for those products to actually come to their country. So, technology is something that is quite exciting and really moves across various national borders.
Swayam Prabha. Digital India. Educated India.
Okay, so we will continue with the discussion on radiative surface properties. So we have already seen 2 or 3 very important properties, namely emissivity and absorptivity. So we will have to see reflectivity, and then when you extend this properties to surfaces which are not opaque, that is surfaces which allow radiation to pass through, then for example glass, okay, or the atmosphere and so on, we have to consider a very important property called transmissivity, right. So first we will look at reflectivity. As the name suggests, and also from a past experience where we have already worked out problems with reflectivity given alpha, right. We assumed an opaque surface and then alpha plus rho equal to 1, therefore rho is equal to 1 minus alpha. So if I give you the distribution of alpha lambda, you can get rho lambda, you have calculated rho, that is reflectivity and so on. But reflectivity is much more difficult than you thought. It is much more difficult and much more conceptually involved than you ever imagined, because radiation is coming onto a surface, right. This radiation coming onto a surface can be from one particular direction, or this radiation coming onto a surface could be from the hemisphere above this surface, correct. By the same token, you can look at the reflected radiation going out in a particular direction, or the reflected direction going out in the hemispherical space above this surface. Spectral is another story. Spectral story remains as far as direction is concerned. So you can have radiation incident from a particular direction, you can find out how much is going out in a particular direction, or you can look at radiation which is coming from a particular direction and what is going out in the hemispherical space, or you can look at radiation impinging from a hemispherical space above it and going out in a particular direction, or finally radiation impinging from a hemispherical space above it and it reflecting in the hemispherical space above it. To all this you add the spectral dependence. Okay. So reflectivity is a very dangerous property, okay. If you have to give, so if you have to get really to the bottom of it, it is going to take a long time. So I will just define the basic bidirectional reflectivity, and then we will proceed to those reflectivities which are of engineering significance. But reflectivity is a highly involved property, okay. So let us draw a picture and then things will become clear. Let us take the spherical coordinate system. Alok, did you use the lift or? Huh? Okay. What are all these? Okay, please look at the figure. So this is our spherical coordinate system. The incident radiation I lambda I is a function of lambda, theta I and phi I. So can you tell me theta I from this figure? What is theta I? Which is theta I? This one? Correct? Now this fellow is going out. di lambda r, so this should be a function of lambda, the temperature of that surface, theta r and phi r. It should also be a function of theta I phi a, right? Because from theta I phi a only it is coming. Okay, so please watch the please watch the orange chalk. Yeah, what is that angle? Orange chalk. No, I am looking at the projection. Suppose you shine light, the shadow falls on this. This is this xy plane. So what is that angle? Huh? Phi what?
Phi r.
Phi? Very good, correct, phi r. Is everybody through with this? That is the azimuthal angle. What is the azimuthal angle? This one. The theta is this angle. Okay. Now can you draw phi I? Okay. So I should take a. We'll use the green chalk. No, I think I have not completed it properly. It should be from here, right? Okay. Now, what about this? I have drawn the other normal here. Now, what about this theta phi I? Phi I. Is this okay? Is that phi I or? Correct? From here, we are always measuring from here. Okay, so this projection is falling here. So this is phi I. So I lambda I is incident from a particular angle theta I phi I. The reflected can take place in any direction. We are looking at reflection from an angle theta r phi r. Now please note, as opposed to the absorptivity, there is a significant departure here, because the reflected I am putting it as di lambda, because this theta r phi r is a small direction. There is a small solid angle in this big 360 degrees over the hemisphere. Therefore I expect the reflected component to be small as opposed to the incident. Therefore I call it as a di lambda r. Is it okay? Now I have to define the bidirectional spectral reflectivity. Okay, this is the what is this bidirectional spectral reflectivity? Directional spectral reflectivity. Incoming is from theta I phi I, outgoing is theta r phi r. It is still spectral, so it is directional. Therefore it should be rho lambda dash rho lambda dash. Yes. No, I lambda I is a finite radiation which is coming in. But since we are not considering whatever is going out in the full hemisphere in a particular direction, I expect that to be a very small quantity as opposed to I lambda I. Therefore I call it di lambda r. Correct? Because it can go equally in all the directions, unless it is a very specular surface or something. Okay, consistent with my understanding that if it is a diffuse surface or whatever, if it is a surface which can reflect in all the directions, what is coming out in a particular direction will be much smaller compared to this. Okay, therefore I call it di. Is that clear to everybody? Now therefore I define this rho lambda I will remove this fellow. So it will be a function of lambda Ta will be equal to di lambda r. Divided by please note that the denominator I am taking the cos theta because projected area, I am also multiplying by d omega I, which is the elemental solid angle, subtended in the reflected direction theta r phi r. If you do not like this, if I do not do this, this rho lambda double dash may be 0.00001 something like that. Okay. So I am multiplying I lambda I by a small angle cos theta to ensure that rho lambda double dash is decent. Please note that this bidirectional spectral reflectivity is not a dimensionless quantity. Huh? No, allow me to complete. The bidirectional reflectivity by definition is not a dimensionless quantity. It has the units of steradian to the power of -1. Okay. So the bidirectional reflectivity is not dimensionless, it has a units of steradian to the power of -1. But you can see that the bidirectional reflectivity is conceptually very clear, and if you have got a good lab, if you have good laboratory facility, it can be experimentally measured, correct. But in engineering we are more interested in, finally we are interested in rho, okay, or at the most we are interested in rho lambda, but this rho lambda double dash and all that, mostly only physics people are interested. It is coming in one direction, it is going another direction. Most of our surfaces are diffuse, that means it is reflecting diffusely in all the directions, or sometimes we use specular surfaces, that is for special applications. Otherwise from one angle it is going to the other angle and all that is not a fundamental concern to engineers, but it is important that all other reflectivities have their origin from this rho lambda double dash. So this is the basic. So it can be calculated, it can be experimentally measured, it can also come from theory of optics. So if you are strong in optics, then this rho lambda double dash, you can get this rho lambda double dash. Once from this rho lambda double dash you can calculate rho lambda dash, rho lambda and so on and proceed. Are you getting the point? So it has limited engineering significance, but it has got lot of conceptual importance. Okay. So it is so the first time we have a property which is not dimensionless, which has got steradian to the power of -1, which means that we have to use it with caution in problems. In this course we will not work with rho lambda double dash hereafter, but I do not want this is a graduate level course, I do not want you to go out of this course without knowing that there is something called rho lambda double dash. I can just start with rho lambda and then how to convert rho lambda to rho, I could have just finished the whole thing in 5 minutes, but you should know that there is something called the bidirectional spectral reflectivity. Okay. Now if I have a conceptual depiction of reflectivity, so reflectivity can be you can talk about a directional, correct, or you can talk about a spectral, very good. Under directional, you can talk about a directional reflectivity. That is the which we saw. It is actually bidirectional spectral reflectivity, but it is usually called BDRF in capitals, that is bidirectional reflectivity. This is what the optics people, physics people will call. So it is a direction to direction from theta I phi I to theta R phi R. I can have a directional to hemispherical, correct? From a particular theta I phi I into the hemisphere above it, okay. I can have a hemispherical to a directional. Then finally I can have a hemispherical to hemispherical, that is of engineering importance for us, okay. This is called bihemispherical. Then I can integrate with respect to lambda, so I can get bihemispherical total reflectivity. So the bihemispherical total reflectivity involves how many integrations? 5. Integration with respect to theta I, integration with respect to phi I, integration with respect to theta R, integration with respect to phi R, integration with respect to lambda. So finally rho, you are simply writing that rho came after doing 5 integrations, is that okay? So this is simply rho lambda, correct? This is simply rho lambda, double dash is gone, okay. So this is basically rho dash. Then if you integrate, you will get, if you integrate both, you will get the hemispherical, bihemispherical total reflectivity. Now we will go to bihemispherical spectral reflectivity and then total reflectivity, or you can keep this bi silent also. When somebody says hemispherical spectral reflectivity, that hemisphere is applicable for incident as well as reflected direction. Yeah. So what will be the symbol for this? Rho lambda, very good. Rho lambda is expected to be a function of lambda and then temperature of the absorbing surface, okay. I lambda R, I lambda reflected, okay, should be a function of lambda T A, yeah, all, okay. Lambda if you want you can put theta I phi also here, okay. So cos theta I So that I lambda reflected in the numerator, okay, that I lambda reflected can be written in terms of I lambda I multiplied by rho lambda dash, where rho lambda dash can be directional to hemispherical or hemispherical to directional, okay, and that rho lambda dash can be connected to rho lambda double dash, which is directional to directional. To cut a long story short, if you know the bidirectional reflectivity rho lambda double dash, it is possible for you to accomplish the integration and calculate the numerator, right. If you know the directional distribution of the incident radiation I lambda I, you can calculate the denominator. With this we can straight away get the rho lambda, okay. So if alpha lambda information is not available to you, and if rho lambda double dash information, that is bidirectional reflectivity, is given to you, you can calculate rho lambda, and if it is opaque surface, 1 minus rho lambda can be taken to be alpha lambda. So from alpha you can go to rho, from rho you can go to alpha, and all those manipulations you can do. But however, the things get little complicated if I suddenly say that tau is not 0, it is not opaque, okay. From there is only one more reflectivity which is involved, which is basically the hemispherical total reflectivity. Let us do one more and then I will work out the quiz paper. And before that, you want to write the directional total reflectivity, or we will get rid of that? You don't want that? Okay, let us go to this straight away. So rho is equal to there may be I lambda I into cos theta, that cos theta may come in the numerator and denominator. Since cos theta and d lambda are not related, the cos theta can be pulled out in the numerator and denominator, we can remove it, okay. So before that there is one thing, right. I leave it as an exercise for you to get the total reflectivity, okay, that is directional total reflectivity. What did I put? Why did I put rho dash? I should have rho double dash, no.
Hemispherical with respect to
so this is a I didn't want to go deep into this because by the time the class is over you will all get confused. I can have a directional total reflectivity, I can have a directional directional or hemispherical directional, correct. So that is why I can have rho double dash, rho dash and all that. Then you may have an issue with whether from a direction to hemisphere or hemisphere to direction, what is the relationship, and okay, so it gets messy, okay. So that is as far as the total reflected is concerned. Now this is very simple, if you know rho lambda you can get the rho, okay, but if you don't know I lambda I, suppose I don't give you the distribution but I say that the incident radiation is from a black body at 5800 Kelvin, then you can convert it into EB lambda d lambda and use the F function charge and use the alpha lambda and take 1 minus alpha lambda as rho lambda and calculate rho, is that okay. Or if I give you rho lambda double dash, then you can do all the integrations and get up to rho lambda and then calculate rho, then if it is opaque surface alpha is 1 minus rho. Or if I give a problem in which I give you rho lambda as well as tau lambda, then alpha plus rho plus tau is equal to 1, you can calculate alpha, is that okay. So you should seamlessly go from one property to another property, okay. So this is as far as reflectivity is concerned. Now what is the story for a surface which is not opaque, which allows some radiation to pass through? Such a surface, so what happens? Such a surface is called a participating medium. Glass is an example, lenses, filters, atmosphere, then combustion chamber filled with gases. Okay, in all these cases there you cannot assume that the medium is opaque. So there is a transmissivity involved, therefore you cannot simply put alpha plus rho equal to 1. So alpha plus rho plus tau is equal to 1, therefore you have to do the same story, spectral transmissivity, total transmissivity, hemispherical total transmissivity. We will quickly go through those derivations and then we will see, then we will work out some problems on, I told you know, tinted glass, sun control film. If you put a tinted glass, whether it really helps in reducing the incoming radiation, I mean the radiation which is transmitted. Okay, so I will stop here and I will we will quickly see the solution to the quiz paper. So first you want to have the papers and then, okay, you can take a break for 3 minutes. I will distribute the paper and then okay. Okay, the first problem is assuming the temperature, determination of the temperature of the earth, right. So this problem is not fully correct because there is an albedo associated with the earth. The earth has a reflectivity, the earth is not a black body, okay, there is a reflectivity associated with the earth, therefore the temperature you are calculating will be different from the actual temperature which is the mean temperature of the earth, but that is okay. For starters you can assume it is black. And so the first problem is basically a test of whether you know your solid angle and solid geometry well, okay. So it is very simple. Okay, so this is the earth and this is the, so this is the earth and this is the sun. So the distance is 1.5 into 10 to the power of 11 meters. Okay, so dE okay, and the diameter of the sun is so the sun has an equivalent temperature of 5800 Kelvin. So we first assume the sun to be a black body, therefore basically the emissive power of the sun is given by sigma T to the power of 4, so basically okay. Now the intensity associated with the solar radiation is E to ES divided by pi, okay, which is 20.42. Some people have done it very correctly, I do not know whether you anticipated, and maybe you looked at the old question paper or 4 years back I gave this question, I do not know, but basically these sorts of questions I cannot change any data, right, I cannot change the diameter of the earth or the diameter of the, so some questions have to get repeated. I see to it that we do not repeat, but this question we cannot change anything, okay. So from next time onwards I should ask you to calculate the equivalent temperature of Venus, Mars, no? Huh? Of course Pluto is out of the solar system right now, yeah, bye bye, Pluto is not there, it is supposed to be part of something else, okay. Now I is there, now just calculate the solid angle and find out what is the radiation which is incident, what is the power which is coming onto the earth, okay. Under equilibrium whatever is going out must be equal to whatever is coming, earth is black, therefore sigma TE to the power of 4 of the earth must be equal to whatever is incident, therefore TE equal to Q divided by sigma whole to the power of 1/4, that is the story, right. Now the solid angle What is the dA? Area of the receiving surface. Who is receiving? Earth. Okay, so pi d squared by 4, that is the projected area. The beauty of this problem is, even if it is a sphere, what it receives from the sun depends on the pi r squared or the pi d squared by 4, but when it emits, it will emit from 4 pi r squared. That is why some people fail to recognize this 4, they got orbit temperature like 557 Kelvin, 450 Kelvin, 557 Kelvin and so on. Okay, the earth is, the projected area as far as incoming is concerned is pi r squared, but when it is emitting it is 4 pi r squared. Okay, so pi d squared by 4 cos 0 divided by, this is very small, 5.81 10 to the power of minus 9 steradian. Okay, this is d omega. Q earth is equal to I sun okay. Okay, please look at the board. I am spending a lot of time on this because other problems all of you have done, most of you have done the other problem. I sun we know, we just calculated area of the sun. What is area of the sun again? As seen by pi d a squared by 4, as seen, it is not 4 pi, it is because as seen by this. Okay, we are looking at solid angle. Okay,
of 1, that is incorrect.
Right? It is correct. Pi d squared by 4 multiplied by this. Okay, so this is basically no into 0, no way, into so this must be equal to is that right? Sigma T to the power of 4 is the black body radiation of the earth multiplied by the total area which is emitting. It is emitting in 4 pi r squared from the surface area. So this 20.40 we calculated. This pi d squared basically it is the projected area for both the earth and the sun. Okay, so if you do that, T is if you calculate the albedo, what will be the final temperature you are getting? 255, 258, not 285. Are we getting 288 or? If you calculate the albedo, the reflectivity, the answer will change. Okay, fine. This is the solution to the first problem. So if you have calculated T and got some incorrect answer, I have given you 4 marks. If not done anything, I cannot give marks. If you got the correct answer, you will get 8 marks. Okay. Second problem and third problem is all straightforward. So second problem you have to use the F function chart, right? So okay, so you have to calculate lambda Ts. So you have to use the F function chart, okay, and then proceed. So you are getting epsilon is 0.46. So 6 marks for getting this. Most of you have got it. There may be some small. Some of you got 0.44, 447, I have ignored all that. But if you have got 0.36 and instead of 0.74 you got 0.64, that means you have made a mistake. So proportionately I have reduced some marks, fine. Now the other part of the question is people, I mean you went wrong. If I twist slightly then you are in trouble. The part C, I told you what is a wavelength lambda 0.5 for which 50% of the total radiation emitted by the surface lies within the spectral region lambda greater than or equal to lambda 0.5. That was the question I asked. It is not so, I am not so dumb, man. I know you can read the tables and take 0.5 from there and say lambda t is 4100. Why will I ask such a dumb question? That is only for a black body. For this body there is already an emissivity. Are you getting that point? So the total radiation emitted by the surface is epsilon sigma T to the power of 4. Okay, that is 0.64 times sigma TW to the power of 4. So what I asked you was, okay, so what is the hemispherical total emissivity that you have seen is 0.46. B you can calculate, that is 0.74. Okay, so what is a wavelength lambda 0.5 for which 50% of the total radiation lies in the spectral region? That means what I am asking you is, epsilon 1 f of 0 to lambda 1 t what is this? This is the overall epsilon. This is multiplied by the sigma t to the power of 4, here also it is sigma t to the power of 4, therefore if you divide it becomes f. Okay, so the right side you get something like 0.232. The first one epsilon 1 into this is 0.105 plus 0.55 into so now corresponding to x, so lambda half t equal to 3468 micrometer. You can see from the table, right? If f is 0.3761, what should be the lambda t? Just look at the f function chart. Huh? 3.5 micrometer. Therefore, no. Yo. Okay, fine. X is point. So lambda half. $2.89, huh? Is that correct? Now for people who completely no idea of what I have done, okay, I am making an assumption, I am making a proposal that it will lie somewhere in between this. Why did I make an assumption that it lie between 2 to 4? Because I know that the temperature is 1200 Kelvin. So from Wien's displacement law, 2898 by 1200 is about 2.5. Therefore I am making an intelligent guess to start with. I am assuming that 50% of the radiation will be somewhere here. Okay, so I am trying to see if I stop somewhere at a particular value of lambda, I can find out what is the f of 0 to lambda up to that place. Now I have to see what is that value of lambda at which this f of 0 to lambda is equal to half of the total radiation which is emitted by the whole surface. The total radiation emitted by the whole surface is the hemispherical total emissivity epsilon multiplied by sigma t to the power of 4, which is that epsilon is given by 0.464. I want 50% of that, so I am multiplying by 0.5. So 0.5 emissivity into that sigma t to the power of 4, I bring it to the left hand side, so that left hand side also instead of sigma t to the power it becomes f of 0 to lambda t. Okay, so the first part I know the epsilon 1 0.75 into this gives you 0.105, then epsilon 2 is 0.55 multiplied by it ends at basically 4 micrometer. I am getting 0.607 minus x and then x equal to 0.33761. Corresponding to this value of f, I find out what is a lambda into t. So that lambda into t turns out to be 3468, but I know t is equal to 1200. Therefore, lambda is 2.89 micrometer. If you do not like any of this, now find out what is the total radiation emitted by the body up to 2.89 micrometer. Calculate the emissivity, multiply by sigma T to the power of 4. Find out the total radiation emitted by the body, which is emissivity into sigma T to the power of 4. You will find that the ratio is half. Okay.
Early morning, when all of us are busy preparing for the day's activity, a section of people with green masks on their faces are out there on the streets. Going door to door, collecting our domestic waste and dumping it into large bins placed at different locations in the campus. At this stage, A to Z organization, a leading provider of waste management services in Kanpur, steps in. It carries away the waste to its recycling plant and recycles it into useful manure. The entire process is a part of elaborate waste management strategy adopted by the institute. While the domestic waste is recycled outside the campus, green waste, mainly comprising fallen leaves, takes two routes. A large fraction of the green waste is handled through composting, a natural and cost-effective way of recycling organic matter. The process is indeed very simple and can be carried out on a wide range of scales in almost any indoor or outdoor environment. In the institute, it is primarily done outdoors owing to availability of large open spaces. The dead leaves are dumped into deep rectangular pits created in open and loosely covered with soil. The fill pits are sprinkled with water and left for few months. During this time, the natural decay process breaks down the organic matter into rich humus-like material. The final product is sieved and used as compost for gardens and flower beds. Another method used for green waste treatment, though on a small scale, is vermicomposting. It is a simple biotechnological process where various species of worms, usually red wigglers, white worms and earthworms, are used for decomposing green waste. In the campus, the complete process is carried out within the confines of a vermicompost plant at the nursery. The unit has 2 storage pits on the left, 6 bins on the right, and 2 large pits in the center. Vermicomposting is a multi-step and a closely monitored process. The stacked leaves are dumped into a bin and left for drying. After a week, the dried heap is shifted to the adjacent bin and sprinkled with water. Water helps in reducing the volume of leaves. The following week, the heap is shifted to the third bin, where a little amount of cow dung is added to it. This stage lasts for about 2 weeks. By the time the process enters the 5th week, the texture of leaves has changed considerably. Now is the time for worm activity. The 2 large pits in the center of the vermicompost unit are used for worm action. Each pit can accommodate 4 vermibeds at a time. A banana leaf serves as the base of the vermibed. A layer of 3 to 4 inches of organic mixture is spread out on the leaf and earthworms are added over it. Earthworms are also known as composting worms as they are very efficient processors of organic material. The whole process is repeated till a pile of 1 to 1.5 feet is created. The pile is topped with cow dung and left undisturbed for a month depending on the weather conditions. During this time, the earthworm digests the organic material and turns it into vermicompost. The finished product is dark and crumbly with an earthy odor. After sieving, it is used as manure for surrounding areas. This manure has been tested for its high nitrogen content in the Institute's laboratory. By using the most eco-friendly alternatives to leaf burning, the Institute has gained the status of Zero Burn Campus. Apart from solid waste, the campus generates large amount of liquid waste as well. It was in 1960 when the first concrete step towards liquid waste management was taken. Back then, the entire campus population was concentrated to the north of a distributory running from the east to west of the campus land, while the southern area remained untouched. To manage the generated liquid waste, the entire northern area was divided into 5 zones, each provided with sump wells at strategic important locations. This elaborate system was designed for sewage to flow under gravity. The sewage was collected and transported via a network of sump wells and fed into the oxidation pond on the northern end of the campus, where it got oxidized. This partially treated water was used for horticulture needs of the surrounding area, which has now turned into a pristine orchard. In the last 5 years, about 200 fruit trees have been planted in the orchard, including guava, mango, chiku, and bear trees. Many bird varieties can be easily spotted here, like the kingfisher, woodpecker, and Indian tree pie. The orchard is also frequented by several vibrant migratory birds who keep coming and going. In 2009, the Institute took another crucial step in this direction. It installed sewage treatment plants in the campus, thus advocating the 3 R's of the waste management strategy: reduce, reuse, and recycle. each sump well has one sewage treatment plant that recycles the sewage collected from the nearby areas. As the years passed by, the campus population increased and the southern area of the campus began teeming with life, thus adding to the liquid waste generated in the campus premises. Since technically it was not feasible to pump the liquid waste from the south to north zone, another sump well 10, and an oxidation pond to collect the sewage from it were built near Hall 8. The sewage treatment plants installed at each sump well are biotreatment based plants. This setup comprises a primary settling chamber, 3 rotating discs also known as rotors, and a lamella zone. The sewage from the adjoining areas flows under gravity and is collected in a sump well. From here, it is pumped into the plant. The first chamber of the plant is the settling chamber where large particles in the sewage settle down. The sewage is then lifted to the first rotor known as the lifting rotor. Lifting rotor lifts it further to the aerobic rotor where aerobic aeration takes place. Aerobic aeration is a process where bacteria act on the sludge, eating away the organic matter and cleaning it. From second rotor, it is lifted to the third rotor where secondary aeration takes place. It then enters the lamella zone where heavy particles settle down. To further disinfect the treated water, it is subjected to chlorination. In the last stages of the treatment, water is passed through 2 filters. From chlorination zone, the treated water enters into the breaker tank, from where it is lifted through pumps into the sand filters. These filters remove the suspended particles left behind in water. Finally, the water enters into the carbon filters for final removal of any foul odor left behind. Beside the oxidation pond, another water body was constructed to collect rainwater and used swimming pool water to prevent it from flowing into drains. Today, this water body is used for fish farming and horticulture purposes. Water recycled at each sump well is used for gardening and other horticulture needs. Presently, the total amount of recycled water is close to 1 million litres. The samples have been tested by the UP Pollution Board and were found to be satisfactory. Also, regular testing is done in the Institute's laboratories. As per the February 2012 lab reports, the BOD level, which stood initially between 80 and 100, went down to between 7 and 12 after treatment. The COD level had also reduced drastically, thus rendering the recycled water suitable for horticulture purposes. Our ultimate goal is not to discharge any untreated water to drains and maximize the use of recycled water. As the campus population increases, the recycling capacity will be increased. The Institute will endeavour to exceed the requirements of relevant environmental legislation and to improve the standards of environmental management. Well, the future looks very vibrant. The Institute is planning to turn the zone into a recreational park offering a variety of leisure activities like boating and fishing. The area with its scenic beauty and clean water bodies will truly be a picturesque place, providing a refreshing break to the campus residents.
Hello, good morning everybody. I am Raghunandan Sengupta. So I'll just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance, as I mentioned. Now, we all know that in 1997 the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics, was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been an exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high-ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also. Obviously, when there is a huge amount of development, so obviously due to some regulation errors or something, there has been some pitfalls, which I think should be a bullet point for people who are really interested to take up quantitative finance. They should be aware. So consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So what should be done? So the main thing is that even if you know the technique, is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner, such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall in-depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.
Swayam Prabha, Digital India, Educated India.
So, in the last class we for the interfacial heat and mass transfer, we included the effect of surface tension and the disjoining pressure, and we found out the equations for continuity, momentum as well as the energy. Okay. In this class we are going to do the species balance, okay, before we move on to specialized topics. Now, in the species balance, unlike temperature, see, temperature is continuous across an interface, right? Temperature is continuous, right, across the phases or across the interface, correct, right. But species or concentrations are basically discontinuous, right. Okay. So, okay. So, a general interface, if we consider a general interface between two phases, say phase K and phase J, all right, okay, and there is a mass flux, and in phase this is phase K and phase J. Now, the species that we are considering is I, okay. So, there is a migration of species I or mass flux of species I between these two phases, right, okay. So, K and J are not the species, these are the two phases, okay. I is basically the species, okay. Now, the total species mass flux, which is basically m dot I, okay, is basically, it will be given as, and we will come across each and every one of them in details, okay, and we will see what each of these terms exactly means. Gi, okay. Now, this Vki, what you see over here, is basically nothing but the velocity of species I, okay, in phase K, right, okay. Similarly, this Ji means the velocity of species I in phase J, right, okay. It's like K, here it was one phase, this is the other phase, okay. So, similarly over here you have basically two velocities that we have defined, okay. Now, these velocities are further defined like this: rho Ki Vki equal to Jki plus, got it, okay. On the other hand, this you guys already know from your previous lectures, got it, okay. So, this is the velocity that has got a diffusion component, obviously, okay, that is the diffusive flux, as you know, J is always the diffusive flux, right. So, the velocity of species I in phase K is represented in this particular fashion, okay. Now, if you substitute these relationships, okay, back in the main governing equation, which is over there, okay, you get your m dot I double prime j k I dot n omega k I rho k v k minus v I is equal to j I, sorry, got it, okay. So, that is now the species flux of the ith species. Remember always this is for the ith species that we have determined this flux term, okay. Now, the overall mass conservation mass conservation at interface. This we already did in the last class, if you recall, was basically this, right. Right, this we already did in the last class itself, right. Okay. And based on this, your m dot I double prime now can be written as j k I, this is the diffusion term, plus omega k I m dot double prime, right, okay, is equal to j I dot n plus omega j I m dot double prime, right. Okay. So, you can understand that there is a diffusive component, there is a bulk component, correct. So, this is basically nothing but the diffusive component, and this is more like the bulk component, right. Okay. Because if you look at this carefully from the previous equations, how we have actually written it is that if you look at this particular term, say for example here, this is nothing but the diffusion. This is the diffusion of species I through the phase k, okay, or through the phase j, correct. Okay. While on the other hand, this is nothing but the bulk velocity with which phase k is actually moving or phase j is actually moving, and as it is moving, it is carrying with it the mass fraction, okay, of whatever that species I is, right. Okay. So, it basically has got two components, bulk and the diffusion, right. So, that should be kind of clear to everyone. So, this is always the case. So, you have a diffusion of species and then you have a bulk of bulk movement, right. Okay. So, diffusion happens because of the diffusion coefficient, right, okay, and bulk happens because there is a bulk migration, okay, of one fluid into another, okay. And as you know, m dot double prime is equal to summation of m dot I double prime I to whatever n that you have, got it, okay. So, if the species flux is not specified, okay, the total mass flux will be okay, got it. Now, for a binary mixture, this diffusion flux J, okay, you know how to represent it for any particular mixture, okay. This is basically represented as something like a rho k d k 1 2, 1 2 being the two components. This is basically nothing but the concentration gradients, if you look at it with this, okay. So, this is a very standard Fickian diffusion kind of a model, right, where this is the diffusion term and this is the concentration gradient, right. So, you can understand in one case this component was transported by the bulk movement, right. This is actually transported by the concentration gradient. So, this term is very much like your heat conduction kind of term, your Fourier's heat conduction. There is a concentration gradient, instead of d there you have k, right, and so there is a transfer of heat. Here instead of transfer of heat you have a transfer of mass, right, you have a transfer of species in this particular case. Okay. Now, the binary mixture can be in the presence of any of the phases. So, for example, here we wrote it in terms of some arbitrary phase, okay. It can also have it in terms of say liquid solid, solid liquid, then liquid gas. It can be with respect to any two combination of phases, right. Okay. So, it does not necessarily mean, so it is basically whichever phase it is present in, it is the diffusion in that particular phase, right. Okay. Say for example, you take the example of say a droplet, because droplet is something that we will cover immediately after in a short while. So, the droplet, say it's a binary droplet, let us assume for the time being it is a binary droplet. Okay. By binary it means let us say a water and ethanol is actually present in this particular droplet, water mixed with ethanol, right, and this droplet is actually evaporating. This is the phase boundary, right. So, this is the liquid phase, this is the gas phase, correct. And what happens in the gas phase, both water and ethanol actually evaporates and gets mixed in the gas phase, right. So, the diffusion of water in ethanol in the liquid phase, when we are talking about this binary diffusivity, right, when we are talking about this, right, that coefficient, that d, will be very different from the d that you have here, got it. So, the evaporation of water vapor in air, right, is very different from or the diffusion of water vapor in air is very different from the diffusion of liquid water in a water ethanol mixture, got it. Okay. So, liquid water, okay, say this water liquid, okay, is actually diffusing in a water plus ethanol mixture, right. Okay. So, it has got a certain value of diffusivity. Okay. On the other hand, water vapor in the vapor phase is diffusing, okay, say in air plus water vapor plus ethanol vapor, right. Okay. So, it is diffusing in all three of these. Okay. So, the diffusion coefficient, this d and this d are very different, they are not equal to each other. Okay. That is what we mean, right. So, that you can easily imagine that in the gas the diffusion is pretty fast, whereas in the liquid the diffusion will be very slow, got it. Okay. So, but the idea was to give that it happens, mass transfer or species transport across the interface happens principally because of diffusion and this, right, individual diffusion and the mass transport that is happening, okay, between the two phases. Okay. So, this actually governs the evaporation. From here you can imagine things like evaporation, condensation and things like that, right. Okay. So, now let us look at this example that we have over here. Okay. So, this example can be of various types, but let us look at one significant one. Okay. So, here is the example. Let us take a liquid and a gas, okay, and the interface is flat. Okay. So, let us not talk about curvature and any other things, the depression of vapor pressure and stuff like that. Okay. So, the liquid, so the species here is XA, right, A is the name of the species, A is the species that is present both in the liquid phase as well as in the gas phase, got it. So, if we look at this particular thing in details, that there is a liquid phase and then there is a gas phase that are present. Okay. What is happening, what we are trying to do, so this is not a pure liquid, this is not a pure gas, right. Okay. So, there is this liquid has got several species, one of those species is A. Okay. So, A, when this A, the fraction of A inside this particular species is denoted as XA, XAL when it is present in the liquid phase, and when it is present in the gas phase it is denoted as XAG, right. Okay. So, this is basically the mass fraction, okay, of the species A in both the phases. Okay. This is direct corollary of the example that we just now saw. Okay. Now, on the other hand, this particular figure, this is a pure evaporation problem, right. This is how things evaporate. You have a saucer filled with water, this is how it actually evaporates, right. On the other hand, you have this solid to gas interface also, sublimation, naphthalene if you have seen. Okay. So, that is a solid gas media or two phases separated by a sharp interface. This is a liquid gas media separated by a sharp interface. Okay. So, evaporation and sublimations are typical examples of mass transfer, got it, two cases of mass transfer. Now, in case 1, if you look at, this is 1, if you look at case 1, okay, it is a pure liquid or a pure solid which is actually evaporating or sublimating, okay, into the gaseous mixture, okay, and it is purely controlled by the species gradient in the gas phase, right. Because why it is flat, that is because there are no other species present, right. There is no other species, the value has to be equal to 1, If it is a pure liquid, say we are evaporating pure water, this is pure water and that is pure that is the atmospheric air, right. So, in the liquid phase you are not going to have any gradient with respect to the water, right, because it is only pure water, it will be always 1, right, no matter what you do it will be always 1, right. So, here in but on the gas phase it need not be 1 because water vapor is going into air, right. So, air basically has got oxygen, nitrogen and all these things, right. So, water vapor is only a very small fraction of the air, right. So, once it evaporates you can see that you develop a gradient, okay, a species gradient in the gas phase, okay, but you do not develop a species gradient in the liquid phase, got it, in both the cases, got it, okay. So, the concentration gradient also exists in the liquid in the case of 2, however, in case 2 that means it is not a pure liquid anymore, like the example that I gave, it may be water mixed with ethanol, water mixed with something else, right, okay, it is not pure, okay. Therefore, concentration gradients will also exist in the liquid and the solid phase also, here and here you are going to have that concentration gradient, right. Why there will be a concentration dip, can you explain that? That is because, okay, it is basically supplying, right, the liquid is actually evaporating or that species is actually evaporating and going into the gas phase, right. So, if it is water, water is getting converted to water vapor. Since it is getting converted to water vapor, okay, there has to be a slope near the interface, right, otherwise how would it match the flux, right. This particular gradient, this particular slope has to match the flux with which the amount of water vapor that is actually escaping or the amount of liquid that is getting converted to vapor, right. Like for example, in the case of heat transfer what happens, that slope basically gives you how much heat is transferred, right, Q is equal to minus K dt by dx, things like that, right. Here it is basically the mass flux of species A, right. So, this is what actually happens and there is a depression of the concentration gradient, here the concentration is lower, here the concentration is higher, that is because at the interface, right, where evaporation actually happens, right, in that particular region if you consider the mass fraction of A is actually lowered, it has to be lowered, right. So, if you look at this particular evaporation, these things are all interfacial phenomena, it is not happening from here, 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 it is always happening from this zone, right, it is not boiling, right. So, it is only happening across the interface, right. Since it happens across the interface, say initially you had a system, say for example, okay, where everything was kind of homogeneous, right. So, if you sample water from any portion of this mixture, it will always give you that XA value and that XA value is some kind of a fixed value, got it, okay. So, that is true, that is because the composition is not varying, but however, as soon as you start having evaporation from one of this side, right, from this surface, what happens is that locally the concentration of water vapor will be lowered, right. That is because some water in that zone is actually escaping, some water in that zone is escaping into the vapor form. So, if you look at it in a kind of a discretized fashion, right, evaporation is happening in this zone, right. So, here the concentrations of water vapor will be more or less the same, right, only in this zone it will start to drop, that is because water is getting converted into water vapor locally, okay. As a result, the other component with whatever that is the other component, that means other species that are present over there, okay, locally the concentration of this particular guy is getting reduced over here, okay. This is particularly true, for example, if you have water mixed with some other non-volatile solvent, right. If you do that, you will find that the water vapor concentration at the surface will continuously decay, okay. Similar thing happens in the case of sublimation as well, okay, because there are two species, okay. Now, so the mass transfer rate is basically limited by both the phases, this and this, how quickly we can supply it and how quickly we can take it away, right. If it is a diffusion driven phenomena, which in most of the cases it is, right, there is no flow as such, right, there is no flow assistance over here. Okay, what you will find is that the water, liquid water gets evaporated into water vapor, that water vapor is basically transported away from the interface, right, by diffusion, because here the slope is in this particular fashion, right. So, locally on the gas phase the concentration of water vapor increases, locally in the liquid phase the concentration of water vapor goes down, right. So, in the liquid what will happen is that more water will rush towards the interface and more vapor will be drawn away from the interface, right. So, this is how evaporation is basically sustained, right. So, when you actually have a saucer of water, okay, let us consider this example. So, when you actually have a saucer full of water, actually let us go to the journal. Let us look at this, that you have a saucer full of water, right. So, this is liquid water and say you have mixed it with something, right. So, it is basically water plus some non-volatile solvent. Non-volatile solvent means it vaporizes very slowly, right, that is what we mean. This is the interface, this is air, okay, hanging over there. Now, what happens, what is the mechanism of evaporation in this case, right. So, that is what we want to answer, correct. Okay. So, what happens is that locally some liquid water vaporizes, right, from the surface, it does not happen from here, it happens only from the surface layer, correct, and it creates an enhanced concentration of vapor on the liquid side. So, that is the vapor side, right. Okay. So, on the vapor side, so if I have to plot this on the vapor side, if I just look at this particular distance, okay, there the concentration of water vapor increases, okay, in the vapor side, right, whereas on the liquid side the concentration of water vapor actually decreases, right, all happening in this small layer, okay. Okay. So, now if this water vapor is saturated completely, I mean this water vapor is present all over, right, okay, the evaporation should actually stop, correct. Okay, this has happened, this is the mechanism, this is because air in this particular location, right, just above the interface, if this is the interface, just above the interface, if you consider that air layer, so this is air plus water vapor, right, that is coming, and this water vapor source is basically the interface, right. Now, air you know has got some particular saturation pressure, right, water vapor has got a particular saturation pressure. In other words, if the relative humidity of this particular section, this RH becomes equal to 100%, right, then what will happen is that no more water vapor this air can actually accommodate, right, because it cannot hold anything more, it is already at its full capacity, right. The evaporation from this surface will stop. Okay. This is what happens when you actually have a very humid environment, right, very humid, like for example, if you want to dry your cloth, say for example in a very humid environment, say during the monsoon, okay, not because of the monsoon per se, but say there is no rain, but the atmosphere is very humid, right. So, 90-95% humidity, okay. So, that means the air in this particular region takes a little bit of water and becomes saturated, right. So, what is the mechanism for relieving this, correct. So, the mechanism of relieving this is, if you, this is the layer which is very close to the interface, right. If you look at a layer which is very away from the interface, okay, far away from the interface, right, here what will happen is that here the water vapor concentration is low, okay, if it is during the winter season what it is right now, right. So, in this near the interface the concentration is high, away from the interface the concentration is low, particularly it is say Bangalore's weather, it is like 40-50% relative humidity, right. So, water vapor by natural diffusion will go from here to here, right, that has to happen, right, because it has to flow from a high concentration to a low concentration, that is exactly what it does. So, as soon as it does, this region now gets relieved, okay, it gets relieved, right. So, as soon as this region gets relieved, okay, more water can come now from the liquid side. Got it? So, this is the mechanism of evaporation, right. So, here what will happen if we draw it across the interface, okay, here the concentration of water vapor will be high, away the concentration of water vapor will be low, right. So, it is from high to low, right, whereas on this side of the interface, right, on the liquid side. So, this is the air side, right, this is the liquid side, right. In the liquid side of the interface, what will happen? It will be just show the opposite trend, right. So, this is actually low, this is actually high, right, because here the liquid is locally depleted, right. Okay. So, this supplies liquid to the interface, this takes away water vapor from the interface, right. So long this process continues, your evaporation continues, you got it. This transfers liquid towards the interface for it to evaporate, this takes the vapor phase away from the interface, so that this region, if we call this as a region, right, these two regions can be relaxed, got it. Okay. So, that is exactly what we have done over here. Okay. So, one other thing is that the gradient of species in, let us go back to the, so the gradient of species A in the solid is greater than the gradient in liquids and greater than the gradient in gas. This you will always observe. That is because these are governed by the relative mass diffusivities. Okay. So, because the mass diffusivity in one case is lower than the other and the gas phase mass diffusivity is the highest usually. So, the gradient will be the lowest, right, because it has to match the flux, right. For matching the flux there are two things, one is basically the diffusion, the other is basically what we call concentration gradient, right. So, if the diffusion is low, then this has to be high, okay, to match the flux, okay. And usually the gas mixture is approximated by an ideal gas, okay, and things like that. These are very standard notations, okay. Now, the other question that you might want to ask, that see, we already saw that with curvature, okay, there was a depression of the vapor pressure, right, of the saturation pressure, that we did in the last class or the last lecture, okay. Now, here the question that one would like to ask is basically, when you have this liquid to gas or solid to gas kind of transitions, right, the partial pressure of water vapor in the gas mixture at the interface, okay, is usually given by something called the Raoult's law, okay. This is called Raoult's law, okay. So, this is basically, if you look at these two terms over there, this P A at y 0 minus and P A at y 0 minus, these two are basically the partial pressure of A in the gas mixture. It is the partial pressure of A in the gas mixture just adjacent to the interface. That is why you have written that minus, right. It is just on the other side of the interface, got it, just on the other side of the interface. And this XAL and XAS, whatever you call it, is basically the mole fraction of species A in the liquid, or it can be the solid, depending on which way you are looking at, okay. And P saturation that you see over here is basically nothing but the saturation pressure at the interface or close to the for which the temperature of the interface is given, okay. So, if the interface temperature is Ts, you calculate whatever is the P saturation because of that, okay. Now, if it is pure species, like for example, as I said, pure liquid, okay, or pure solid. Now, in that particular case, this was equal to 1, this we already established in the last thing, right. As soon as we say that this is equal to 1, the partial pressure of water vapor in the vapor phase, okay, is equal to the saturation pressure, right. If it is not, however, which is normally the case with mixtures, the vapor pressure is actually depressed. That is because XAL is always less than 1, right, because it is a mass fraction. The maximum value that it can have is equal to 1, it is always less than 1. Because it is always less than 1, okay, because it is always less than 1, the partial pressure of the vapor phase is actually lowered, okay, when other species are present. That means when you are dealing with say water plus ethanol, right, mixture, got it. The vapor pressure of water vapor, right, in the gas mixture at the interface, okay, will be lower than the saturation pressure, got it, okay. It will be lower, it has to be lower. That is because you can think about it like a fight, right. The space is limited, right. So, there is an interface, right. Here you have two species like species A, XA and say XB, correct. Both are trying to evaporate and go into that same space, right. The space is limited, right. Okay. So, as it tries to go into the same space, obviously if it is alone, okay, its pressure will be the same as its saturation pressure. Since it is not alone, right, depending on what amount of A and what amount of B is present, okay, its pressure that is present in this particular region is consequently lowered. It is basically common sense, right. Pressure is what? The number of molecules you can consider in a particular space, right. So, species A, okay, is actually evaporating into the same space, species B is also evaporating into the same space, right. So, they are both fighting basically for the same space, right. Since they are both fighting for the same space, right, it is obvious that the pressure of species A in that space will be lower than the saturation pressure that species A would have had if it was present alone, right. So, if it is just a pure liquid water droplet, that space will be only water vapor, right, H2O. Now that it has got ethanol, okay, this space will contain water plus ethanol, right. It will have the vapor phase of both. As a result of that, you cannot have the same partial pressure, right. So, the mass fraction of species A in the gas phase now can be determined just by that partial pressure that you have determined over here divided by the total pressure. Total pressure is always the same, okay, because it is a total pressure, it is atmospheric, right. Okay. Similarly, you can find out other things like mole fraction and things like that. Basically, you bring in the molecular weight because species A and species B are there. Okay. So, conceptually it should be clear that why evaporation happens, this is what we explained, okay, and how it actually proceeds, right. There is a depression of vapor pressure if we are dealing with two species. If we are not dealing with two species, there is no curvature effect, right. We will have the partial pressure of species A to be the same as the saturation pressure, okay. So, that part needs to be very clear, okay. So, here we have tried to explain how evaporation happens across the interface, okay. So, in the next class we are going to look at a particular topic which is basically what we call the droplet, okay, and the droplet is what we are going to do in the next lecture.
Swayam Prabha, Digital India, Educated India.
So, now that we have established this interfacial heat and mass transfer, we know how the interface actually behaves. Now, let us look at some of the speciality problems right now, okay. And one of the speciality problem is basically droplet evaporation and combustion, okay. Why is it important? As I said, that droplet evaporation is fundamental to almost all applications that you can think of, okay. From gas turbines to spray dryers to surface patterning, whatever you can think of. This droplet may be in the sessile mode. Sessile mode means it may be on a surface like this, or it can be in a spray mode where the droplet is basically injected as a part of a spray, okay, like this. There are many droplets, okay. So, these droplets basically represent a multi-phase system, right, because there is a liquid core and then there is a gas exterior, right, whatever it may be. It need not be water, it can be anything, okay. And the liquid core can be multi-component, multi-species kind of a system as well, right. For example, as I said, water ethanol was one example, okay. These days, for example, when we go to renewable type of energy, okay, people use something called biofuels, say for example. So biofuel is a mixture of n number of hydrocarbons, okay, from very small hydrocarbons to very large hydrocarbons, right. So this liquid phase usually have a multi-component nature or a multi-species nature to it, right. Apart from that, so that is the gas phase, okay. This is the sessile droplet. Sessile droplet, for example, is used in surface patterning a lot, right. So these sessile droplets might contain, you know, polymers or nanoparticles, okay, and it can be used to create structures on the surface, right. Similar things can be done in biological applications also, okay, like flow cytometry and things like that will all have this droplet based framework, okay, and they will have this droplet based thing is also used in microfluidics application, for example, where a droplet containing cells, okay, may be actually used for some point of care type of diagnostics, right. Okay. So there are many applications of droplet vaporization, okay, and droplet deformation, droplet atomization, and it covers regions from healthcare all the way up to combustion, that means all the way up to power generation. So it affects every part of our life, so to say, okay. However, the combustion part is a little bit more special. It deals with only combustion, that when these droplets actually participate in combustion, what happens, okay. So in this particular series of lectures that will follow, we will first try to anchor what is droplet vaporization, how we can actually analyze droplet vaporization, and then we will go on to a little bit more special topic concerning combustion, okay. And we are going to use a PPT as well as the journal to actually look into what we can have, okay. Now, what is the phenomenology of droplet evaporation, right, that is the key thing, okay. Let us consider one droplet now, that is because multiple droplets had got its own problems, okay, there are interference between multiple droplets, okay. So this is important, droplet vaporization, because most of the technological processes that we talked about just now, it is desirable basically that you want to gasify the droplet or even combust the particular liquid in a gaseous medium, okay, at a fast rate or at a controlled rate with various degrees of control, right. We want to do that, right. We basically want to control this evaporation rate, okay, in order to achieve certain goals, whatever those goals may be, right. So what does this droplet actually do? If you carefully look at the droplet, okay, this is a isolated droplet that we have put over here. This is isolated. That means let us not assume that it is surrounded by any other droplets. It is like one building block that we have taken out, okay. So there is, what this droplet actually do is that there will be heat and mass exchange between the droplet as well as the gaseous medium in which it is in, right, okay. It is important. So what will happen is that there will be heat that will come from the ambient and the droplet will generate the vapor which will actually get mixed with the ambient, right, that is vaporization. The reverse you can talk about is condensation, right. So there will be heat that will be given out by the droplet, the vapor that is there around the droplet will just condense, okay. So in that case the droplet size will increase. So this single droplet actually exchanges heat, mass and momentum with the gaseous medium, right. So if I want to analyze this droplet, right, okay, in its complete and holistic view, okay, what are the things that we need to do, right, that is a pertinent question over here. Forget about it is combusting or not, just to do the heat and mass transfer, what equations do we need to write, what is the mode of analysis that we need to do, right, okay. So the complete analysis will involve basically 4, emphasize the word 4 interacting processes. One is a liquid phase transport, that means what happens in the liquid phase, that means within the droplet what happens. The gas phase transport, that means what happens in the gas phase, okay. The phase change at the liquid and gas interface, right, and if you have combustion, then what are the chemical reactions that are taking place in the gas phase, right. These are the 4 things that we need to answer, right. So we have to basically solve the governing equations, that is mass, momentum, energy, species, right, in both the phases, that means in the liquid phase, in the gas phase. These are all the equations that we derived, right, so far in the lectures, right, how to write equations in the liquid phase and in the gas phase, right. So, here in this case, this is a very dispersed kind of a system. It's had got a well defined boundary. It's not a problematic boundary anymore, not in this spherical configuration, because the droplets we are assuming it is spherical, okay. But you need to solve for the liquid phase, the gas phase, the phase change, as well as the chemical reactions. These 4 things needs to be solved properly, right. What are the important considerations for this? Okay. Important consideration is that there could be relative motion between the droplet and the gas phase. This is normally it is true, because for example, we are spraying droplets, okay, into a heated environment, right. Let us take that example, right. Okay, they are spraying something in an environment, okay. So, the liquid phase velocity or the speed with which the droplets are injected into that particular phase may be different from whatever is the gas phase velocity, right. Okay. So, the gas may be moving at a different, so it is, say you have a pipe, there is a flow which is going at a velocity V1, right. You are injecting droplets into this flow field, right, at a velocity, say for example V2, right. So, this V1 may not be equal to V2, in most of the cases they will not be, right. So, there will be a relative motion between the gas and the liquid phase, okay. There will be something called a Stefan flow due to surface gasification. As this droplet evaporates, right, the interface is actually shrinking, okay, or expanding depending on which way you think it is, right, either it is a evaporation or it is a condensation phenomena. So, there is something called a Stefan flow which is created due to this surface gasification. That means there is conversion, okay, of species from one phase to the other, that is what is happening, correct. Now, there is also droplet drag. If there is relative motion between the droplet and the gas phase, there has to be drag, right, because if say for example, you put a cylinder in a flow field, right, you develop a drag on the cylinder, right, that is very common, okay. But that drag comes because of the relative motion, pressure drag, and there is viscous drag also. Same drags will be applicable over here also, not in that exact form, but it will be applicable, right. Similarly, there will be internal recirculation also inside the droplet. When there is a flow outside, why shouldn't there be a flow inside, right. The droplet is also in the liquid phase, right. So, there will be a flow inside. So, all these important considerations needs to be taken into account if we want to solve this full problem, right. Okay. So, given that introduction, let us look at some of the interesting features, okay, of this now, okay, and some of the data that comes from our group, was essentially from my group. So, I can share a few data with you, okay. Like for example, as I said, we have assumed that the droplets are normally very spherical. That is true in some of the cases, right. In some of the cases it is not, okay. So, you get this catastrophic shapes, right, got it. So, this you cannot tell that it is spherical, this is non-spherical, right. So, this becomes a problem in which the interface is not very well defined, right. So, so there are situations like hydrodynamic, thermal and shear instabilities, okay, that leads to configurations like this, right, but we will come to that later, okay. So, there may be also temperature and concentration species profile within the droplet because of internal recirculation, right. So, as you can see in this particular configuration, okay, the species profile is not very symmetric, right, it is shows that kind of a behavior, isn't that so? That happens because there is a flow that is generated inside the droplet, okay. Forget about this for the time being, this is if you have particle matter within the droplet, how do they accumulate, okay. One other interesting thing, so these are some of the examples where you can see that why the droplet is very useful, okay. Now, one other interesting thing that will come after this one, that most of the time people assume that there is something called a spherically symmetric model, right. What is a spherically symmetric model? Spherically symmetric model is that a model of a droplet which is actually vaporizing into a quiescent ambient where there is no flow, okay. So, the droplet is nice and easy sitting over there, there is no flow. So, if you are considering flow around the droplet, there are no such flow, right, and it is isotropically actually vaporizing inside a quiescent environment. This particular thing is very hard to achieve because normally even your room, okay, at this condition actually has a flow, Okay, if you put an anemometer or a pitot tube over here, you will detect a flow, and that flow is not very trivial. Okay. So, by spherically symmetric model, we mean that the droplet is vaporizing in a spherically symmetric fashion, where there are no flow effects. When there is flow, the symmetry is usually destroyed, as we will show in the next one. If there is something like a buoyancy, or if there is something like an external flow, you can see what happens within the droplet. This is basically the outer flow streamlines. Okay, streamlines of the outer flow. You can see that there is a flow separation that happens at the back of the droplet. This is very common. If you guys have done fluid mechanics, you know that behind a cylindrical or a spherical obstacle, there is always a flow separation. The similar thing happens within the droplet also. In addition, however, you can see that there are recirculating flows that are created within the droplet, right? Okay. Similarly, okay, so you can have another situation in which the flow is very high, probably like a little bit of a high velocity flow, and you have basically two recirculation zones, right? So, we are not considering these two at all in a spherically symmetric analysis, right, because there is strong flow inside the droplet, whatever the nature of that flow may be. Okay. It can be buoyancy driven flow, it can be imposed flow. So, it can be natural internal recirculation, it can be imposed recirculation due to the gas phase velocity. Got it? Okay. So, that part is very important. Okay. We will look at this a little bit later. Now, if we want to solve this equation along with combustion, okay, and this is not to basically scare people away. Okay. So, basically this is the droplet, this is where the combustion front is, basically what we call the flame, and this is basically the gas phase flow field, right. Okay. Now, you can see it is a multi-component molecular diffusion. When you have combustion, you have complicated kinetics, the chemical kinetics is extremely complicated. So, you can have as much as 50 species, okay, 250 reactions, sometimes even more. Okay. There will be non-luminous thermal radiation, there will be UV emission. So, you have to solve for all those things. Okay. So, you have a mass conservation, you have multiple species conservation equation that you need to solve, and you need to solve it for both phases. That is the interesting part, right. Okay. Then you have the energy conservation equation, and from the droplet surface you have to take into account the surface regression, the evaporation, condensation, radiative heat addition. In the droplet interior you have to solve all these equations, right. So, it becomes a framework and all these equations will be coupled with each other based on the interface conditions. They will be all matched at the interface, the solutions have to match at the interface, right, and they have to physically make sense also, right. So, this is a very onerous job, as you can understand, right. There are a lot of reactions floating around, there are a lot of things that you need to solve, there is gas phase, there is liquid phase and all these things. Okay. So, how, but fortunately the spherically symmetric assumption offers a very good tool, right. It offers a solution without much of a headache, right. So, before we go there, and we will emphasize on something called a d square law, and then we will try to prove that how it actually comes. Now, some people, some researchers actually did some experiments, right, using this kind of a droplet, and what they did was that they suspended a droplet. Okay, they maintained it probably in a box or something where there is no flow. So, no flow, got it. Okay, and it is quiescent. So, the spherically symmetric assumption can be applied. When they did the measurement and when they normalized the droplet diameter by the initial droplet diameter square, right, and here you are plotting something like delta t by d naught square, right. Forget about that time scale, that is not important as of now. Okay. So, the important part is that d by d naught square. Okay. So, when they divided the instantaneous droplet diameter with the initial diameter of the droplet, so what they basically did was that perhaps they took a camera, okay, and they basically monitored how this droplet is actually evaporating. So, they were basically calculating the droplet diameter at each time instant, okay, and after they were done with that, okay, they squared the diameter and they divided it by the initial diameter square, right, and they plotted it. What they saw was something, so it will be always 1 to 0, right, because the droplet will always shrink, and this is a evaporation case, let us not consider condensation, okay, and they saw that they got a straight line, a linear line, right. They got a linear, no matter what fuel they did with, okay, they always got a linear profile, So, this linearity of the profile suggests basically that with time, okay, there is a constant slope. So, this means that d by d naught square, okay, will be basically some kind of a constant slope, some kind of a constant slope kt, right, no matter what happens with how you normalize time. So, it shows that there is a constant slope always. The slope value can vary depending on what droplet you are dealing with, but they got a constant slope, right, no matter which droplet they actually dealt with. Okay. So, this was actually proposed in the famous d square law, okay, d square law by Law and Scirinniano. Okay. So, they actually proposed that there will be something like a d square law which the droplet has to obey, okay, in the case of this quiescent spherically symmetric evaporation. Okay. Now, what is the prelude to that d square law? Okay. So, first and foremost, it is spherically symmetric. Okay. Forced and natural convections are neglected, not just neglected, they are assumed to be negligible, right. So, this reduction leads to a one dimensional analysis, okay, because there is no flow, there is no spray effect. That means there is one droplet is isolated and it is all by itself in an infinite environment, there is no other droplet that is present. So, it is very restrictive, right. Diffusion is the rate controlling parameter. That means the liquid does not move relative to the droplet center. That means there is no internal motion of the liquid, got it. The surface regresses into the liquid as evaporation happens. That means the surface slowly shrinks, right. That is common, right, a droplet should shrink. Okay. Therefore, heat and mass transfer in the liquid occurs only because of diffusion with a moving boundary, but not convection. Got it. So, there are no convection effect, it is basically a diffusion problem. There is no flow inside the droplet, outside the droplet, okay. There is heat and mass transfer only due to diffusion with a moving boundary. So, it is a slowly shrinking droplet, okay, where there is no flow, okay, and it is an isobaric process, it is a constant pressure process. So, we are not varying the pressure, constant gas phase properties, okay. That is because the gas phase properties, if for example due to evaporation or during the time of evaporation, during temperature changes, if the specific heat, thermal conductivity, diffusion coefficients, density, etc. varies, you will have a different problem. So, we are assuming that is a constant property. Now, the sixth assumption is the most important one. It says gas phase quasi steadiness. What is quasi steady? Steady means steady, that means there is no temporal derivative. If you take a temporal derivative, it will come out to be 0. Quasi steadiness actually means it is steady with respect to certain time scales, right. So, because there is a significant disparity between the liquid and the gas, usually that is the case, it is of the order of 1000, right. Liquid properties at the droplet surface, okay, at the droplet surface changes at a rate much slower than the gas phase transport processes, okay. This assumption actually breaks down far away from the droplet surface, we will see when it breaks down, but the liquid properties at the droplet surface, that is the regression rate, shrinking of the droplet, the temperature and the species concentration, if there is a multi-component thing, changes at a rate which is much lower than the gas phase transport processes. So, that means the gas phase changes so fast, right, that the liquid is almost seeing a steady gas phase outside. It is not able to detect what is going on in the gas phase because its own movement is very slow, right. So, that is one of the key important parameter, that the gas phase with respect to the droplet is actually a quasi steady thing, okay. This will happen if there is a very fast process that is going on, and if you are very slow, then you would almost see like a steady thing. This happens everywhere, like for example with your human eye, right, with a human eye. In some cases, if I change something very quickly, okay, you may not be able to see that the difference, the subtle difference. So, why that happens? Because I am actually not able to respond that fast, right. So, if my response time is slow and the gas phase response time is very fast, then of course, you will see the gas phase almost like a quasi steady kind of a situation, okay. Now, the gas phase quasi steady, let us look at some of the characteristic time scale analysis, right. Now, in a standard environment where there is a gas phase heat and mass diffusivities, like for example, so the gas phase heat diffusivity is alpha g, mass diffusivity is say delta g, okay. They are usually of the same order, right. They are usually of the same order, which is roughly given as 10 to the power of 0 centimeter square second inverse, right. Okay. A typical example is a Lewis number equal to 1 kind of a situation, right. Okay. Now, the droplet regression rate is of the order of this 10 to the power of minus 3 centimeter square plus second inverse. Okay. That the droplet from the experimental data, if you consider that how it vaporizes, this is the rate of regression, surface regression, right, how the droplet diameter is shrinking, right. That happens in the order of 10 to the power of minus 3 centimeter inverse second. Okay. This happens actually in a time scale of 10 to the power of 0, right. This is for conventional hydrocarbon fuels evaporating in the atmosphere, right. So, that the ratio of the same order of liquid to gas densities, okay, that is, this is liquid, this is gas, okay. If you divide these two things like the mass diffusivity divided by the regression rate, it means essentially that the gas mass and heat diffusion occurs much faster than the droplet regression time, got it. So, the mass diffusion, the mass transfer that is happening from the droplet surface, okay, is happening at a much faster time scale compared to the regression, and these ratios will actually show you, one is 10 to the power of minus 3, one is 10 to the power of minus 10 to the power of 0, right, and alpha and delta are basically the diffusive time scales, right. So, it essentially means that when you have a disparate density difference like this thing, rho liquid by rho g, you can readily see over here, okay, because this is of the order of 1000, there is this is also of the order of 1000, right, which is very clear from over here. This is of the order of 1000, isn't that so? Okay. So, it essentially means that the diffusion process is very fast compared to the regression or the surface regression. Okay. So, thus the gas phase processes can be assumed to be steady, okay, time independent, because the surface almost freezes during that period, the surface does not see anything else, okay, with the boundary variations occurring at much longer scales. Now, the question then actually remains that what value of this d, that means the separation distance, right, this assumption actually breaks down. That means when the diffusion time is equal to the surface regression time, right. So, when the surface regression time becomes equal to the gas phase heat and mass diffusion time, that means this particular relationship when it is actually valid, right. So, d naught square by k will be equal to what value of d, okay, what value of the diffusion length, right, for which these two time scales will be the same, remembering that these two is of the order of 1000 always, right. So, once you do that, you will find that this d infinity is actually 32 times the droplet diameter, okay. So, that means if your distance is less than that, okay, you are okay. You can assume this gas phase quasi steadiness, but if you are far away, right, then of course this will not be valid, got it. So, it is 32 times the droplet diameter, at that particular distance you can actually have this thing breaking down. That means you cannot apply gas quasi steadiness at that kind of a distance, right, which is 32 diameters away from the droplet, okay, which makes kind of sense, right, because this is basically the scale at which the droplet surface actually regresses. This is the scale at which the vapor will travel to that kind of a distance. This d infinity is basically a distance, right. So, so long the distance is small comparable with the droplet diameter, okay, this assumption is still valid, right. That means your quasi steadiness is valid. However, if the distance becomes very large, that means you are trying to compare whether a point which is 32 diameters away from the droplet is actually quasi steady or not, then that particular assumption is not valid, got it. Okay. So, that is roughly a rough figure 32 diameters. So, that means our model will be valid for less than that, right. So, this d square law is very powerful, but it comes with its own caveats, that these are the assumptions that we have stated and we have assumed that it is a liquid vapor. Of course, if this difference between the densities of the liquid and the gas, if they are very small, okay, very small, Okay, like for example, if you go to supercritical type of cases, okay, so that could be very small. Okay, so in that particular cases, you cannot assume actually quasi steadiness. Okay, so be prepared to understand what assumptions and why they are applied and why it is valid. That is an important part of this argument. Okay, so as some of the additional assumptions are that you have to assume a single fuel species or whatever species that you are assuming is a constant and uniform temperature, droplet surface temperature. That means there is no spatial variation of the droplet surface temperature, there is no temporal variation of the droplet surface temperature as well. Okay, and it is basically a gas phase model. We won't do anything to the liquid phase. Okay, it is basically a gas phase model. So as you will find when I do the modeling, it will be just a gas phase model, and we will do something to the liquid phase, but not that much. The saturation vapor pressure exists at the droplet surface. Okay, that means the vaporization happens through the obeying the Clausius-Clapeyron type of equation. Okay, so the evaporation at the surface is always at a thermodynamic equilibrium. Okay, so it produces the vapor which is at a saturation pressure corresponding to the droplet surface temperature. Okay, so it is not that fast a process also, that the evaporation is always in a nice thermodynamic equilibrium state. Okay, so it is not away from equilibrium. Okay, and then there is no effect like Soret and Dufour. These effects basically comes due to the second order effects. These are all second order effects, so these are neglected, usually they are, and the radiation effects also are neglected. Got it? So these are the 10 assumptions basically, okay, that goes into the making of the d square law, which is experimentally people have validated, right. But however, I did not do the math as of now, so the math will be done in the next few slides or the next few journals entries, but I want you to kind of understand before we go to the next lecture, okay, to state that the d square law is valid experimentally. People have seen it, right. And in order to apply it mathematically, there are a set of assumptions that we have said. Two principal assumptions are that there is a gas phase quasi steadiness, that is very, very important, right. The liquid phase does not feel any flow, does not feel anything, essentially it just vaporizes. The saturation vapor pressure exists, so it is a thermodynamically equilibrium process always. That is how the liquid is going into the vapor phase. There are no second order effects. Okay, forget about second order effects, that may be important in some specific applications, not for this. Okay, and you have a constant and uniform surface temperature, right. So whatever heat that you are supplying to the droplet basically goes towards the latent heat. Okay, and of course there is no spatial change in temperature, that is because it is a spherically symmetric case, right. So there is no temperature gradient also, okay, within the droplet as such. Okay, so so when there is no gradient within the droplet, can you imagine what that is called? So when you are dumping heat to the droplet there is no internal temperature variation within the droplet, not with time but with space, right. Why is that? That happens because the droplet has got a very high value of thermal conductivity, right. So when the droplet has got a very high value of thermal conductivity, it is called basically an infinite conductivity approximation. That means whatever heat that you are supplying is only during the initial phase, the droplet surface, the droplet core versus the droplet surface does not see any temperature gradient. Okay, so the heat is instantaneously conducted, right. Now if this temperature does not vary with time also, then that means that whatever heat now you are supplying to the droplet is basically going towards heating or evaporating the solvent, right. So these are the few assumptions that will come. This is an important assumption, and once we do the math we will see that what is the implication of this particular assumption. Take a look. So remember the constraints, that what are the time scale analyses that we did, okay, and remember another important thing is that the diffusion is a rate controlling step. Okay, there is no convection effect at all, and constant properties and other things are fairly obvious, so we should not be bothered about that. Okay, so what we do is that we finish this lecture over here, we will then start and derive this d square law from first principles, right, and show that why it should come constant. basically match the experiments. Okay, and there once we write the equations, you will see that we will write only gas phase equations, mostly gas phase equations with some limiting boundary conditions. Okay, so it will be better if we do it in the next class and complete the droplet spherically symmetric, then we will move to more complicated cases. Okay, thank you.
Swayam Prabha. Digital India. Educated India.
Previous lectures we have been dealing with one kind of common fault in rotating machinery, that is unbalance. Apart from this unbalance, there are several other faults which may appear in rotating machinery, and those obviously reflect in the vibration signature, because whatever the dynamics is taking place inside the machine, that reflects as a vibration, and if we measure the vibration onto the machine body or any other component, then we can able to have some idea about the condition of the that particular machine component. So in the today's lecture we will be dealing with various kind of common fault in the rotating machinery and how it affects the vibration signature, and we'll try to analyze these vibration signatures. Are there in time domain, generally we captured through some sensor, and then we are generally these whatever the signal comes in analog form, then we convert into the digital form using analog to digital converter, so that we can able to store the data in computer, and then we can able to do the post processing of those data. Either we can convert the time domain data into frequency domain or any other domain in which these signals can be interpreted. So we'll start the introduction to this particular topic. So it is very important to display the measured signal in convenient form, so as to be useful for the interpretation of the condition of the rotating machinery. As I mentioned, the measured signal we need to display in a convenient form, which will be useful for the finding the condition of the rotating machinery. As we will go into the deep into the lecture, we will find how these signals can give condition of rotating machinery. So looking at various forms of measured signal, possible condition of machine is provided. It also looks into the correlation of a particular signature or the vibration signature with a particular failure in more detail. Every fault has a specific signature in the measured signal, and it is most convenient and cheapest way to identify possible fault in machinery. Now, very advanced signal processing techniques like wavelet transform, neural network, fuzzy logic, genetic algorithm, genetic programming, machine support factor (SVM) are being applied in vibration signals of laboratory test setup to detect, locate and quantify the faults. So not only the detection of the fault, now with these techniques we can able to pinpoint where is the fault, and even we can able to quantify the fault, and based on this even the life of the machinery is also being predicted. How much we can able to run the machine without much danger. So detailed treatment of these newly emerging methods is beyond the scope of the present lecture, but mainly we will be focusing on based on signature based on the vibration signature, we will try to correlate various kind of faults in the present lecture. So, vibration based identification of fault such as rotor unbalance, rotor bends, cracks, rubs, misalignment, fluid induced instability based on the qualitative understanding of measured data is well developed and widely used in practice. So, even this is being applied in actual machinery in industry also. However, the quantitative part, the estimation of the event of fault or the extent of the fault and their location has been an active research for many years. So, qualitative we can able to detect the fault, but quantifying that is still a research area. Over the past 3 to 4 decades, theoretical models have played an increasing role in the rapid resolution of problems in rotating machinery. So, the most common fault which we already seen is the unbalance. So, let us see slightly more detail on this. So, in any rotating machinery, the rotor unbalance is always present, and it is one of the most common source of severe vibration in rotating machinery. When a severely unbalanced rotor is rotated freely on frictionless bearing, it stops at nearly fixed orientation. So, this is nothing but the static balancing of the rotor. It indicates that the gravity force acting at the center of the gravity pulls the rotor to a fixed orientation due to its eccentricity. So, this we already discussed regarding the static balancing of a practical rotor, how we can able to do it. So, there are two terminology. One is the position of the unbalance, that is we call it as heavy or hot spot. This position is always remain fixed onto the shaft. The point on an unbalanced rotating shaft with the maximum displacement is called the high spot. So, that is heavy spot, and high spot is the where the maximum displacement of the rotor take place in the axial position of the rotor, and this point is variable and depends upon the speed of rotor, and it is observed by vibration pickup or sensor as a point of maximum positive displacement or amplitude of vibration. And because once we are rotating the rotor in the flexible mode, we know that this high spot may change. So, that is why it is depend upon the this particular speed. So, this is a typical unbalanced response. This is the, you can able to see there are two critical speeds of the rotor. This is the phase plot. So, phase is also changing wherever there is a peak. So, this is another way of identifying where are the critical speed. This is the orbit of the shaft. That means, in vertical direction and horizontal direction, displacement can be plotted like this, and we can able to see even in some instrument we can able to see the sense of rotation of the this particular orbit using a z direction. Even in some oscilloscope we can able to see this particular orbit, the sense of rotation also, and using a third axis. So, x and y, and another axis that is z axis. In that we can able to introduce a reference signal, and with the help of that we can able to show the sense of the this orbit also. So, this is below the critical speed, but so critical speeds are there, you can able to see. So, 200 rpm is below the first critical speed. So, sense of rotation is in this particular case counterclockwise direction, but if we are between two critical speed, the sense of rotation is changed, or it is clockwise, and if we cross the second critical speed, again it rotates in the counterclockwise direction. So, this also indicates how in which region of the critical speed range we are there. Even the shape of the orbit helps us in understanding the especially what kind of fault may come into the rotating machinery. So, as we will see in the subsequent slides, that the shape also gives indication of incipient fault in the rotating machinery. So, the high and heavy spots may or may not coincide depending upon whether the rotor is operating relative to the critical speed. So, in a Jeffcott rotor, the example which I showed in the previous slide, it is observed that the high and heavy spot coincide below the critical speed and they are opposite above the critical speed. At critical speed, they have a 90-degree phase with heavy spot. These kind of phase we already seen in very beginning of these lectures when we considered the Jeffcott rotor. In some instances, the magnitude and the phase of the unbalanced vibration vector might change with time. When symptom of unbalance exhibit this feature, the correct treatment is not normally to simply rebalance the machine. So, if magnitude and phase of the unbalanced vibration is changing with time, then there is not a balancing problem. That is a different problem. The example of fault in such category are the heavy spot on the shaft causing a thermal bow. It occurs when the heavy rotors of turbine are left non-rotated for cooling during shutdown, and due to heavy sag, it get permanent bent configuration, or even when the rotor has axial asymmetry of the thermal distortion. So, because of this, we may find that the response may change over period of time. Components mounted loosely on shaft like discs, gear, flywheel, etc. If that is the case, then also we find this particular kind of behavior in the response. Moisture entering in a hollow shaft, which vary in amount and location during the operation of the machinery. So, this is another potential cause of that we may find that the response may change over time. Now, coming to the unbalance, we already seen how the procedure how to balance a rotor. So, this is a typical rotor in which there is a motor, the bearings are there here, this is a fluid film bearing and this is a bush bearing, this is a 2 discs and this is mounted on flexible shaft. There are provision to measure the vibrations at several locations. So, we can able to use proximity displacement probes to measure the displacement. So, you can able to see this is the shaft, these are the proximity probes. So, there is a gap between the shaft and the probe, and when gap changes, it produces the current proportional to that, and we can able to measure the displacement. This is a fluid film bearing in which we can able to measure the pressure also at various locations. And this is a disc, and you can in this particular disc you can able to see there are threaded holes in which we can able to put some kind of screw, so that we can put some kind of trial mass in this. So, basically we can call this as a perturbator disc. Now, this is a typical response. So, this is without unbalance. So, you can able to see this is a response of the rotor. This has been filtered at the rotational speed of the rotor. That is why it is so perfectly sinusoidal in nature. This is a reference signal which we generally keep at keyway onto the shaft, or by putting some kind of tape, photo reflecting tape. So, these spikes helps us in finding the phase of this with respect to this reference signal. So, it has been balanced by the procedure described earlier, and now you can able to see after putting the correction mass, again we measured the displacement, and you can able to see compare this drastic decrease in the amplitude of the vibration took place after balancing. Next category of the fault is the shaft bow or thermal bow, as we have seen in the previous discussion. These bows in shafts may caused in several ways. For example, due to creep, thermal distortion, or a previously large unbalanced force. The forcing caused by a shaft bow is similar or slightly different to that caused by conventional mass unbalance. The bow and the eccentricity are in general in different angular location, and warped rotor behaves somewhat differently from purely unbalanced rotor. So unbalanced and the bent rotor, they have slightly different behavior. Both shaft response is independent of the shaft speed. This is very important to observe. This particular thing is independent of the speed of the shaft and causes different amplitude and phase angle relationship then is found with the ordinary mass unbalance, where the forcing is proportional to the square of the speed, because we know for unbalance the force is proportional to the square of the speed, but for the boat shaft it is not the case. Boat shaft gives rise to synchronous excitation as with the as the mass unbalance, and the relative phase between the bent and the unbalance causes different changes of phase angle through resonance then would be seen in the pure unbalanced case. So this is a typical a test rig in which the bearing blocks are there and there is a shaft, and we can able to introduce a bow in this particular shaft. That means permanent bend we can able to introduce, and we can able to rotate this shaft by some motor, and then we can able to measure the vibrations at some location onto the shaft. And this is a particular these vibration have been measured at the bearing block through accelerometer. So now you can able to see in this, basically this is a horizontal and vertical response. This is in the frequency domain. From 0 to 200 hertz is the frequency span in this, and this is the amplitude of vibration. This is in horizontal and this is in the vertical direction, and this is without any bow into the shaft. At one particular speed, 1000 rpm, it has been rotated. Now you can able to see this is corresponding to the 1x, that is corresponding to the rotating speed of the shaft. This is also corresponding to the rotating speed of the shaft. Speed is 1000 rpm, which is relatively low, and this is the response when we introduce the bend into the shaft, and we are measuring the vibration from the bearing housing. At the same speed we are operating as this one, and in this we can able to see there is still those peaks are there, but the amplitudes are different. You can able to see here is 9.2 but is 15.0. So amplitudes are different, and but not much appreciable amount of difference was found between these two responses for slow speed of operation. So this I discussed. This is the same experiment with slightly higher speed at 5000 rpm. This has been taken from SpectraQuest case studies. In this you can able to see that this is the corresponding to the rotational speed of the shaft. This is in the horizontal direction, vertical direction. This is a baseline, that means without bend, and this with bend. And with bend we can able to see there is a change in the amplitude of vibration. Now quite drastic change in the amplitude of vibration at the rotational speed frequency we observed. So in this a careful inspection of the previous two figures indicate that the amplitude 1x, that is rotational speed, has a significant increase both in the horizontal and vertical directions. They increase 3 to 4 times respectively. The experimental results indicate that for low speed the effect of bend shaft on bearing vibration can be neglected. Under high speed 5000 rpm, a center bent shaft, the bend was there at the center of the shaft, will increase 1x of the bearing vibration. So we are measuring the vibration at bearing. So it has been observed in the previous figures that for high speed the bent shaft is having significant effect onto the 1x component of the vibration. Next fault is the misalignment. Unbalance and misalignment are the two most common source of vibration in the machinery. Objective of the alignment is to have two coupled shaft perfectly collinear under operating condition, or between the bearing and the shaft their axis should be collinear, or the two bearing carrying a common shaft should have their axis collinear. So, these are the condition is the perfect alignment, but if it deviates then we will be having misalignment in the system, in the rotating components. So, accordingly misalignment can be classified as parallel, angular, or combination of parallel and angular misalignments. So, this we can able to see here. There are two shafts, rigid shafts, and they are offset by some amount. So, this is parallel, this shaft axes are parallel, but they are offset. So, this is a parallel misalignment. Then another is in which two shafts are having some inclination. So, this is a angular misalignment, but there is no parallel offset. And third is the combination of both parallel as well as angular. So, in this both the parallel and angular misalignments are present. So, we can able to expect that there will be large forces which will be coming out of the bearing because of this misalignment, and that will reflect in the vibration signatures. Like the unbalance, the misalignment is an installation, and again I am repeating this. Like the unbalance, the misalignment is an installation and subsequent maintenance problem, since it can be corrected and prevented by using the proper installation and maintenance procedures. The vibration associated with misalignment occur at one machine running speed, but unlike unbalanced case, there is a usually substantial component in the axial direction which may be greater than the radial direction. So, apart from the radial vibration, we can have axial vibration in this particular case when the misalignment is present, which is not there in the case of unbalance. In unbalance, only pure radial vibrations will take place. Substantial amount of misalignment or the preload can also cause vibrations at frequencies of two machine running frequency, twice of the machine running speed, and sometimes higher multiples also, 3, 4 also. So, this is a typical cascade plot with shaft misalignment. So, this is the vibration frequency, this is the shaft running frequency. So, you can able to see this is the 1x. So, amplitudes are present in this. Even in 2x machine, some of the peaks are present as we are increasing the speed. 3x few are there. So, this kind of behavior we can able to get when the misalignment is present in the system. So, this is the Lissajous plot for different level of misalignment. For moderate misalignment, we will be having elliptical shape of the orbit, or the Lissajous plot, which is nothing but the x and y plot as we have shown earlier. But for heavier misalignment, we have banana shape, or for very severe misalignment, we will be having shape of 8 or maybe multiple loops we may find because of severe misalignment. So, by looking into the these plots, we can able to pinpoint that whether the rotor system is having some kind of misalignment, and what is the degree of misalignment we can able to identify with this. Now, we will take up one case study, which is of a stone crusher unit in a cement plant. So, in this this is a typical industrial stone crusher. Basically, here motor is there, drive is there, then this is the coupling unit which we can able to see it, and then in this side there was one crusher unit in which the stones used to crush from bigger size to smaller size, and in this particular case they had a lot of problem of the vibration. Basically, this whole unit was mounted on a platform, and so basically it was in the first floor kind of thing. So, if we see from bottom, so this was the support to mount that machinery at the top, and they had a lot of vibration in this order of vibration was very large, and because of that, even in the columns, so whatever the this kind of columns, they had the cracks in the columns, and the machine was in a very bad condition, and they were not knowing what is the actual cause of such vibration. So we took measurement of that particular vibration, and then after 1 week of that, there was total shutdown of the plant, and this is the typical gearbox they took out and try to find out where is the failure of the machine took place. So basically at the rear end of this gearbox, this is a spline shaft which connects the this particular gearbox to the store rollers. So this spline shaft is shown here in more close view of that. So that spline shaft has had crack, and this is the crack which is very severe crack is present in this, and this was after the measurement we took. So that was after 1 week this happened, and this is a typical vibration measurement which we took prior to the failure. In this we could able to find out some of the frequencies which were natural frequency of the system, because in several plots they were appearing and disappearing. So whenever there was excitation close to this, they were appearing, and otherwise it was not appearing. The gear mesh frequency, one of them was here. This was a typical low frequency peak which was otherwise should not have been present, and we found this was because of the misalignment between the spline shaft and the roller shaft, and that misalignment, when we calculated because the speed of that was very low, and this is the typical misalignment behavior we could able to identify from this vibration signature. So this is a typical case study on the misalignment, how we can able to find out through vibration signature directly. Next kind of fault is the stator rotor rubs. So when the rotor touches the stator, there will be rub, and this may reflect in the vibration signal. So rubs are produced when the rotating shafts comes into contact with the stationary component of the machine. Rubs are said to accompanied by a great deal of high frequency spectral activity. A rub is generally transient behavior is there. The rub may typically be caused by the mass unbalance, heavy mass unbalance, turbine or compression blade failure, defective bearing or seal, or the rotor misalignment, either thermal or mechanical. Several different physical events may occur during a period of contact between the rotor and the stator. The initial impending stage, frictional behavior between the two contacting parts, an increase in the stiffness of the rotating system while contact is maintained. The behavior of the system during this period is highly nonlinear and may be chaotic also in the nature. Some of the research have been reported that this may give a chaotic behavior of the system. The rotor to stator rub is one of the malfunctions occurring often in rotating machinery. It is usually a secondary phenomena resulting from other faults. So because of the other fault this comes, that's why it is a secondary phenomena. Rubs may be classified as a partial rub, full rub, or take a form of a stick slip action. A partial rub is that where contact between the shaft and the stationary component exists only for a part of the cycle. For example, the high spot on the shaft rubs against part of the seal, or a bored rotor rubs the stator. The flattened waveform and orbit are strong indication of the partial rub. So from the waveform we can able to identify whether rub is taking place if it is getting flattened. In the case of full rub, the shaft may may make contact with stationary member not only at local high spot, but instead bounce its way all around its orbit. For example, in case of severe misalignment or due to severe unbalance, which produces large unbalance response in the rotor. The main component is at 1x rotational speed. Harmonics and subharmonics may also be present in either the forward or backward directions because of the rub, full rub. This is a typical plot of the vibration which take place due to the rub. So, this is without rub, and with rub you can able to see various higher order components have appeared. So, this could be the indication of the rub in the rotor system. Mechanical looseness of component, this is another kind of fault which is which comes into the system because of the poor maintenance. So, mechanical looseness, the improper fitting between component parts is generally characterized by a long string of harmonics of running frequency with abnormally high amplitudes. In some machines, vibration levels may be excessive as a consequence of component being assembled too loosely. For example, in the case of bearing which is not properly secured, the vibration signal detected from a transducer is normally a sine wave, but is truncated at one extreme as shown in the figure. So, that means vibration signal should be sinusoidal, but sometimes we will see that at one extreme is getting flattened, and because of this looseness. So, a truncation of sine wave occurs because of non-unity of, for example, the bearing mount that suddenly becomes very stiff when the loose component reaches the limit of its allowable level. The frequency domain, in frequency domain, these truncation impulses show up as a series of harmonics of rotational frequency. So, if we see this particular signal in frequency domain, there will be a fundamental harmonics and then higher harmonics will be there. For this intact without looseness, we expect only single peak, but because of the truncation, now we will be having multiple harmonics of the signal will be present. Next common fault in the shaft, especially for where the high power transmission is there, that is the shaft cracks. The presence of various flaws such as cracks, notches, slits, etc. in any structure and machinery may lead to catastrophic failures. They are particularly likely to occur in instances where shaft stresses are high and where machines have endured many operation cycles throughout its life, so that material failure has occurred as a consequence of fatigue. In the shaft cracks, again I am repeating, if the shaft cracks can be detected before catastrophic failure occur, then the machine can be temporarily taken out of service and repaired before the situation gets out of hand. The presence of transverse shaft crack sometimes detected by monitoring change in the vibration characteristics of the machine. The shaft stiffness at the location of the crack is reduced by an amount depending upon the crack size. That is in turn affects the machine natural frequency, so that changes in the natural frequency may be that could be a symptom of the shaft crack, because crack introduces flexibility in the shaft that changes the stiffness, and natural frequency is nothing but root k by m. So, if stiffness changes, we expect there will be change in the natural frequency of the system. So, that could be one indication of the crack in the rotor system. But unfortunately, the changes in natural frequency may not occur until the crack has reached a dangerously large size. For this reason, most users for rotating machinery depend on changes in vibration amplitude, phase and frequency spectrum to detect shaft cracks rather than the change in natural frequency. A transverse crack or the breathing crack, sometimes we call it, in which continuously opening and closing of the crack take place during vibration, that results in significant change in both 1x and 2x vibration component. So not only 1x and 2x component are also present in this. So as I have shown earlier, this is a typical cracked shaft, but we measured the vibration at the housing of these, so that we could not able to locate this particular behavior in the vibration. But if we could have taken near to this shaft, we could have got some indication of the cracking in the shaft. Till now we have seen some of the very common fault in the rotating machinery. There are various components in the rotating machinery which do get failures, and like bearings and gears. So now we will take up a case of bearing faults, because in bearing we know there are various components and gears. So now we will take up a case of bearing faults, because in bearing fault, the primary example of characteristic associated with a specific component is the frequencies generated by the defects and flaw in the rolling element bearings. Faults in rolling element bearing may occur prematurely as a consequence of operating the bearing under appropriate loading condition, inappropriate loading condition, including misalignment and excessive speeds. Alternately, they may be produced simply as part of normal wear process during the life cycle of the bearing. Defects in the bearing may be developed on either raceway, on the rolling element or themselves, or on the cage. Subsequent vibrations are forced as a consequence of impact between the fault and the bearing components, so that the frequency of the resulting vibration is largely dependent on the frequency of impacting. For example, a defect in a bearing outer raceway would set up vibrations corresponding to the frequency with which rolling element passed over the defects. Consideration of bearing kinematics geometry enables calculation of these frequency associated with defects in different component of the bearing. So if we see the bearing, this is a deep groove ball bearing. So you can able to see this is a rolling element, outer raceway, inner raceway, and we can have a fault in any of these two, four components. This is the contact angle. This is the mean diameter of the bearing. This is a ball diameter. So based on geometry, we can able to calculate the outer raceway defect frequency like this, where Z is the number of rolling element, N is the speed of the shaft, and these are already defined. Similarly, inner race defect frequency can be given by this, rolling element defect frequency, cage defect frequency. So these frequency we can look into the vibration signal if we are monitoring a bearing. So even additionally, sum and difference frequencies may be apparent as a result of interaction or modulation between two or more characteristic frequencies. So even with the rotor speed and the other defect frequency, there can be sum and difference of the frequency may be present in the spectra because of the modulation. Such sum and difference frequency appear as a side bands of frequency peaks either side of the higher main frequency component of the signal. So side bands are nothing but frequency. There will be predominant peak, and either side of that there will be two smaller peaks. So that is called side bands. For example, let the carrier or the central frequency is omega c, the carrier signal is sine omega t, and the modulation frequency would be, let us say, omega m, and the modulation signal is some constant plus sine omega mt. Then multiplication of this can be written like this, and the sine omega ct and sine omega mt can be again rewritten like this. So you can able to see that basically we are getting the sum and the difference of the frequencies. So in general, side band frequency could be central frequency plus minus of the n times the modulated frequency. Some of the plots will be showing in the subsequent slides. A wear of the bearing progresses. As the wear of the bearing progresses, the frequency spectrum changes further. Sometimes higher order harmonics of the defect frequency becomes present, sometimes with their own sidebands and can dominate the spectrum. So, even the high frequency component can be there in the bearing fault. The micro irregularity of the bearing contacting surface give very high frequency component in the response. A popular method of monitoring rolling element bearing condition is the shock impulse method. The basic principle of this is the method depends upon the signal input to the measuring instrument like accelerometer being passed through a narrowband filter whose central frequency is corresponding to the accelerometer natural frequency. So, basically as the part of the bearing collides with the defect, a shock wave is transmitted through the bearing and the machine casing, thus exciting the accelerometer by means of a pulse input. And because the frequency is close to the accelerometer natural frequency, so we will get a very high amplitude of vibration. So, this is one case study for the bearing. So, the physics and the physics sorry. So, based on the geometry and the calculated frequency for the one of the machine fault simulator we have taken, in which the bearing was of this category and various parameters like number of rolling element, ball diameter, pitch diameter, contact angles are given here, and based on this specification. So, these are the specification of the bearing, and these are various frequency factors which we have obtained from the previous formula. So, only thing the speed is not there in this. So, whatever the formula we given, so if we remove the speed part and by 60, these are the factor are there. So, you can able to see FTF is that thing, but the cage defect frequency, BSF is ball defect frequency. Similarly, this is ball passing frequency for outer raceway and this for inner raceway. So, this is for outer raceway defect, this for inner raceway defect. So, these are the factors. So, if you multiply by the speed of the rotor, we will get what frequency will be coming because of these faults. So, at 10 hertz, if you are operating the rotor, so we can able to see a different kind of fault. These are the factors. So, we will be having the frequencies like this corresponding to the various faults, inner raceway, outer raceway, like that. Similarly, for 20 hertz we can able to calculate. So, basically the main purpose of this to find out where we should look into the signal, these frequencies. So, these are the various frequencies, these are the closest value corresponding to the calculated frequency of the faults. So, this is a typical signal in which the inner raceway defect is there. So, you can able to see that there is. So, in this experiment we had normal bearing and bearing with various kind of defects. So, we measured the signal with normal bearing and with various defects, and we plotted in the frequency domain. So, this particular peak you can able to see is corresponding to the inner race fault frequency, and which is very close to the calculated ones. Similarly, this is for the outer raceway ball, outer raceway fault frequency, and so this is very predominant, and the value which we calculated earlier is close to this, and based on the speed of the rotor they may change as we have seen in the previous calculation. Similarly, this is for the rolling element fault at 10 hertz. So, some spike we can able to see. So, if we have baseline signal in which there is no fault, and if suddenly such peak comes, then we can able to pinpoint what kind of fault is there in the bearing. So, this is when combined fault is there. So, you can able to see outer raceway, inner raceway, and all kind of faults, ball fault is there. All we can able to see when simultaneously all faults are there in the bearing. So, that will reflect in the vibration signal, all the frequencies. Now, we will take up another machine element, that is gear, in which we can have several kind of fault. So, one typical case study will be taking up after a brief description of the gears, in which what kind of frequency it can produce in the vibration signal. So, the forces in the fault in the gear, the forces generated at gears are finally transmitted through the bearing, to the base of or the foundation. Thus, vibration measurement taken at the bearing can also indicate the condition of the gearbox. So, finally, whatever the dynamics is taking place at the gear will reflect at the bearing location, and if you are measuring the vibration there, it will give the condition of the gear also. So, gears typically generate a complex broad vibration spectrum beginning with frequencies well below the shaft rotational speed and extending to the several multiples of the gear mesh frequency. Gear mesh frequency is nothing but the number of gear teeth times the shaft speed. So, the amplitude of mesh frequency may vary greatly from gear to gear depending upon the number of teeth, gear ratio, tooth surface finish and load. As a general rule, the amplitude of mesh frequency will be smaller with a larger number of teeth, lower gear ratio, high quality of gear finish and lower load applied to the gear. A narrow band spectrum analyzer is very useful for this purpose because the monitoring processes involve the detection of discrete frequency component that must be distinguished from frequencies generated through other mechanisms like rolling element bearing. So, the natural frequency of geared shaft and the gear mesh frequency may have accompanying the side bands. Sometimes side bands themselves may have main indicator of the defective gearbox. So, if there are side bands in the near to the gear mesh frequency, then we can have the fault in the gearbox. So, this is a typical spectrum for a healthy pinion with indication of the mesh frequency and its sideband at no load condition. So, you can able to see that there is a mesh frequency for a typical gear and this kind of sideband. So, only one side is there, but if severity of the fault is more, then we can have sidebands on other side of this main particular frequency. And this mesh frequency will be there always, but if there is fault, then the amplitude of this will increase. This is a typical time domain signal. Generally, time domain signal is very difficult to analyze, but in this particular case, the signal in time domain for one chipped tooth pinion. So, one tooth has been chipped or removed, and in that obviously we will be having impact. So, whenever there will be that particular teeth will appear during the meshing, there will be impulse, and you can able to see there are impulses which are there, that is indicating that the one tooth has been chipped off, and this could be indication of which one tooth has been chipped. We can have a baseline signal, and we can able to compare with that. These impulses may not be present in a healthy gear. So, in the today's lecture, we have seen various kind of fault, and without going too much into the mathematics, we directly try to see these kind of faults, how they can be detected, especially through vibration signatures in frequency domain. We took up various kind of fault like unbalanced, bowed shaft, bent shaft, even the rubs, gears, bearings, and we have seen that each of these machine elements or this kind of faults, they have some unique frequency which they give, which they reflect in the vibration signal. And as a maintenance engineer, obviously we need to look into these frequency continuously, and if they appear suddenly, then we should able to pinpoint where the fault is appearing or where the fault is starting to grow before the failure of the whole machinery may take place. In the subsequent lecture, now we will be extending the similar concept of the condition monitoring, but we will be giving more broader view of the condition based condition monitoring, in which we will be looking into the various techniques which are available at present and what are the research people are doing on that particular topic. So, just we will try to brief them in the next lecture.
I am A.K. Sharma and I am professor of sociology at IIT Kanpur. The question I am going to address is what is urbanization? Urbanization is essentially the process of population concentration, which means that if more people start living in a smaller number of places, or if the distribution of population becomes more unequal, like more people living in places like Bombay, Calcutta, Mexico, then we say that the urbanization is taking place. Essentially it means increase in percentage of population living in areas or localities which are defined as urban. Urbanization is a new phenomenon, of course, a post-industrial phenomenon. About 200 years ago, hardly 5% population of the world lived in urban areas, and today more than 50% population of the world is living in urban areas or localities which are classified as urban. You will be happy to know that according to 2011 census of India, in our own country for the first time, increase in the urban population has been greater than the increase in the rural population. Though India is not so urban as the developed countries, and about 31% population of India only is living in urban areas. We can believe that in 10 years, 20 years, 30 years time, India will also be more urban, at least more urban than what it is. It may not be 80%, but certainly it will be 35% or 40%. Now, how is this urban locality defined? Because this definition of locality as urban or rural is crucial to measure level of urbanization. I will give you definition of our own country. In Indian census, an urban locality is defined in two ways. There are statutory towns and there are census towns. All places with municipality, municipal corporation, cantonment or notified town area committees are called urban. This is statutory definition. According to demographic definition, there are three main criteria. If a locality has more than 5,000 people, or 75% of male labor force is engaged in non-agricultural activities, or the density of population is 400 per square kilometer or 1000 per square mile, then we say that the locality may be classified as urban. There are many other additions to this definition. Now we have the concept of urban agglomeration and many other things, but essentially this is how urban population is defined in India. And as I said that urbanization is associated with economic development and industrialization, same is the case with India. About 100 years ago in India only 11% people were living in urban areas, today 31% are living in urban areas, and this is obviously linked with economic development of the country, growth of per capita income and industrialization. I remember that in one 5-year plan it was mentioned that today this urban population can grow by way of natural increase of births minus deaths in the urban areas itself or through rural to urban migration. Today nearly 60% contribution to growth of urban population is due to rural to urban migration, and this is going to increase. This is essentially what urbanization means. Urbanization means growth of population in localities defined as urban in relation to population of localities defined as rural, and I have given you Indian definition. Thank you very much.
When Copernicus said the earth revolves round the sun, it was considered blasphemy. When Galileo said the earth was round, we thought he was mad. When Darwin said that monkeys are the ancestors of man, we thought he had lost it. When the ecologists said this was the end of the world and the human race, we didn't believe them.
Swayam Prabha. Digital India. Educated India.
Hello and welcome. Let us now start with our introductory lecture on B-spline segments or curves. This is lecture number 19. Here we'll talk about polynomial splines in general. But first, why B-splines? Rather, why an alternative approach or method to design curves? Let's look at some composite curve models that we had discussed previously. First, composite Ferguson curves. For C1 composite Ferguson curve, the model is naturally continuous at junction points. However, to specify the first order or slope information is not very intuitive from the designer's perspective. And this is true especially in three-dimensional case. To specify individual components, the x, y, and z components of slope is not very straightforward for a designer. For C2 composite Ferguson curves, the slope information is required at only two endpoints. All the intermediate slopes will get computed due to C2 continuity conditions. However, there is no local shape control for the entire curve. In fact, C1 composite Ferguson curves can be locally controlled in shape. In case of composite Bezier curves that we had recently studied, once again, individual segments constituting a composite Bezier curve do not have local control. Position of data points of these subsequent segments are constrained. Anyhow, this is what I emphasize, and this is what is going to motivate us to pursue design of spline segments and curves. No local control in the Ferguson and composite Bezier curves, particularly C2 composite Bezier curves and Ferguson curves that we had studied before. We would, as designers, like to achieve local control in shape design of curves. The following few lectures will be devoted entirely to this discussion. After motivating us enough to study splines, first let us figure what splines are. How do you think Britishers, Portuguese and Spaniards could build huge ships about 300 to 400, maybe 500 years ago and travel across the world? They used something called ducts, and within or in between those ducts they used to place wooden strip or metallic strips and get the shape of the hull of the ship. These strips used to remain within these ducts for days and days. They then possibly did not know that what they are designing are essentially spline curves protruded in the third dimension. If you look at these individual segments, each segment is a simply supported beam. You might want to revisit the discussions in your second year solid mechanics course or strength of materials course. Each beam, therefore, will appear like this, simply supported at both ends. Let's try to analyze the structure using Euler-Bernoulli beam theory that assumes small deformation. This expression or relation would be very familiar to mechanical engineers or burgeoning mechanical engineers. It says EI times chi is equal to EI times the second derivative of the vertical deflection with respect to x squared, where x is along the beam length, which is equal to a times x plus b. EI is the flexural rigidity. Chi is the curvature, and for small deformation, the curvature is given by d2y over dx squared. Y is the vertical deflection. A and B are known constants. 10 points for guessing what this is. You're right. This is the moment at any cross section. If we integrate this relation twice, we'll have y equals a times x cubed over 6ei plus b times x squared over 2ei plus c1x plus c2. c1 and c2 are unknown constants which you can compute using boundary conditions. Boundary conditions at say x equals 0 and x equals L, the beam length, are that the vertical deflections are 0. Why? Because we are considering a simply supported beam. If we put x equals 0 here, and if you know that y equals 0, this would mean C2 equals 0. And for x equals L, we can substitute y equals 0, x equals L, and find what C1 is. So C1 will be minus of AL squared over 6EI minus BL over 2EI. If we substitute the values of C1 and C2 back into this equation, we have y equals minus a times L squared x minus x cubed over 6EI minus b times Lx minus x squared over 2EI. Once again, L is the beam length. What do we see? We see the vertical deflection over here as a function of the coordinate along the beam length. And we can also observe what the relation or what the nature of the relation is. It is cubic for values of x between 0 and L across the entire simply supported beam segment. One should note that Ax plus b which would represent the moment conditions at any cross section, is matched at endpoints due to equilibrium. If we look or if we observe this relation closely, this seems to be inherently a C2 continuous curve, because you would be able to differentiate this at least twice. If we go back and if we try to differentiate this thing the third time, d3y over dx cube will be equal to a, and this value a will be different across different contiguous simply supported segments. What do we note now? We can comment on what we are going to term as a cubic spline. A cubic spline is a curve for which the second derivative is continuous throughout the interval of definition. Let's go back to this figure here. We are considering this entire strip, and what we are saying is this strip is a cubic spline. It may be possible for us to generalize and define what an n minus 1th degree or an nth degree spline is. So the definition of a spline: an nth order, which is an n minus 1th degree curve. A spline is a curve which is C n minus 2 continuous in the entire domain of definition. This means that the n minus 2th derivative of the curve exists anywhere in the above domain. A little note about what order is and what degree is. Order is always degree plus 1. For example, an nth order curve will be of degree n minus 1. The basic question: why splines? Recall our discussion on Bernstein polynomials when we are discussing Bezier segments and composite Bezier curves. We would like to develop basis functions which are very similar to Bernstein polynomials. Let's call those functions as psi sub I, as a function of parameter t. T here may or may not be restricted to values between 0 and 1. Also recall the salient properties of Bernstein polynomials. Remember that they are barycentric in nature, that all these Bernstein polynomials are positive or non-negative in the respective parameter intervals, that is 0 and 1, and that all these polynomials, they sum to 1, no matter what the t value or what the parameter value is. We would want these barycentric properties to be local now. What do I mean here? Bernstein polynomials, they sum to 1 for values of t in between 0 and 1. Here we would want not all but some spline basis functions, psi's, to sum to 1 in some sub-interval of t. And of course, we would want these basis functions, psi I, to be bell-shaped. Say, for example, if you are trying to plot different spline basis functions, psi i's, one of those psi i's will look like this. Let's say for parameter values between t0 and t3. The second one will look like this, say in between t1 and t4. The third one may look like this, between, let's say, t2 and t5. And we can keep on going until the final one may look like this. Coming back to this statement, local barycentricity, we do not want all these psi's to sum to 1. Rather, we would want now only a few of these basis functions to sum to 1. irrespective of how the rest of the functions behave. And it is this that would give us the local control property. We'll see later how. Let's continue our discussion on polynomial splines. Let's consider one of these functions here, and let's try to design that function. Let's say, for example, that this function is a cubic polynomial, number one. Number two, that it is designed in a similar way as a piecewise continuous curve that we had seen when discussing Ferguson composite curves and Bezier composite curves. Let me explain this on the board. I first draw the parameter axis t. I draw the vertical axis that would represent the value of psi I. So remember, I am now constructing a bell-shaped basis function or a bell-shaped piecewise composite curve. This is how I would do this. I'll start with some parameter value, let's say TO, and I'll end at some other parameter value, say TF. And in between, I'll construct different polynomial segments. Let's say in between T0 and T1, I construct this segment. In between T1 and say T2, I construct another segment. And in between T2 and TF, I construct the third segment. Segment 1, segment 2, segment 3. Each of these segments will be pure polynomials. As you would notice, there would be junction points. In this case, we'll have two junction points here. And like we had discussed in case of Ferguson-Bezier curves, we will have to impose continuity conditions. C0, C1, up till Cn minus 2. In case this bell-shaped curve is an nth order spline. Let's now continue with some mathematics. Let me work with a few of these polynomial segments. This is the parameter axis. This is the axis that will correspond to non-zero values of the basis functions. And let's say this is a generic spline curve. We have these points at parameter value t I minus 1. We have the value of this generic spline curve as y minus 1. At ti, we have the value yi. Likewise, at ti plus 1, we have the value yi plus 1, and so on and so forth. Let's say these ordered pairs are given to us, and we have to construct a generic spline. Let's say that we are going to be constructing phi t, which would be a cubic spline in each sub-interval ti minus 1 to ti. What would this mean? At these junction points, we would want that the spline is slope continuous, and also we would want that the second derivative of the entire spline is continuous. Of course, position continuity is implicit. Some terminology. These parameter values ti minus 1, ti, ti plus 1, and so on and so forth, they are fixed values for a given spline for I equals 0, 1 up till n, and these fixed values for t are called knots. You might want to keep this in mind because we are going to be frequently using the term knots later on. Going further, these spans ti minus 1 to ti, ti to ti plus 1 for different values of I are called knot spans. If the knots are equally spaced, that would mean that if these knot intervals are of constant length, the knot sequence is said to be uniform. Otherwise, if these fixed parameter values are arbitrarily placed, the knot span is called non-uniform. We assume here that these knots are arranged in ascending order. That means ti minus 1 is smaller than ti, and so on and so forth. Let's enlarge this figure now. Same, we have the knots now, and we have the values of this composite spline at each knot. Let phi sub I be a spline in the ith span. The ith span would be corresponding to the values of t in between ti and ti plus 1. So here, this is the ith span. Let's assume that in the first span, for values of t in between t0 and t1, phi 0 t0 and phi 0 t1 are known. Coming back to the board, this is my parameter axis t. I start with parameter values t0, t1, t2, and so on and so forth. Of course, I'm interested in constructing a bell-shaped basis function, but let me generalize this discussion here. This is my phi axis. Let me start constructing a spline curve from here. At t0, let me assume that I know the value of phi 0. Likewise, at t1, let me assume that I know the value of phi 0 again. Phi 0 would be the curve in between t0 and t1. That is within the first knot span. Since I'm trying to construct a cubic curve or a cubic polynomial, let's say let it have a shape like this. I have these two conditions. I would need two more conditions. What are they? They can be the slope and the second derivative at the first parameter value. Let's assume that we have the slope information given here and also the information corresponding to the second derivative given here. Three conditions. The fourth condition, this is a cubic polynomial. I would be able to determine this polynomial. This is the first piece of the cubic spline that we are interested in constructing. How about the second one? We would need 4 conditions again, because this again would be a pure cubic polynomial. Let's construct those conditions. Let me call this phi 1 t. Phi 1 t at t2, let's say, is known. That is the first condition. How about the other 3 conditions? Let's concentrate on this point here, which is the junction point. Do I know the value of phi 1 at t equals t1? Yes, and that is the same as phi 0 at t1, which comes from here. This would give us position continuity or C0 continuity. Let's recall now what would be a cubic spline. A cubic spline would be such that this entire curve would be C2 continuous throughout. That would mean that the second derivative should be uniquely available at any point on this curve. In a sense, we need to ensure that we have not only C1 continuity or the slope continuity, but also continuity in the second derivative at this junction point. What would that mean? This would mean that we would be able to generate 2 more conditions. The slope should be equal. And the second derivative would also be equal. The slope and the second derivative for this segment and the slope and the second derivative for this segment. This ensures slope continuity, and this condition ensures the continuity in the second derivative. In a sense, for this cubic segment, phi 1t, we now have 4 conditions. The value at t equals t2, the value at not t1, the slope continuity condition, and the curvature continuity condition. Since this again is a cubic segment, with 4 conditions, we should be able to determine the 4 unknowns. Constructing the third segment. We would construct the third segment in an exact fashion that we used to construct the second segment. Let me call this segment phi 2. Let this not value be T3. Let me assume the value right here, phi 2, T3. Let me assume that this is known. At this junction point, we will have C0 continuity, C1 continuity, and C2 continuity. Now that you know what the second segment is, you can generate these 3 conditions. 3 conditions here, the 4th condition here, the 3rd segment of the spline is known. Once again, let me emphasize that this is a cubic spline. By definition, a cubic spline is supposed to have C2 continuity condition intact throughout. If we keep on constructing subsequent segments, we would be able to extend this curve as much as we want. In other words, to any not value we want. By the way, any idea as to how we can make the shape of this spline very similar to a bell-shaped curve? Well, one way would be to start with the first value as 0 and end with the last value as 0. How about the slope and curvature? Let's reserve this discussion for later. So this is a summary of the construction procedure that I had just described on board. In a sense, cubic segments, phi it, I going from 0 to n minus 1, over the entire knot span can be determined. But should the spline be constructed this way? Possibly not. Because if there are errors to start with from here, they keep on getting accumulated. They keep on getting added. To avoid that, we have a slightly different way of constructing polynomial splines. Let's start with this figure again. Let's say we know the values at different knots of the spline. The values would be yi minus 1 at ti minus 1, yi at ti, and yi plus 1 at ti plus 1, and so on and so forth. Or let's discuss an alternate approach. Since each segment over here, represented by phi I, is cubic, I can write phi I in this form as a function of parameter t. Phi I is equal to a sub 0 plus a sub 1 times t plus a sub 2 times t squared plus a 3 times t cubed. A0, A1, A2, and A3 are unknown constants or coefficients. And phi I would be defined within the knot span ti and ti plus 1, right here. Now let's say that Si and Si plus 1 are unknown slopes at values of t equals ti and t equals ti plus 1. Okay, now in terms of the two positions and two slopes, what do we have? we have a linear system in the coefficients. We'll have the coefficient matrix as 1 Ti, Ti squared, Ti cube, 1 Ti plus 1, Ti plus 1 the whole squared, Ti plus 1 the whole cube, 0, 1, 2 Ti, 3 Ti squared, 0, 1, 2 Ti plus 1, and 3 Ti plus 1 squared. What would these coefficients correspond to? Well, this corresponds to the first equation if we substitute phi I equals yi for t equals ti. This row here corresponds to the second equation. Phi I at ti plus 1 is yi plus 1. If we differentiate this, we'll have a0, which is gone. We'll have a1 plus 2a2 plus 3a3 t squared. If we substitute t equals ti, these two terms are 0, corresponding to the first coefficient, a0. These two terms will be 1. We'll have a1 here. These two terms will be corresponding to ti and ti plus 1 times 2, first differentiation of this term. And these two terms here would be corresponding to the first differentiation of this term here for values of ti and ti plus 1. This is a column vector comprising unknown coefficients, and these are the respective y and y plus 1 values here, and also the values of the two slopes, si and si plus 1. We know this column, we know this coefficient matrix, or this 4x4 matrix. We can compute what a0, a1, a2, and a3 are, which would be this 4x4 matrix, inverse of that, times yi, yi plus 1, si, and si plus 1. But wait a minute. When did I tell you that si and si plus 1 are knowns? We just said let the slopes be unknowns at these 2 points. Let's see where this takes us. Okay, this is a little more involved expression here. Phi it can be represented in matrix form or in compact form. Okay, so the first matrix will be the 1/4 matrix in terms of parameter values t, 1, t, t squared, and t cubed. This is a very complex looking 4x4 matrix, and this is the geometric matrix pertaining to the geometric information here, the 2 points and the 2 slopes. What is this 4x4 matrix? The inverse of this matrix here. Okay, let me read out the terms. The first term, ti plus 1 minus 3ti times ti plus 1 squared over hi cubed. 3 times ti plus 1 minus ti times ti squared over hi cubed minus ti, ti plus 1 squared over hi squared minus ti squared, ti plus 1 over hi squared. Second row, 6 ti, ti plus 1 over hi cubed minus 6 ti, ti plus 1 over hi cubed, 2 times ti plus 1 times ti plus 1. The fourth term, ti plus 2 times ti plus 1 times ti over hi squared. In the third row, we have minus 3 ti plus ti plus 1 over hi cubed, 3 ti plus ti plus 1 over hi cubed minus ti plus 2 ti plus 1 over hi squared minus 2 ti plus ti plus 1 over hi squared. In the fourth row, we have 2 over hi cubed minus 2 over hi cubed, 1 over hi squared
and 1 over hi squared. Okay, what is hi? Hi is the difference ti plus 1 minus ti. Let's continue with this math. Okay, now the entire cubic spline is essentially a set of each cubic segment phi it, I going from 0 to n minus 1. Okay, and this spline is position and slope continuous within the entire knot span going from T0 up till Tn. Notice that since phi I is a cubic spline, it needs to be having unique second derivatives at each value of t in the entire span. Okay, this would mean that phi I minus 1, which is the I minus 1th segment, the second derivative of that at the knot value ti should be equal to phi the ith polynomial segment, the second derivative of that at ti. From that previous complex relation, it should be possible for us to compute what the second derivative is. This coefficient matrix will not change. This geometric column vector will not change. What would change would be this first 1 by 4 row matrix. If I differentiate the previous relation twice, the first term is 0, the second term is 0, the third term is 2, and the fourth term is 6 times t. These two matrices are constants in differentiation. All I need to do is plug in this expression here in this equation for value t equals ti for both I minus 1th cubic segment and the ith cubic segment, and figure what that relation would look like. You'll have to bear with me here because the math is really quite involved. Let's continue. If you work out and simplify the math, you'll have the second derivative of the ith cubic segment written as 6 times 2t minus ti plus 1 over hi cube minus 6 times 2t minus ti plus 1 over hi cube, 2 times 3t minus ti minus 2ti plus 1 over hi squared, and 2 times 3t minus 2ti minus ti plus 1 over hi squared. This is your 1 by 4 row matrix multiplying this column vector here. yi plus 1, si, and si plus 1. Remember, the second derivatives of the I minus 1th segment and the ith segment at the common knot ti are equal. All you need to do is set I equals I minus 1 to get this expression. The composition of each term will be similar, just that ti is going to be replaced by ti minus 1 and ti plus 1 will be replaced by ti. Hi gets replaced by hi minus 1, yi gets replaced by yi minus 1, si gets replaced by si minus 1, and so on. On comparison, that is, when you impose C2 continuity conditions, we'll have this expression: 6 over hi minus 1 squared minus 6 over hi minus 1 squared, 2 over hi minus 1, 4 over hi minus 1 times yi minus 1, yi, si minus 1, si.
is equal to minus 6 over hi squared, 6 over hi squared, minus 4 over hi, minus 2 over hi times yi, yi plus 1, si plus 1. Look how that complex math turns simpler as we go on. We can further simplify this and have this relation. Si minus 1 over hi minus 1 plus 2 times si within parenthesis 1 over hi minus 1 plus 1 over hi plus si plus 1 over hi equals 3 times yi plus 1 over hi squared plus 3 times yi times within parenthesis 1 over h sub I minus 1 squared minus 1 over hi squared minus 3 times y I minus 1 over h I minus 1 squared. Now this is for I going from 1 to n minus 1. There's something important about this relation. Now, while we were doing the complex math that we just did, let's not try to forget what was the physics behind the entire discussion. Remember, I had mentioned that the slopes, in fact, at all junction points were unknown, implying that these slopes si minus 1, si, si plus 1, they are all unknowns. What is known to us is the values at each junction point, yi minus 1, yi plus 1, and so on and so forth, and also the knots at each junction point. That is ti minus 1, ti plus 1, and so on and so forth. So here we have a relation that relates 3 consecutive slopes. Si minus 1, si, and si plus 1. Have you seen such an expression before? Yes. When we are discussing composite Ferguson curves, rather a C2 composite Ferguson curve. This condition right here is a condition for generalized Ferguson curve. Going back, how many equations will we have here? I going from 1 to n minus 1. We'll have therefore n minus 1 such equations. How many unknowns will we have? We'll possibly have n plus 1 unknowns. Okay, let me copy the previous equation right here. And let me also observe a few more things about these equations. These equations are linear in the slopes si minus 1, si, and si plus 1. The slopes which are unknowns are s0, s1 up till sn. These are n plus 1 slopes or unknowns I had just mentioned a while ago. These equations right here are n minus 1 in number. We'll have therefore 2 free choices or 2 more conditions that we would need to generate. Those conditions could be any one of the following. 1, free end, that is, no curvature at a knot. We call it a natural spline. Condition 2, built-in end. What do I mean by that? The first
derivatives at the first knot or the last knot are specified as phi 0 prime t0, which is s of 0, or phi n minus 1 prime tn equals sn. In other words, slope s0 and sn are specified. Condition 3, quadratic end spans. Here, if the end spans are quadratic, the end curvatures are constant. So the two conditions that we need to solve the system of n minus 1 equations can be any two of these three conditions. Remember, for C2 composite Ferguson curves, we had specified the two end slopes as free choices. This is here a more general set of end conditions. Let's work with an example. Compute a cubic polynomial spline to fit the data points 0, 0, 1, 3, and 2, 0 with free end conditions. Let's assume the three knot values as t0 equals 0, t1 equals 1, and t2 equals 2. We have uniform knot spans here. H0, which is t1 minus t0, is 1, and h1, which is t2 minus t1, is again 1. I would want you to remember the mathematics that we had gone through. With that, we'll have the second derivative of the first spline segment evaluated at t0 as 6 times 2 times t0 minus t1 over h0 cube minus 6 times 2 times t0 minus t1 over h0 cube 2 times 3 times t0 minus 2t1 over h0 squared 2 times 3 times t0 minus 2 times t0 minus t1 over h0 squared. The column vector here will have entries y0, y1, s0, and s1. We know what y0 is, what y1 is, and s0 and s1 are unknowns at this time. We'll have an equation that will say 18 minus 4 times s0 minus 2 times s1 equals 0. For the second spline segment, phi 1, we'll have a very similar expression. Phi 1 double prime evaluated at t2 will give 6 times 2t2 minus t1 minus t2 over h1 cube minus 6 2t2 minus t1 minus t2 over h1 cube 2 3t2 minus t1 minus 2t2 over h1 squared 2 3t2 minus 2t1 minus t2 over h1 squared. The column here will have y1, y2, s1, and s2. Working on this equation gives us 18 plus 2s1 plus 4s2 equals 0. We have this equation in s0 and s1, and we have this equation in s1 and s2. For a moment, I was confused as to what I was doing. Okay. Now let's go back. We are saying that we are going to be using free end conditions. That would mean that the second derivatives at t0 equals 0 and t2 equals 2 will be 0. So the second derivative of phi 0 at t0 is 0. The second derivative of phi 1 at t2 is 0.
So these are the two conditions corresponding to that. Now this condition is a familiar one. We have seen this before. Relates the slopes S0, S1 and S2. If you plug in the values of H0, H1, Y2, Y1 and Y0, we'll have S0 plus 4 S1 plus S2 equals 0. So the three conditions will give us S0 equals 4.5, S1 equals 0 and S2 equals minus 4.5. If we compute what phi 0 t is, this is 1 t squared t cubed. We would be able to compute what the coefficient matrix is. You would need to compute the inverse of that, and we'll have y0, y1, s0 and s1 here. We solve or we simplify this expression to get phi 0 t as minus 3 over 2 t cubed plus 9 over 2 t. Likewise, phi 1 t will be 3 over 2 times t cubed minus 9 t squared plus 27 over 2 t minus 3. We now know what the analytical expressions of individual cubic segments phi 0 and phi 1 are. Let's plot them. The red curve here and the green curve here, they represent the first cubic segment and the second cubic segment. We get a shape very similar to a bell-shaped curve. But I'm not saying that these would correspond to our basis B-splines. We'll still have to do a lot of work to be able to get nice looking bell-shaped basis functions. In the lectures that will follow this one, we would like to design bell-shaped like basis functions, which will be composite polynomial splines, which will be locally barycentric as opposed to globally barycentric, which are the Bernstein polynomials. In a sense, we will be concentrating essentially on designing these basis functions.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other. Correct? So when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.
Swayam Prabha. Digital India. Educated India.
Welcome back to the manufacturing automation series of lectures. Now, in our last session, we discussed some of the important points about the feed track, and it was told that feed tracks should not be unnecessarily long to make use of the space optimally. Second very important point that we discussed is that the feed track, apart from passing the parts or transmitting the parts from the ball feeder to the assembly machine, it should also act as a buffer stock. If anything happens or any stoppage happens in the ball feeder, so that the parts can still be available in the feed track so that the machine does not starve. And the third point that we said, that is the feed tracks, they also we did not mention that the feed track should not be unnecessarily expensive as well. After that, we have discussed some escapements. These are the devices. We said that when the parts have to be fed to the assembly machine one by one, so there are certain natural devices we have seen. For example, I will show it once again. So you can see that these are the natural devices. I am just summarizing them. These devices are activating the escapement. Okay, escapements are being activated by the parts and the work area, but in the actual escapement, the idea is that the escapement will activate the parts and the work carriers, so that one by one the parts could be fed to the assembly machine. We have shown some of the examples of the escapement. For example, here it was a ratchet escapement. It is for releasing of one part at a time or more than one part by using a pawl which is pivoted here and which actually goes to and fro. So this is the arrow which is shown, which is the direction of movement of the pawl. Now, here is another example that have been shown, that using these kind of pulse or these kind of mechanisms, one can pull it to and fro, okay, pull or push to and fro, and the parts will be taken from the feeder, delivered to the machine, assembly machine, one by one. Well, let us see the other examples. For example, in this case, slide escapements delivering into single feed chute. Here, these are the parts coming from the feeder. Either it can be a horizontal feeder, or it can be a vertical feed delivery. And the parts, when it is coming at the end of the feeder, there is a cross slide here, and this slide can reciprocate. While reciprocating, while the slide is going to this side, it will take one part from the feed track, and it will deliver to the machine. So, this is going to the assembly machine. So, while it is delivering one part to the assembly machine, the other parts in the feeder will be held back. So, they will not be able to fall. And then again, when the cross slide is going to the right side, then all parts will be falling up to this, and the size of this cross slide accordingly made according to the parts, so that only one part can be selected, and the one part can go into the machine. So, for more than one part, depending on the thickness or the size of the part, it can be made in this way. For example, in this case, 3 parts at a time will be given to will be fed to the delivery chute. So, in that case, the height of the cross slide or the width of the cross slide is made in accordingly, either to be fed fed one part, or more than one part can be fed. Slide escapements operating several feed chutes. Look at this. From the feeders, the parts are coming in this way, and here there is a slide where it has the grooves for the parts to be nested, and these grooves are made according to the size of the part, so that only one part can go to that groove. So, as you can understand, this is also self-explanatory, that as the slide is going to the right side, it will subsequently take up the parts from the feeders in the grooves, and when the slide is going to the left, these parts will be coming, one to this, another to this slide feed chute, and the third to this feed chute. So, as you can understand that depending on the requirement, it can be number of parts can be fed taken from the feeder, and this line diagram is quite self-explanatory. So, this is for spherical, cylindrical, or plates, for example, this kind of escapements can be used. So, again, let me remind you why this is called the escapement, because when from the feeders all the parts are coming together, they cannot go directly to the machine, because machine cannot take all of them together. So, this is the kind of a mechanism which is used, called as an escapement, to feed the parts from the feeder one by one, and all these other also you have seen. One point here you can actually note down, that these parts, when they are coming from the feeder and with the help of these poles, when the parts are being fed one by one, of course, there should be some gap between the parts, so that the poles could actually penetrate. Otherwise, they cannot segregate the one part from the other part. So, there are certain kind of chamfers made, so that the pole can go into that groove or the space, and they can segregate one part from the others. The next escapements you can see from here. For example, this is an example which is the slide escapement, supplying 2 or more delivery chutes from a single feed chute. Look at this example here. What we are saying is that there is 3 from the feeders, the 3 parts are coming in this example and delivered to 3 feed chutes. In this example, what we are doing is, when we are taking from the feed track, from one feed track, and it is being delivered to once to this feed chute and another to this delivery chute. So, how it works, it is also quite explanatory, self-explanatory. This slider, this has 2 groups, one in here, one in here. While it is coming from this side, while it is going to the left, for example, this will be collected, the parts will be collected in group 1 and group 2, and then when it is going to the other side, the parts from this will be coming to this groove or sorry this chute, and this part will be coming, another part will be coming to the another chute. So, that means from one feeder subsequently you can put in one delivery chute once and in the second delivery chute next. So, parts fed from a single feed track to be equally divided between two delivery tracks, useful where two identical parts are to be used particularly. So, parts are being supplied alternatively to the delivery chutes. Once it is one part is going and the similar part is coming to the other delivery chute during the movement of the slide. Here for example, if it is 2, so more than 2 can be also supplied. Here it is another design is given, supplying parts simultaneously to several delivery chutes, and the diagram is again self-explanatory, that from the feeder the parts will be collected to this groove in the movement of this slider in one way, and while it is coming to the other way, these parts will be delivered to the chutes, to the delivery chutes. There is a compression spring given here, and that compression spring helps the arm to move to and fro. Okay. Now, here is another example of an escapement which is called the drum escapement, and in the drum escapements parts fed and delivered side by side, in the sense that from the feeder it is coming to the escapement, to the drum, and the drum is inside, which is rotating inside a casing. This outer casing is a stationary casing. So, in the drum we have the groups here, all right, and these groups can nest the parts which are coming from the feeder. So, if suppose the drum is rotating in the anti-clockwise direction, so while it is aligning with the feeder, the parts will be nested to this groove of the drum, and while rotating further and as it is being aligned to the exit, the parts will be stripped off the drum and it will come down to the delivery chute. Drum is mounted vertically and the parts are fed and delivered side by side. Okay, so this is another advantage, and also this drum escapement also is used for using the space, where the space between the ball feeder and the machine is limited. On passing through the escapement, the parts can be turned through a given angle. This is another advantage of the drum escapement. Now, here this is another principle, parts fed end to end, all right, and delivered side by side. So, it may so require that parts are coming in a certain position, and the machine that the assembly machine will accept the part in another position, for example. Okay, so here for example, the parts are coming like this, parts are coming end to end and they are delivered side by side, and this is again the example of this, and this is the rotary side escapements, which is the example shown here. This is similar to this. Okay. Next is the star wheel and the worm escapements, and these are also given, the diagrams are here, you can see this, there is a star wheel here, and this is the feed track. Now, inside the feed track there is a space here through which the star wheel can rotate, and while rotating the distance between the teeth of the star wheel is made in such a way that it will actually grab one part and then deliver, while the other parts will be held by the other teeth of the star wheel while it is rotating. It rotates at a very lower speed, the speed which is required for the machine to be, for the parts to go to the machine. Now, direction of motion is unaffected by the escapement. That is one thing. Parts should have suitable gap between the outer edges. Here by virtue of this size of the parts, okay, that means the shape of the part, that is the round shape, you can see that always there will be a space for this star wheel tooth to go in and then segregate the other parts, and one part can come to the assembly machine. Here there is a worm, okay, like in case of worm and worm wheel. So, this worm rotates again inside the some portion of this worm will go inside the feed track. There is an opening here, and the teeth which are these teeth which are of the worm, when it will rotate, they will actually take the parts one by one to the machine, because this is rotating, let us say this is rotating in this direction, and then parts will be guided by the space here, and it will be taken to the machine, assembly machine. Now, these worms, if it rotates continuously, for example, then the speed of the feeding of the parts will be too high. Okay. So, therefore, this is rotated intermittently as and when the when the part will be required for to the machine. So, depending on the cycle time in the machine, for example, if it is an assembly machine, so how much time it takes for making one assembly of one part, let us say it is 5 seconds. So, it will stop for 5 seconds, after 5 seconds it will again take another part, so that the machine can accept. That is what we mean by driving this intermittently. This is one example of the jaw escapement, and the jaw escapement works in the following way, that we have the actuator, which is a punch also, and here there are poles. Okay. So, it is actually when the parts are coming, let us say in this figure you can see that from the feeder the parts are coming like this, and the actuator can be also used as the escapement, as well as when it is required to push, for example. Let us say for push fitting or for riveting, for example, used when some forming process is necessary on the parts after it has been placed in the position. The positioning is done one by one from the feeder by this punch, and then it can also work further to push it, to make some to impart some forces, so that either it goes in or it is push fitted or it is riveted, for example, if it is required, and so on. So, this is called the jaw escapement, and it works very well. So, here in this diagram, as you can see, that this is the escapement, and the actuator comes, releases this part from the escapement, and then doing some forming work, that means imparting some force if it is required. I hope this is clear. By far the most widely used parts placing mechanism is a conventional gravity feed track working in conjunction with an escapement. This system of part placing is probably the cheapest available. Example, I have shown it to you earlier. All right. So, those are the conventional gravity feed tracks in conjunction with an escapement. Now, it has certain limitations, and those limitations are, it may not be possible to place and fasten parts at the same position on the machine because of interference between the feed track and the workhead. This would necessitate a separate workstation for positioning the part, which would result in an increase in the length of the machine. It then becomes necessary to retain the part in its correct orientation in the assembly during the transfer. So, these points have to be kept in mind, because these are the important things, that whether you are going to have what kind of part placing mechanism you should have, what kind of escapements you should have, and so on. If a close fit is required between the part and the assembly, the force due to gravity may not be sufficient to ensure that the part sits properly. This example exactly means that suppose you are putting that in the place, and it is not enough that with the gravity it will go into the position. So, there you may need some kind of force from outside to impart on the part, so that it can actually be placed here. Otherwise, also what may happen is that part may be misplaced in the position. It may be wrongly positioned. Okay. So, that is another thing which will be which can make a faulty assembly, for example. If a part cannot be suitably chamfered, the gravity feed track may not give the precise location required. So, if they are chamfered, that is fine, it can be, but not all parts could be chamfered, and in that case the gravity feed track alone cannot actually work. So, there have to be some kind of a part placing mechanism. Okay. Apart from the escapement what we have discussed, their job is to put the part one by one to the feed the part one by one to the machine. Okay. Here what we are talking about, that some of the gravity feed tracks along with the escapement, that may not be enough for the parts to put in a right position. So, for that we need normally a part placing mechanism. Let us see what are the part placing mechanisms. Normally they are the manipulators, they are the robot hands and so on. However, look here, this is the diagram which is showing the screw placing and driving. See here in this diagram what is shown is that from the feed track the parts are coming in here. So, this is the jaw, or this is the screw drive, for example. This can go up and down. So, while going up to this position, it can allow the part to come in, one part to come in. The space can be such that one part goes in, and then after that this screwdriver, it can be a screwdriver as well. So, this can go in and it can apply some torque so that the screw can actually go inside the threaded hole. So, both of them, both these two working conditions are shown here. For example, here the part is placed, okay, and there are jaws here, so that the jaws could be acted as an escapement, and after that the screwdriver comes in and it rotates to impart the torque to this. So, for placing of screws and rivets which together form a large proportion of all part placing requirements, and where the tool activates the escapement and applies the required force to make assembly possible, the gravity feed track is invariably used. So, in all these cases the gravity feed track is used. Another part placing mechanism or other part placing mechanisms, as I said, that this kind of robotic arm or manipulator can be used. So, in this, part is picked up from the feed track by means of mechanical, magnetic or vacuum hand. So, this is the manipulator or the robot arm, and it has at this end effector. It can be a mechanical gripping, or it can be a magnetic if the parts are of ferromagnetic material, or it can be a vacuum hand. For example, if the television screens are to be picked up, or if a very precise plate should be picked up where you cannot afford to have any kind of gripping, so that there is no scratch or anything, okay, or computer screens, for example, okay. So, from the feeder the parts are coming here, and it will the robot manipulator, it will come like this, then the end effector will come to this position, pick it up, go up, and then again going to this side and putting it in the work area. So, it will pick up from the feeder and it will place to the work area. That is the part placing mechanism, the job of the part placing mechanism. Picks up job vertically, transfers along a straight path and horizontally, and place vertically again. So, this kind of movement can be programmed, so that all the time it will move like this, come here, go up again and come to this position. So, it can actually repeat this position. So, they are normally programmed so that the parts can be placed one by one from the feeder to the work area. Here is another example using the same using the robotic hand, but that manipulator is of different configuration. For example, this is the manipulator like in here. So, here this manipulator picks up the part from here and it rotates and placed it here. In this case, what is happening is that the work carriers and the feeders, in this case it is side by side, and the mechanism is behind the work carrier. So, it may so happen that the mechanism is placed in between the work carrier and the feeder. In this case, it will take up the job from the feeder. This hand will rotate about this axis and it will place it vertically to the work carrier. Picks up job vertically, transfers around the arc of a circle in horizontal plane and places vertically. So, this is the idea and this is the working principle of the part placing mechanisms. These are simple mechanisms, pick and place units, and those units can be placed either behind the work carriers or in between the work carrier and the feeder, as I said. Now, the signal when it has to activate, this may come from the machine itself, from the assembly machine itself. Assembly machine, when it finishes a work, sends a signal to the pick and place unit, and then it will activate and bring the part from the feeder to the work carrier. Here are some other examples of the part placing mechanisms. The diagrams, as you can see, they are self explanatory. Here the picks and here picks and places by rotary motion of the transfer arm in a vertical plane, and throughout transfer the hand remains vertical. See, here we have the feeder, the parts are coming from the feed track, and this is the pick and place unit. Here we have the manipulator. This is pivoted here in the sense that it can this arm can rotate about this pivot, about this point, and here there is a manipulator. This manipulator can also rotate like that at a 90-degree angle. All right. So, what it does is that this arm will rotate, this manipulator will pick up the part, and then again it will go to this position and then place the part vertically. So, here you can understand that it may actually have two movements. One movement will be by this and another movement will be by this. So, there are two degrees of freedom here. Here is another example, like pick and place unit is here. This is the work feeder, and parts are coming from the feeder and to be placed to the work carriers. So, here also, like in this design, we have the manipulator which can actually rotate about this point. Okay, it can swivel around this point, and here this arm can also swivel about this axis. All right. So, that if the part is taken from the feeder in one orientation, it can turn the part and put the part in another orientation. So, it is like it is taking like this and putting it in this way. So, this is the idea of this part placing mechanism. The part is turned over during the operation. Suppose if it is so required. So, in this case, this kind of part placing mechanisms are used. Here I will come back to this. In this case, the part can be placed in the same position as it is picked up. Here the part is turned from the position it is coming. Next we will discuss some of the points in the design for automatic assembly. Now, when we are having the automatic assembly, it is understood that since the human being is not involved there, so some of the jobs that the human being can do very easily may be very difficult for the automatic assembly to perform or automatic machines to perform, and therefore some of the points we should consider in the design of the part when we are designing the part, so that the automatic assembly could be done in a better way without the intervention of the human being. I will give you some examples. Suppose you have a part which is of a very complicated shape, and there are several of them, they have to be assembled. So, in that case what is happening is that we require several machines for performing each of these assembly operations. All right. Whereas, we can change the design in such a way that some of the parts could be combined together in the design to make one one part out of those, in the sense that suppose using developed let us say metal forming processes or metal casting techniques to join some of the parts and make it as one part, so that if we have two parts joined together in the design, in that case two assembly processes could be avoided and there would be only one assembly process. So therefore, for design for automatic assembly, two aspects will be required. One is the product design for ease of assembly. As I said, for example, product design for ease of assembly, chamfer is one thing which you have discussed earlier, which actually facilitates the facilitates the parts to get assembled. Okay. And there are many other aspects that we will see in the subsequent discussion, that the product design should be for ease of assembly. Another aspect is that design of parts for feeding and orientation. It is not only that we are assembling the part, but we are also feeding the part. So in the design we should consider some of the aspects so that the feeding could be done in a proper way, as well as the part could be assembled in a proper way. These things in details we will discuss in the next session. Thank you very much.
Swayam Prabha. Digital India. Educated India.
Welcome back to this series of manufacturing automation lectures. So let me remind you, in our last session we have discussed some part placing mechanisms, we have discussed some escapements. So we said that there are some natural escapements that is activated by the parts and the work carriers, but actual escapements activate the parts and the work carrier and facilitate the parts to go to the assembly machine one by one. We have also discussed that the parts, when they are going to the assembly or the work carrier, the assembly machine, then the part may be displaced, and therefore only gravity feed track along with the escapement may not be enough for the part to position in a right way or to keep the position intact. In that case, what is used is the part placing mechanisms, and we have seen different mechanisms of the part placing mechanisms, which are basically the robot arms, manipulators, etc., and they may take up the part from the feeder and they will place it to the work carrier, so that the work carrier could carry the parts to the machine, to the assembly machine. Next, what we said is that there are certain changes in the design that can be made so that the automatic assembly can be efficiently made, and a huge amount of spending can be saved by these designs. Let us see some of them. So we said that the design for automatic assembly is basically, there are of two aspects there. One is the product design for ease of assembly. I gave you some examples of chamfers, for example, or so that the two parts cannot be stacked together, because you should understand that when the parts are fed from the ball feeder, inside the ball feeder the parts are stacked, many of those together. So they may entangle with each other, they may stack to one, stick to one another, stacked in between, and so on. And the design of parts for feeding and orientation. We will take some examples how the design can be changed so that it can be easily assembled or it can be easily fed and oriented. Product design for ease of assembly. First point is the reduce the number of different parts to a minimum. This just in the previous session I discussed it. Can be achieved by employing one of the new processes that enable complex parts to be produced. For example, precision die casting or new forming processes. Let me explain it to you. If a complex part can be produced, that will reduce the number of assembly processes drastically. That means that 2 or 3 parts, they are actually designed and made together, okay, by casting process or by metal forming process, and that way we are reducing the number of different parts. Second point is introduction of guides and tapers which directly facilitate assembly. These examples we will see later, that how the implementation of the taper or a chamfer could facilitate the assembly. Assembly in sandwich or layer fashion, in the sense that when the assembly is made, it should be made preferably on a base plate, and then parts should be stacked one on another, on top of another, and access to the sub assembly or the assembly should be from one direction as far as possible. That is what we mean, that the assembly in the sandwich or layer fashion. We will see the example. Assembly on a base, as I said. So here are some of the examples. These examples are quite self-explanatory. For example, the product design for ease of assembly, introduction of guides and tapers which directly facilitate assembly. Let us take an example. Suppose we have a part like this, all right, and a spring has to be assembled, a spring has to go in. So part placing mechanism will take the spring and put it here. Now because of this edge, all right, the spring actually may not go up to the end and it may get stuck here, okay, because of the design in this part. But this design can be changed by making a chamfer here, that is one thing, and a chamfer or tapering in this case, so that even if it happens like this, as it is shown in the first diagram, the taper that will guide the spring to the desired position, and with this chamfer and this taper, the spring will never be in this position actually, because in this case here it is also lying on that edge of this part, all right. In this case, if there is a chamfer, so this will also guide the spring to come to the desired location. There are different kind of threaded points. For example, here there is a rolled thread point. This is taken from, I mean, it can be obtained from the cold roll, all right. This is the headed point, and here we have a chamfer. The difference between this is that this is cold rolled and this is with a chamfer, all right. Now this also has a chamfer. Now here this is a dog point, this point is called the dog point, here there is a cone point, and here there is a oval point, all right. So these different types of screws, now they mostly are used in practice, like for example, if there is no chamfer, cold rolled, so they are very cheap, so therefore they can be easily used. But when these are used in the automatic assembly, to facilitate the automatic assembly, basically the cone point or the oval points, this should be used, because the cone point and the oval point, this will facilitate the parts, this will to go to the threaded adjoining part, for example. So dog point, for example, this also can guide the screw, okay, or the threaded part inside the threaded hole. Here there are some examples. For example, this insertion is difficult because it is blind here, and sometimes there is a small hole made so that the insertion can be facilitated, all right, or there could be a flat here. This is the hole in the pin or flat in the pin, okay. So this will facilitate the assembly. Here is an example of a plug which you understand this is a simple 3 pin plug. When we said assembly in sandwich or layer position, this is exactly what we mean, that this is a base for the plug, and to the base the parts are coming from one direction, preferably from the top. See, this is the ground pin, this is the fuse clip coming to the ground pin, this is the fuse when these two clips are made, so then the fuse can be put in. This is the neutral pin, alright. So, neutral pin, live pin, ground pin, they are placed here, then the cover can come. So, all are coming from the top. See, the access to the parts, to the assembly is from one direction, preferably as far as possible. When everything goes in, after the cord grip is made with the screws will be coming from the opposite direction, and the main screw to fix this base to the cover, this will also come from here. So, as far as possible, most of them will be coming from top, okay, sandwich or layer fashion. Only thing is that cord grip screws and the main screw, these have to come from the opposite direction. Product design for ease of assembly, we are continuing. It is always necessary in automatic assembly to have a base part on which the assembly can be built. This base part must have features that make it suitable for quick and accurate location on the work area. Let us take an example of this. For example, this is a base, all right. Now, when this base, this is a work area. So, when this work carrier, it will be coming on this, on the work carrier. So, this part as a base part coming on to the work carrier, this will be unstable in here, because any force which you impart at this point, this will actually rotate the part, because they will be touching these two edges. As you understand that without this ledge or without this alteration in the base part, this base part will be unstably located on the work carrier, because any force which is imparted here, this will actually rotate on the edges. So, there is a small change in the base part that we are doing here, small feature that has been introduced. This is making the quick and accurate location of the work area on the work area possible. So, once again, this is the base part, this has to come on the work area, and for quick location and accurate location of the base part on the work area, there should be some specific feature. So, without that feature having here, this base part on the work area may not be located easily or accurately. That is what we are saying. Now, sometimes the work carrier base part is here. So, they sit on the work carrier with a dual pin. Okay. So, these are the pins, and these pins go into these holes, so that the base part can be quickly located here. Location of the base part in the horizontal plane is often achieved by dowel pins mounted in the work carrier. So, these are the dowel pins, and they are, as I said, they can come in. So, in that case, what is happening, that base part can be located with respect to these holes as well, and that is very important, because some screws, something, some rivet, something goes in this. So, they have to be located properly with respect to the axis in this direction, and they can be done by putting the base part on the dowel pin. These are other examples. Here some of the examples given with the help of self-explanatory diagrams, how the parts can be designed for feeding and orientation and orienting. For example, this kind of parts, glass type, all right, with a cone, or a part which is like this, there is a straight slot here. Now, here there is open-ended spring. So, here you can see the change in the design, the small feature that can be introduced, so that these parts can be fed or oriented in a proper way. For example, these parts may nest, one glass may go into another and they can stack, and it will be very difficult for the parts to go out on its own. So, this feature is made, that is the rib in part will stop the nesting. Now, one thing we have to keep in mind, that these are the small features which should be non-functional, in the sense that these features which we are introducing, either the feature that we said here, all right, in the base plate, or the feature, for example, these features which we are introducing, either the feature that we said here, all right, in the base plate, or the feature disturb the operation of the part. So, they will be non-functional. For example, here there is a straight slot. So, another of this kind of a part which are there stacked in the bowl feeder, they can be actually entangled. So, if we have a crank slot entangled between each other. So, this is the advantage of changing the small feature in the design. For example, if we have the open ended spring, so another spring can come in easily and they can get entangled and they will clog the exit of the ball feeder. Now, here we can have a close ended spring instead of the open ended spring, all right, and in this case the springs will not be entangled with each other. Here there is an example of an open spring lock washer, and that can be closed, for example. Now, here you may one may ask that if this is the open spring lock washer, then if we close it, then this spring lock washer functioning will be affected. This will not, because still we have, you can see that this is not exactly flat, but it will still have the springy action, so that it can still work as a spring lock washer. The only thing is that it will not be open here, so that they are not entangled with each other. Look at this example for here. This is asymmetrical. Okay, here there is a stud. So, this stud has one end with a thread which is smaller than the thread at the other end. All right. In this case, what will happen, if for example, this is the ideal orientation that we want, but if the part is coming in the other orientation, there will be no feature here, so that it can be reoriented. Okay. But to avoid that problem, suppose we are actually increasing the length of this thread by this much, so that it could be equal to the length of the thread made at the other side. In that case, whether the part comes in this position or that other position, it will not be matter. Now, one question that we should discuss here, that when we are increasing the length of this thread to this length, in that case we are incurring some cost, of course, because this we require this much length. So, it was designed like this, and now you are changing the design by increasing the length of the thread, for which we have to incur some cost, but it can be economically justified, because otherwise what will happen, some reorienting device has to be created for this to reorient the part if it is not coming in the right orientation. So, economically it has to be properly justified, that if we can make the change in the design in such a way, how much cost will be incurred, and whether it can be justified by eliminating the reorienting device for this kind of parts. Here there is a part shown which actually is very difficult to orient because of this groove here. So, this groove, since it is made not completely, okay, let us say halfway or something, this is the design. So, this feature makes it very difficult to make them to orient the parts. Suppose if we make it like this, all right, in this case this functioning should not be affected, that is one thing, all right. So, we say that any feature, I repeat once again, that any feature that we are introducing, this will be non-functional, in the sense that it should not disturb the functioning of that particular part. So, if we are extending that, in that case it will look like this position, they look like this diagram, and here it will be very easy to orient, because this orienting device can base on this surface, whereas here there is no base, because it is not open, all right, meaning that there could be some thing, some part here based on which this part can be transmitted, all right, but here it is not possible because it is closed, as you understand that. So, this feature, by extending this feature in the design, we are not disturbing the functioning of the part, but we are facilitating the parts to get reoriented. These are the ideas of this kind of changes in the design. Look at these parts, for example. These examples are given for parts to feed the parts and orient the parts in a better way, meaning that these changes in the design which are shown here, they will make the feeding and the orienting easier. Let us see this design. This is a disc with a center hole and 2 holes on the sides. Now, this disc is very difficult to orient with respect to these small holes, because there is no surface here to grab, okay, for the gripping. So, in case we change the design in this way, we are making the flat here, okay, flat here and flat here. In this case, this flat can be taken as a base for orienting this this part with respect to these 2 holes. Otherwise, what will happen, this disc may be gripped in this way or this way or this way. So, there is no way for orienting the part with respect to these 2 holes, as you understand. Look at this part, for example. If we change the part design in this way, so that there is a hook kind of a thing introduced here in the design, in that case this part can be transmitted, this part can be fed to the assembly machine when it is hanging on a wire, for example. If this is the case, if for this part, for example, there is no way for the part to be fed in a direction or in the orientation like this. And otherwise, what will happen, suppose if we do not introduce this, then this part can come in any orientation, but we have to use the reorienting device, for example, to give this kind of an orientation to the machine, to the assembly machine. Whereas, by making this small change in the design, we are facilitating the part to hang on the wire, and it can actually wire on any kind of a rail, so that it can be transmitted in a proper way. In this design, for example, triangular shape of part makes automatic hole orientation difficult. Now, here is a triangular shape. So, either it can come this way or with this edge or with this edge, then it will be difficult to orient the part with respect to these holes. Whereas, suppose we want the part to come in this orientation as it is given here. If we make a small non-functional change, okay, and make a shoulder, small shoulder like this, it is given here. So, this can be based, this surface can be based to orient the part, triangular part, with respect to these holes, for example. So, as you understand that these small changes, here there is a small flat, here there is a kind of a hook here, here there is a small shoulder, they will not change the functioning ability of these parts, but these changes will actually facilitate the parts to feed and orient, for the feeding and the orientation. Well, next let us see what is a precedence diagram and what way it helps us in the automatic assembly. Take an example of this plug assembly that we have seen here earlier. So, here what we said is that 2 things. One is that it has to be assembled on a base plate, this is the base, and all the other parts should be coming in a sandwich manner or a layer manner from top, basically preferably, and in one direction. It should not come from different directions. Okay. What is the logic behind this? If we are having that from one direction, in that case, first of all it is from the top, so that we can use the gravity, okay. And otherwise what we have to do is we have to use some kind of assistance for the part to flow, because if it is horizontal feed track, as you have seen, in the horizontal position of the horizontal feed track, it will be very difficult for the parts to move to the workstation until unless there are other parts pushing on the top of this, okay, above these parts. So, vertical delivery feed tracks will always be advantageous because there is a gravity which is working. So, that is one reason why we should take the parts from the top, and different direction will give you the positioning of the bowl feeder and the feed track in different directions. So, the space cannot be utilized properly. So, because of these two reasons, we are saying that assembly should be in a sandwich manner, and preferably the part should be coming from one direction and preferably from the top. Now, the precedence diagram as it is shown here, I will explain it to you what is it. This tells us, precedence diagram tells us the ways, the number of ways an assembly can be made. To give you that example, take this very simple assembly. This assembly is simple because there are only few parts, but as you understand that production machines or production assemblies, they can have thousands or 10,000s of parts, okay, and the way to make the assembly, the order of assembly, this is very important, because in that case the time taken for the assembly will be minimized. So, precedence diagram exactly tells us how many ways we can make that assembly. So, in this case, for example, we say that we have a base. After that, next we will mount the ground pin and the live pin. After that, we will make the fuse clip. After that, we will make the screws, then the fuse on top, then the neutral pin, then this screw, then the cord grip, and from here the cord grip screws, then the cover and the screws. So, this is the sequence of assembly that you can make. However, in this sequence we can have some alteration. So, what are those alterations that could be done? It is shown by the precedence diagram that we will discuss in the next discussion. Thank you very much.
I am A.K. Sharma and I am professor of sociology at IIT Kanpur. The question I am going to address is what is urbanization? Urbanization is essentially the process of population concentration, which means that if more people start living in a smaller number of places, or if the distribution of population becomes more unequal, like more people living in places like Bombay, Calcutta, Mexico, then we say that the urbanization is taking place. Essentially, it means increase in percentage of population living in areas or localities which are defined as urban. Urbanization is a new phenomenon, of course, a post-industrial phenomenon. About 200 years ago, hardly 5% population of the world lived in urban areas, and today more than 50% population of the world is living in urban areas or localities which are classified as urban. You will be happy to know that according to 2011 census of India, in our own country for the first time, increase in the urban population has been greater than the increase in the rural population, though India is not so urban as the developed countries, and about 31% population of India only is living in urban areas. We can believe that in 10 years, 20 years, 30 years time, India will also be more urban, at least more urban than what it is. It may not be 80%, but certainly it will be 35% or 40%. Now, how is this urban locality defined? Because this definition of locality as urban or rural is crucial to measure level of urbanization. I will give you definition of our own country. In Indian census, an urban locality is defined in two ways. There are statutory towns and there are census towns. All places with municipality, municipal corporation, cantonment or notified town area committees are called urban. This is statutory definition. According to demographic definition, there are three main criteria. If a locality has more than 5,000 people, or 75% of male labor force is engaged in non-agricultural activities, or the density of population is 400 per square kilometer or 1000 per square mile, then we say that the locality may be classified as urban. There are many other additions to this definition. Now we have the concept of urban agglomeration and many other things, but essentially this is how urban population is defined in India. And as I said that urbanization is associated with economic development and industrialization, same is the case with India. About 100 years ago in India only 11% people were living in urban areas, today 31% are living in urban areas. And this is obviously linked with economic development of the country, growth of per capita income and industrialization. I remember that in one 5-year plan it was mentioned that today this urban population can grow by way of natural increase of births minus deaths in the urban areas itself or through rural to urban migration. Today nearly 60% contribution to growth of urban population is due to rural to urban migration, and this is going to increase. This is essentially what urbanization means. Urbanization means growth of population in localities defined as urban in relation to population of localities defined as rural, and I have given you Indian definition. Thank you very much.
Swayam Prabha, Digital India, Educated India.
Hello everyone, good morning to all of you. We are back with the week number 8 where we are going to talk about the measurement of a parameter which is very common to all of you, something you have heard from very early school days, which is pressure. Pressure is a term which probably you can relate to several day-to-day common phenomenon or common activities, and of course we are not talking about the mental stress or mental pressure, we are talking about only the thermodynamic quantity, the pressure. But still there are several situations where you have been introduced to this particular term or you have made use of the term pressure. Most common example can be the day-to-day weather report which you keep on hearing on the televisions or on the radios, where along with the local temperature and humidity they also quite often mention about the pressure, or may not be explicitly mentioning about the term pressure, but very commonly you can keep on hearing the terms like low pressure or depression formed in some part of the country or some part of the ocean, thereby leading to the formation of some local disturbances, maybe a cyclone, etc. And we are going to talk about that very parameter in this particular week. Now, last couple of weeks were a bit light, where the total content of the week was a bit lesser, as we discussed about the measurement of stress and strain and also the measurement of force and torque in the previous week. But this one probably having a bit more content, but I hope most of that part will already be known to you. I shall just be trying to emphasize on some of the associated concepts and maybe introducing a few more. So, the first question that we have to answer is, what is pressure? Now, what answer is coming to your mind? What is pressure? We all know that pressure is force per unit area, but which area should we be talking about, or which is the direction of force that we are talking about? That of course we have to be very careful of before we can go for the measurement of the pressure. Now, if we go to the molecular level itself, then let us consider a container like this filled with certain gas molecules. Now, as per the property of the molecules, unless they are at the absolute zero temperature, because of their internal energies, they will keep on moving around quite randomly throughout the entire container, thereby colliding with themselves and also colliding with the walls of the container. And as they are colliding with the walls, if we assume even elastic collision also, there will be a change in the momentum of this. During the collision part, there may be a change in the velocity, and so that during the collision they will be transferring a part of their momentum to the wall, or it may be possible that there may be a net change in the value of this velocity, that is the magnitude of v1 and v2 may not exactly be same. Quite often the exit velocity actually is lower than the incoming velocity, thereby causing a net reduction in the momentum of the molecule itself, and that amount of momentum will be transferred to the associated wall or to the adjacent wall. Now, the rate of transfer of this particular momentum will definitely lead to some kind of force. So, this particular molecule, as it is striking the wall at this particular position, it is putting some kind of force to this. This way all the molecules are striking the adjacent walls and each of them are putting some kind of force. So, if we combine the cumulative effect of all this force or momentum transfer of all these molecules on a particular wall, then the force that we get, that is what is associated with the pressure, or the force per unit that area is the pressure. Means if we pick up this particular vertical surface, then whatever momentum that has been transferred by all the molecules which are hitting this particular surface will lead to a certain force, and now if we divide that total force by this particular area, then we get the pressure which is acting on this particular surface. This pressure force or the force associated with pressure always has to be normal to the concerned surface, and therefore depending upon the contour of the surface, the direction of force may keep on changing. Like the examples shown here, particularly interesting can be the aerofoil one. As the surface profile keeps on changing, the direction of the corresponding pressure force also will keep on changing, because at every point the direction of the pressure force has to be normal to the concerned surface. Like if we pick up this particular point, this is the direction of the force, whereas if we pick up this particular portion of the surface, the direction is this particular one. So, depending on the orientation, the direction of the pressure force will also keep on changing, and that is why while evaluating the magnitude of this pressure, we have to be very careful about which area we are talking about. But what about stress then? Because just 1 week back we are talking about the measurement of stress and strain, and you know that stress is also force per unit area. Then what is the difference between pressure and stress? Both are force per unit area, and then whatever way we have measured stress, the same way we can measure pressure, or even more fundamentally, why you need a separate quantity at all? We could have just continued with stress itself instead of introducing any new parameter in the form of pressure. Now, let us say this is one particular surface and a force is acting at this particular point of the surface, or let me draw it in a better way. Say this is a force acting at a particular point on this particular surface, say the magnitude of the force is F. Now, if we divide this particular force, or if we distribute it into two components, one normal to the wall, something like this, let us say let us call this particular as Fn, and the other tangential to the wall, let us say this is Ft. Then of course this is a vector addition, so the total force F is a combination of this tangential component and the normal component. Now if we take an unit area around this point of application of this force such that this area is A, then Ft by A, the magnitude will lead to, let us say we write it as sigma t, and similarly if n, the normal component of force divided by area, let us write it as sigma n. These two are the two stresses that is acting at this particular point. This one is the tangential stress, this one is the normal stress. Then what about pressure? Actually none of these two are stresses. What we have written here are force per unit area, and but this particular part is not correct, because stress refers not to these external forces which are acting on the surface, rather stress refers to an internal force which is originated when the body is getting deformed and is trying to resist that deformation. That means what I am trying to mean that because of the action of this particular force F, there may be some deformation that is happening in the body. Now because of its own structure, the body is trying to resist this deformation, and therefore following Newton's third law of motion, it will also produce a force of equal and opposite magnitude, another force F, as an internal mechanism or as a part of the internal mechanism. Now if we divide these internal resistive forces into two components, what will be the components? The normal one will be Fn itself and tangential one will be Ft itself. You can say that the one which is opposing this normal component of the imposed force is this one, whereas the one which is opposing this tangential component of the imposed force is this one, and they have to be equal to their corresponding external counterpart. Now the force per unit area corresponding to these internal forces are the stresses. So the magnitude of the tangential stress sigma t and normal stress sigma n, that remains the same, because this Ft and Fn are same, and also we are talking about the same area, but the difference is in form of senses. Here this Ft and Fn are not the component of this imposed force F, rather they are component of this internally generated resistive force F. So stresses are internal force or part or result of internal force which are trying to resist the deformation of the body, whereas pressure is purely an external one. And if we continue with this particular diagram, then pressure actually is the normal component of the imposed force, that is pressure is the normal component of this imposed force Fn per unit area, that is this particular one, magnitude of pressure will be this particular one itself. However, here we are not talking about the internal component, rather we are talking about the external part. So in magnitude, purely from magnitude wise, this normal component and pressure, their magnitudes will be equal to each other. However, when this normal component sigma n, normal stress I should say, refers to this particular internally normal component of this internal generated force, P refers to the normal component of this externally imposed force. So though their magnitudes are different, their senses are their magnitudes are the same, their senses are completely different. The stress refers to the internal forces or corresponds to the internal forces, whereas pressure refers to the normal component of this externally imposed force. And another important factor is that pressure or rather the force corresponding to pressure will always point towards inward, that is it is always compressive in nature, always pointing into the surface for this. So if we try to compare force and pressure, then of course just as I mentioned, pressure refers to the external force, whereas stress is generated because of the internal forces developed within the body to resist any kind of deformation. Pressure is always compressive in nature, that is if I just clean up this particular mess a bit, then if the force is acting this way, that is into the surface, then pressure will correspond to its normal counterpart. However, if the force is say acting outwards and its normal counterpart is this Fn, then this one will not correspond to pressure, rather its opposite. Like if we can draw something like this Fn bar, let us say I am these are all vectors, I am not putting the arrow. So pressure will correspond to this Fn bar. It is always compressive in nature, always pointing into the surface. That is not related to stress. Stress can be compressive or tensile or maybe shear. Shear actually referring to this tangential part or the like just shown in the diagram. We can have tensional stress where the force are actually pointing outward. We can have compressive stress, and we can also have shear stress where the force is acting parallel to the surface. But pressure is only related to this compressional part. Then pressure forces are always normal to the surface, but as can seen from the diagram, stress can be at any angle. Like we can see here. Here we are having a cube and forces acting parallel to each of them. Now if we break them, here also the surfaces are, in the second case also surfaces are parallel to each other and the forces acting normal to the surface. However, if we look at this particular case, here the force is acting, here again the force is acting normal to the surface, but it is not an orthogonal direction, because here we are talking about the surface which is not parallel to any of the orthogonal axes. So the pressure force will always be normal to the surface, and magnitude is direction independent, or to be more specific, pressure is a scalar quantity. Of course, force associated with pressure is a vector like any force, but pressure itself is a scalar quantity, because at a particular point the magnitude of pressure remains the same coming from all possible directions, and that is why pressure is a scalar quantity which does not have any direction dependency. However, stress, it is not a vector, it is a its magnitude can be unequal, that is at a different, at the same point stress in different direction can be different, and that is why it is not a vector, it is actually a second order tensor, whereas pressure is a scalar which can also be viewed as a zeroth order tensor. And now pressure can be measured directly, which we are going to learn in this course. But what about stress? We have already learned some basic mechanisms of stress measurement. Stress can't be measured directly because stress is only internal to the system. What we can measure is generally strain, that is deformation of a body per unit initial length scale. And now the deformation or the strain can be related to the stress through Young's modulus and maybe Poisson's ratio to get an indirect measurement of the stress. But there is no way you can get a direct measurement of the stress, which is possible in case of pressure. Pressure we can have a direct measurement, and there are infinite number of devices. There are lots and lots of different kinds of mechanisms by virtue of which we can directly measure pressure. Now that direction independency is given by the Pascal's law, which all of you have definitely learned at the school, that is at a particular point on a liquid or maybe on a gas, also on a fluid, if we apply pressure, then force is transmitted equally in all possible direction, which essentially proves that pressure is a scalar quantity, and that also has lots of applications in practice. Like a very simple situations, here you are having a sphere. Just consider the sphere to be extremely small so that the pressure remains uniform throughout the entire body of the sphere, and now there are 4 outlets, each having a different area. Then the force that is acting at this particular surface, if that force is F, then corresponding pressure will be force divided by the area small a. This is the pressure which is acting at point A, or force you are putting at point A. Now at point B, that is this particular point, what will be the force then? Then FB, pressure remaining the same, should be equal to P into the area, where area is twice of A, and so if we put back the expression, it will be twice of FA. So it is, area is double, accordingly the total force is also double because pressure remains the same. Similarly at D, here area is 4 times, so the force which is acting at D is again the pressure into the area of D, that which is 4 of A, and that is, it is 4 times of force which is acting at point A, which is this particular one. One possible application, you must have seen the application of hydraulic jacks, where you have 2 connected cylinders filled with certain fluid, generally liquid. On one of the cylinders which is having a smaller diameter or smaller cross section area, we are putting some kind of force like this, and that gets transmitted through the fluid body into the other cylinder, into the piston on the other cylinder, where the area is much larger, accordingly there is a magnification of the force despite pressure remaining the same, and that we can use for doing much heavier work, just like lifting a car. So at this particular point in this particular cylinder, the pressure which is acting P1 will be equal to F1 divided by A1, where F1 is the force that you have imposed initially, and pressure remaining the same, P1 will be equal to P2. So the force which is acting on the car or on the second piston will be equal to P2 into the area of the second one, which is A2, and P2 equal to P1, and putting the expression for P1 we have F1 into A2 by A1, or if we write F2 by F1 is equal to A2 by A1. So if A2 is 10 times of A1, there will be 10 times magnification of the force. So this comes from the Pascal's law, which you already know, and there can be several practical applications of this. But now we need to classify pressure into a few categories before we go for the measurement, because we need to be very sure which pressure we are going to talk about. This is the most common kind of definition or classification of pressure. Generally, whenever we are trying to define the value of pressure, we do that with respect to certain reference length scale, and the most common reference can be the atmosphere itself, or I should say the atmospheric pressure. Atmospheric pressure is the most common reference that we generally take. Now, if this is the point where we want to measure the pressure, then we can do in two ways. One, we can define the pressure at this particular point with respect to the atmospheric pressure or with respect to our reference, or we can define it with respect to a reference where pressure, absolute pressure is, or rather I should say the pressure is really 0 or truly 0. Now, when we are doing this with respect to the atmospheric pressure, then we call that gauge pressure. Here the spelling, both this particular spelling and this particular spelling, both are applicable depending upon which language system you are using. I shall be sticking to my definition like this. However, when you are evaluating the magnitude of pressure with respect to absolute 0 pressure, then we call it absolute pressure. So if PA refers to absolute pressure and PG refers to a gauge pressure of the same location, then what will be the relation? Absolute pressure will be equal to gauge pressure plus the atmospheric pressure, and therefore once we know the atmospheric pressure value at a particular location, then either gauge pressure or absolute pressure will allow us to calculate the other one. However, if we are talking about a point where the pressure is lower than the atmospheric pressure, then what we should do? There again, like a point here whose absolute pressure is lower than the atmospheric pressure. Of course, we can define the absolute pressure because we are always defining with respect to the absolute 0, and so there will be a positive value of this absolute pressure. However, if we calculate gauge pressure, then gauge pressure will be negative, because here like in the first case our absolute pressure was greater than gauge pressure, because the actual pressure was greater than atmospheric, so gauge pressure was positive, or I should say absolute pressure was greater than atmospheric pressure, accordingly gauge pressure was positive. However, when we are doing this particular case, here the absolute pressure is less than atmospheric pressure, so the gauge pressure is negative. So we can define it either by a negative gauge pressure, or there is an alternate way of doing this, which is the definition of vacuum pressure. Vacuum pressure refers to, vacuum pressure we use, the term vacuum pressure we use only when we are talking about an absolute pressure lower than atmospheric pressure. In that case, this vacuum pressure is defined as P ATM minus P absolute. It recognizes the fact that the absolute value of pressure is lower than atmospheric pressure, so that we get a positive value of this vacuum pressure. Now, if we compare this with the definition of the gauge pressure, then what we are going to get? If we compare this, then from the first definition, absolute pressure will be Pg plus P atmospheric, and from the second definition it will be equal to P atmospheric minus P vacuum, which is gauge pressure is equal to minus of vacuum pressure. Vacuum pressure will be a positive quantity and gauge pressure will be a negative quantity at this particular location where the absolute pressure is lower than the atmospheric pressure. So both gauge and absolute pressures are used. You will find pressure measuring devices, pressure transducers or pressure gauges which are coming in both ways, that is some devices which can give you absolute pressure or some devices which can give you the gauge pressure. Quite commonly you can find gauges where it is clearly specified whether it is measuring the gauge pressure or absolute pressure. What is the unit of pressure measurement, can you say? Of course, the most common SI unit is force per unit area, that is Newton per meter square, which is called Pascal. But 1 Pascal being extremely small quantity, quite often we deal with kilopascal, which is 10 to the power 3 Pascal, or megapascal, which is 10 to the power 5 Pascal. But one unit which is very common in practical use for industrial application, that is bar. 1 bar refers to 10 to the power 5 Pascal, that is 100 kilopascal or 0.1 megapascal. Bar is generally a very well used, probably the most well used value of, or I should say the unit of pressure that we commonly use in engineering. Now these are in SI units, but we can also have British units. Several pressure measuring devices you will find where the measurement is given in terms of British unit. Here the most common unit is PSI. PSI refers to pound per square inch. That is, it refers to a force of 1 pound weight, that is the weight of a body having a mass of 1 pound divided by the area of a 1 inch square, or a square having side of 1 inch. Now what is the conversion factor between the two? We can easily put the relation between kg and pound and meter and inch, and you will get that 1 bar is equal to 14.0538 psi. So this is a very common relation. You will quite often find that in some laboratories, maybe at your college or universities, or even when you are going to some industry for your professional purpose, you will find the pressure measuring devices are given with unit of PSIA or PSIG. Don't get confused, their unit actually is PSI, but this A or G refers to, if A is there, then it is giving you the absolute pressure, whereas if G is there, it is giving you the gauge pressure. You have to add the atmospheric pressure to the second case to get the absolute value. Another very common, I should not say it's commonly used, but another possible unit of pressure that is generally used for very low pressure, like when you are talking about a point whose pressure is somewhere very close to the absolute zero, well below the atmospheric pressure. There, if we go for a vacuum pressure or gauge pressure kind of measurement, there may be lots of errors, because because we have to understand that atmospheric pressure itself is not a constant. At sea level, the standard atmospheric pressure 1 atm, atm is also commonly used as a unit for pressure, is given as 1.01325 bar. That is slightly above 1 bar, and that is the reason of having bar as such important unit of pressure. Now 1 atmospheric pressure is not 1 bar, but slightly greater than this. But this is that pressure value at sea level. This is the normal atmospheric pressure, but at different locations on the planet, the value of pressure can keep on changing. Even at the same location also, the value of pressure may fluctuate depending upon the weather condition, and therefore when you are talking about such low pressure levels, then small fluctuation in the atmospheric pressure may lead to significant amount of error in the absolute pressure value at this. In that case, we sometimes use another unit which is called 1 torr, TORR. 1 torr is extremely small value. Instead of writing 1 torr, I should write that 1 bar is equal to 750.062 torr. You don't need to remember this particular conversion factor. 1 bar is about 750.062 torr. There is another quite commonly used unit of pressure which is in terms of mercury coulomb, but I shall be coming back to that shortly afterwards. common units of pressure can be either in terms of bar or kilopascal, or in terms of PSIs, sometimes in terms of atmosphere, and if you are talking about very low pressure, we may also have to deal with this torr. And the one which I shall be talking later on, that generally is given as millimeter of mercury column, which we shall be discussing very shortly, and that can also be related to torr or bar or PSI. Another classification of pressure that is very important in fluid mechanic measurement is the terms static and dynamic pressure. Now, just consider the picture that is shown here. Here we have a channel through which some liquid is flowing. Actually, I should not say liquid, some fluid is flowing. It can be liquid or can be gaseous, but effect is more pronounced in case of liquids, and actually effect can be quite pronounced in case of gases also, when this value v, the velocity is high. Now, if we are measuring pressure at this particular location by using some kind of tapping which is parallel to the flow or which is normal to the flow direction, that is fluid is allowed to flow in its normal course without affecting the fluid velocities, then it will give you a certain pressure value, and this pressure is known as the static pressure. However, if we mount the pressure measuring device this way, then the fluid elements which are flowing in this direction, as they come in contact with the tip of this, then at this particular position, to satisfy the no slip boundary condition, its velocity has to become 0, because it is in contact with the stationary surface now, and so its velocity will become 0. Now, as the velocity is becoming 0, then what is happening? It is losing all the kinetic energies, and as it is losing the kinetic energy, this entire kinetic energy gets converted to pressure. Thereby, the pressure measurement that we get at this particular point, this measurement will be greater than this particular value, because in the second case the kinetic energy also gets converted to pressure, and therefore this kinetic head gets added to the static pressure to give you a higher value of pressure, which is known as the stagnation pressure. Stagnation refers to the stagnation of the fluid at this particular point, also called the stagnation point. Now, let us clean up the diagram. Let us say this particular point is 1 and this particular point is 2. Here the 2 refers to actually the stagnation point. Now, if we apply Bernoulli's equation at these two particular point, or maybe one plane through 1, another plane through this stagnation point, the one, let me be more precise, this one refers to the point where we are measuring the static pressure. So, let us say here the pressure is P, here the pressure is P naught. Then if we apply Bernoulli's equation, then at point 1 we can write P1 plus half rho V square, rho being the density of the fluid, plus Z1, Z being the elevation of location 1 or this point 1 with respect to certain datum, is equal to P2, which is equal, let me just write P2 now, plus velocity is 0 plus Z2. Now, if Z1 and Z2 are equal to each other, which is frequently the case, we can neglect that. So, P1 becomes P plus half rho V square is equal to P naught at the stagnation point. So, we are seeing that this P naught is higher than the pressure at point number 1. So, this P is the static pressure, P naught is called the stagnation pressure, and this is often called the dynamic pressure, that is the kinetic head or the pressure gained because of the conversion of kinetic energy to pressure energy. This is called the dynamic pressure. In fluid mechanics, we can easily measure both the static pressure and the stagnation pressure. However, dynamic pressure is not that easily, we can't evaluate dynamic pressure directly, rather we go for both static and stagnation pressure measurement, and from there we can calculate the dynamic pressure as their difference. In fact, this also provides a very easy way of calculating the velocity of the fluid, because what we can easily see that V square will be equal to 2 by rho into P naught minus P, or V is equal to 2 by rho into P naught minus P. So, if for a flowing stream where the density rho remains constant, if we can get a measurement of the static and stagnation pressure, then using this very simple mathematical formula we can get the value of the velocity of the fluid, which is one of the very important way of fluid velocity measurement using a device called pitot tube. We shall be talking about this later on. Now let us come to the, once we know this kind of classifications, that is absolute on gauge pressure and also the static and dynamic pressure, let us talk about a few instruments of pressure measurement. And the first one that we have is dead weight pressure tester. It is a very simple mechanism. However, this is generally used more for calibration of the gauges, not for common pressure measurements. That is why they are generally available either in the standard laboratories or places which are used for manufacturing of pressure gauges. Now here we have a chamber generally filled with certain liquid, certain heavy density fluid, and one side of this chamber is connected to this plunger pump. By controlling this plunger pump, by operating this one, we can change the pressure inside this chamber. Now on top of this chamber we have a piston and we have standard weights, or rather on top of the piston we have a platform where we can put in some weights. On the other side of the piston we have the gauge which is connected, and this is the gauge which is going to be calibrated using this test facility. Now initially the chamber is filled with certain fluid and it is initially at some pressure. We can control the pressure of this in two ways, one by operating the plunger pump and also by changing the weight on top of the piston. So what we do, initially put certain kind of force or standard weights on the piston. So let us say we want to get a measurement of 10 kg force, that is 10 kg force refers to 10 into 9.81 Newton, that is 98.1 Newton. So what we shall be doing, we shall be taking standard weight of 10 kg and that will be put on top of the piston. So the initial pressure may be quite high compared to the initial weight of this, the weight put by this piston may be quite high now for the fluid inside the chamber. So we start the plunger pump and we keep on operating the plunger pump, thereby increasing the fluid pressure by adding more and more mass of fluid inside the chamber till the moment this piston and weight assembly starts to float. It starts to float means now it has reached some kind of pressure balance, that is the pressure of fluid inside this is sufficient, just sufficient to balance the weight of this standard weight. Then whatever value, whatever reading the gauge is showing, that should be equal to this 98.1 Newton, that is the gauge may be pointing to a location somewhere here. So we can put the mark of 98.1 Newton. Now we can change the weight on top of the piston and thereby setting up a new value and accordingly modify this. Like suppose in this next case we have set up force of 60 Newton. So once the system becomes stable, then wherever the pointer is pointing, that has to be 60 Newton. This way we can keep on calibrating our pressure gauges and also we can recalibrate any existing instrument. This is a very standard assembly and we can by precise control of the plunger pump and the weight and also this gauge calibration procedure, we can get extremely accurate measurement, something in the range of maybe 1 in 1000 ppm, that is in every 1000 parts there may be error of just one part. This level of accuracy we can easily reach with this. However, there are a few concerns that or considerations that we have to be mindful of, like the friction which may be acting between the piston and cylinder. As the piston starts to float or it starts to move because of the increase in the pressure inside the chamber, some energy may be lost because of the friction. There will be viscous stresses, of course, because we are talking about a fluid which is which starts to move inside the chamber because of the action of the plunger pump, and viscous stresses may get developed. Significant viscous stresses may get developed inside the chamber. There can be thermal effects because of the operation of the pump. Energy gets added to the fluid inside the chamber itself, and that may change the density of the fluid and also other associated properties. Buoyancy is another factor. As we are interested to get the piston floating into the fluid, buoyancy is definitely an important factor. local gravity also may keep on varying. So, where you are doing this experiment, that also matters. Therefore, for every different location and for every scenario, it is important to calibrate the tester itself before we can start calibrating pressure gauges. So, deadweight pressure tester is more for calibration purpose, but similarly balancing the weight of some external thing to get the value of pressure is used in another very common kind of device, where instead of using solid we keep on using fluid, or to be more specific we can keep on using liquid columns, and something which falls under this manometry. You definitely have heard about the term manometers, and that is what we are going to talk about here. In manometers we have a liquid column to balance the force. Just look at this. This is there are generally two broad kinds of manometers. This is the first one, which is called the well type manometer. The other one is a U-tube manometer. In well type manometer we have one big chamber or shell and connected with a small diameter tube. So, both are connected. This is the connection here, so that fluid can keep on moving in and out of the tank and also the cylinder. Let us say the tank is having a diameter of A1, sorry, the cross section area of A1, and the cylinder is having a cross section area of A2. This datum is the initial level of fluid in both tank and the cylinder when both are at equal pressure. Now, we have imposed a pressure P1 on the tank and a pressure P2 on the cylinder. Because of that, if P2 is lower than P1, then there will be a reduction in the fluid level on tank 1 or on the big tank, thereby displacing some fluid from the big tank into the cylinder and leading to the formation of an water column, or I should not say water, it is fluid column, generally liquid column. So, if we now write a pressure balance we can write with respect to which point? Let us say this is the level that we pick up to write a pressure balance equation. So, what is the pressure that is acting on the tank side? The pressure will be equal to P1 itself. Similarly, what is the pressure that is acting on the cylinder side? Cylinder side pressure will be P2 plus the pressure corresponding to the weight of this liquid column. Now, how much is the weight of the liquid column? Weight of the liquid column will be, let us say rho is the density of this liquid into g is the gravity into volume of this liquid column will be A2 into H plus delta H. This is the volume of the liquid column. This divided by the cross section area of the tube. This is the pressure, or we can write P1 minus P2 is equal to this gamma into H plus delta H, where gamma is rho into G. Quite commonly we use a subscript m to denote this is the density of the fluid inside the manometer or the manometric fluid. Similarly, gamma m is the rho m into G product. Now, this delta H can be related to this area is A1 and A2. How much is the displacement of fluid or change in volume of fluid in tank 1? This is the initial fluid level, this is the final fluid level in tank. There is a difference of height delta H, and we also know the cross section area. So, the change in fluid volume in tank 1 or reduction in fluid volume is just A1 into delta H, and that fluid where it has gone, this is we are talking about a liquid which is incompressible. So, the volume has to be conserved, and if we assume the volume to be conserved, then whatever is the reduction in the volume in tank, that has to be the gain in volume in the cylinder. Now, how much is the change in volume? The cross section area is A2 and there is change of height H. You have to mindful that this was the initial level, this is the final level. So, from there we can say that delta H is equal to A2 upon A1 into H. If we take it back to the previous equation, P1 minus P2 is equal to gamma n into H plus A2 upon A1 into H, or 1 plus 2 upon A1 into gamma m into H. So, by choosing this ratio A2 by A1 at the design level itself and also the density value gamma m, or I should say the density value rho m or the value of gamma m, we can relate even significantly large pressure levels P1 to in terms of H. How we can define a sensitivity of this instrument? Do you remember how we defined sensitivity in the very first week of this? Sensitivity refers to the change in output with respect to the change in input. Now, what is output here? Your output is this change in the liquid column height H, and how much is your input? That is the pressure difference P1 minus P2. So, how much is that? That is equal to 1 by 1 plus 2 by A1 into gamma m. So, this is the sensitivity of the instrument. If this A2 is extremely small compared to A1, that is A2 is negligibly small compared to A1, in that case P1 minus P2 is equal to, or I should say is nearly equal to gamma m into H, that is manometric fluid density into G into H. So, assuming the fluid density to remain constant and gravity can, this G, gravitational acceleration, can also be assumed to be constant, then we are having P1 minus P2 to be a linear function of H, and therefore, on this particular cylinder surface we can also put proper scale or length scale, which can be directly calibrated in terms of the pressure difference. So, this well type manometer is the first kind of manometer, a very simple instrument, but we can get quite accurate measurement if we just by knowing the value of this gamma m and also this ratio of A2 upon A1, which generally is provided by the manufacturer itself. So, well type manometer, however, there is one problem. This kind of things, or actually any manometer, they are not that much suitable for dynamic pressure measurement, as long as we are looking, because they need sufficient some amount of time for this liquid column to get developed and get settled at a particular elevation. And therefore, if we are looking for too frequent change in the value of pressure, we may not be able to capture the corresponding value of H properly. That is why manometers are excellent devices as long as we are looking for static pressure measurement, and also we have to be careful of the range of pressure. They are generally not suitable for very large value of this P1 minus P2, whatever may be the choice for rho m or the ratio A2 by A1. As long as we are working with low to moderate pressure difference levels or pressure levels, and there is more or less static or steady state condition, manometers are very good devices for pressure measurement. However, if you are looking for either measurement of very large pressure or also very small pressure difference between this P1 and P2, or also if you are looking for very frequent changes in pressure, we may have to look for different devices. But now think about the situation where your P1 is equal to the atmospheric pressure and P2 is equal to 0. How can we have P2 equal to 0? Let us just close the top of this cylinder, and the area, that is this area on top of the liquid column, let us evacuate this using some vacuum pump or etc. Then what will be your relation? Going back to this particular equation, your P atmospheric will be equal to 1 plus A2 upon A1 into gamma m into H, or if A2 is extremely small compared to A1, then this just becomes gamma m into H, that is rho m into G into H. So, we can get a measurement of the atmospheric pressure, and that is what we do in case of a barometer, which is just a modification of this well type manometer. Here we have just one liquid pool which is open to atmosphere, and a small diameter liquid column cylinder, which is generally a capillary tube, and as the atmospheric pressure gets applied on this, if we take a pressure balance at this particular location, then the atmospheric pressure which is acting at this particular point has to be balanced by this particular liquid column. This particular liquid column or weight of this liquid column must balance the atmospheric pressure which is acting on the free surface of the liquid pool. Commonly mercury is the choice as the liquid, and accordingly here if we compare the areas, generally A2 is refers to a capillary tube which is having an extremely small diameter A2 really is extremely small compared to A1, and we comfortably can equate this one to be equal to rho mg into H being the column of this mercury inside this. Mind you, we can have liquids of any density or any kind of liquid in the column, but one advantage we get is this H is equal to rho m into g, that is H is inversely proportional to the rho to this manometric fluid density. Therefore, if we are using a fluid having low density, something like water is not very low density, but compared to mercury it is extremely small, then this value of H will be much larger. Density of mercury is quite high, 13.6 times more than water under normal atmospheric condition, and therefore corresponding value of H is also 13 to 14 times lesser compared to what we would have got with water itself. Now barometers are very standard devices used everywhere in the world and for ages, and also this simple relation gives us another way of defining a pressure scale, which I have mentioned a few slides back. Now standard atmospheric pressure, as I have mentioned, P ATM is equal to 1.01325 bar, or maybe if we write in terms of pascals, so this into 10 to the power 5 Pascal. Rho m for mercury is 13560 kg per meter cube. Small g can be taken as 9.81 meter per second square. So if we combine this value, your H comes something like 76.17 centimeter. That is, under standard atmospheric condition, the height of this mercury column will be about 76 centimeter, and that provides another scale for pressure where we can easily relate one atmospheric pressure to this height of height of mercury column, or as a matter of fact a column of any liquid. So quite frequently we take, as a normal conversion, we take 1 atmosphere as 76 centimeter or 760 millimeter of mercury, and as I mentioned earlier about torr, 1 torr is actually 1 millimeter of mercury. Therefore, this is equal to 760 torr. So liquid column height can also be a quite frequently used pressure unit, which we can instead of mercury we can use any other fluids also and easily get a conversion. Now well type manometer is one of them, but before I move on to the next one, we have to be careful that in this evacuated portion, perfect evacuation is never possible in practice. So some amount of mercury vapor may remain there. However, under normal atmospheric condition or I should say normal temperatures like 20 to 30 degrees Celsius, which is the normal atmospheric temperature, the vapor pressure of mercury is extremely small, negligibly small. So we can easily carry on with this relation. However, if we are talking about significant value of this vapor pressure, then this relation needs to be modified. In that case, we have to write this one as P ATM minus P the vapor pressure of mercury, or whatever fluid you are using in that so called evacuated portion should be equal to gamma m into G, and this should be the correct relation. So that correction, if we are looking for extremely highly or extremely accurate value of this atmospheric pressure, then this vapor pressure correction must be considered. So the next kind of manometer that we get, the other variation, where we do not have a liquid pool, rather we just have one tube which is bent in the form of an U. One side of the tube, or rather both the arms, can be connected to different locations. We can also keep one connected to the location where we want to measure the pressure, other being open to the atmosphere. Accordingly, we get some kind of difference in the fluid column level, and that difference can directly be related in terms of a scale like shown in diagram. The scale can be calibrated like this, height H can be directly calibrated in terms of any unit of pressure, bar or psi or mercury column, whatever we want, and accordingly we can get a pressure measurement. So, if we take say this is the level along which we want to measure, get a force balance, let us say rho W is the density of the working fluid which is connected to this pressure P1, and rho M is the density of the mercury manometric fluid. M may not be necessarily mercury, it can be any other manometric fluid also. And then on top of this, from this particular elevation to this particular position, let us say this distance is y, and this to this distance is x. We can have some other fluid connected to this portion also. Let us say this fluid is having a density of rho f. Then if we take a pressure or balance or force balance at this cross section BB, then at the left hand side we have P1 plus rho W into H plus Y into G is equal to P2 plus rho F G into X plus rho M into H into or G into H, or P1 minus P2 is equal to rho M G H plus rho F G X minus rho W into H plus Y into G, or let me be consistent, G into H plus Y. And quite often we would like to represent this one as divided by rho M into G, so that we can convert this one to some kind of length scale. Then it just becomes H plus rho F by rho M into X minus rho W by rho M into H plus Y. In most of the practical cases, this P2 remains to be the atmospheric pressure and rho F become density of air, and in most situations, particularly if you are going for a mercury kind of fluid, you may have rho M to be significantly larger than both rho F and rho W. In that case, P1 minus P2 upon rho M into G will nearly be equal to just H. So, just the measurement of H itself is going to give you the value of the pressure that you are looking for. However, if the value of rho W or rho F is significant, then we have to consider them during the calculation itself, which is not a very difficult one. Once you know all these density values, you can easily calculate the value of the pressure difference between P1 and P2. Or another important thing is that this one, particularly when this P2 is atmospheric pressure, you can directly get a measurement of the gauge pressure using this manometer, because P1 minus P2 is the one that you are evaluating, which is precisely the idea of gauge pressure. Means what you are getting is P1 minus P atmosphere, that is P1 gauge or P gauge pressure at location 1. So, U-tube manometer can easily be used for calculation of gauge pressure. However, if we are looking for an absolute pressure measurement, then P2 should be equal to 0 if we want absolute pressure measurement. Quite often we use this kind of manometer for differential reading as well. Like think about, we have a flow stream through which some fluid is flowing in one location to other, and we want to get the pressure difference between these two locations. So, this is our location 1, this is our location 2. Then we can easily connect a manometer between these two locations and accordingly get a reading. Like it may be possible that this is the manometric fluid which is showing an elevation difference of H, and on top of the fluid we have this X that is left with. Now, if we across this particular section, say BB, if we take a force balance again, rho M is the density of the manometric fluid and rho W is the density of the working fluid. Then on the left hand side you will be having very similar way, P1 plus rho W into H plus X into G, and on the right hand side you will be having P2 plus rho W G into X plus rho M G into H. From there you can get P1 minus P2, which is the difference in pressure between location 1 and 2. This kind of manometers are called differential U-tube manometers or just differential pressure manometers. U-tube manometer can have different kinds of variations. If we here also the same way we can calculate an expression for sensitivity, but that will be quite similar to what we got in case of well types. Now, if we are looking for extremely small pressure difference measurement, that is P1 minus P2, then or if our manometric fluid is having a density lower than the working fluid density, then how we can do it? You can see that the situations that we are talking about here, always the manometric fluid density, that is this rho m, has to be greater than this rho w or rho f. However, if rho m is lesser than this rho w or rho f, then definitely we can't use this, because in that case the working fluid will come down and push this manometric fluid in the upward direction. And in that situation, therefore, what we do is just to invert the manometer in a configuration like this. This is called an inverted U-tube manometer. In case of inverted U-tube manometer, let us say this is your location where you want to measure the pressure. This is your location 1, this is your location 2, and here the manometric fluid is having density lower than the densities of rho 1 and rho 2. If we again take a pressure difference or pressure balance between location 1 and 2, then what we are going to get at point if we take say a pressure balance at this particular location BB, then what will be your pressure on the left hand side? Your pressure will be P1, P1 is the pressure at this particular point, minus there is a column of height H2 of liquid rho 2, so rho 2 G into H2 minus if there is a column of height H1 minus H2 of manometric fluid, so rho m into G into H1 minus H2. What about the right hand side? P2 is the pressure at this particular location, minus there is a column of height H1 of liquid density rho 2 G into H1. So P1 minus P2 will be equal to, in the first case it should have been rho 1, sorry, this. So it should be rho 1 G H2 minus rho 2 G H1 plus rho m G H1 minus H2, and we can separate it out into two components. That is, if we take say the H2 part out, then we shall be having rho 1 minus rho m into G into H2 minus rho 2 minus rho m to G into H1, and now depending upon the value of rho 1, rho 2 and rho m, we can easily calculate the pressure difference between these two locations despite the density of the manometric fluid being lower than the density of both the involved fluid. Quite often in inverted U-tube manometers actually use air as the manometric fluid, and if you are using air as the manometric fluid, then this rho m is negligibly small compared to both rho 1 and rho 2 in most of the practical cases. In that case, your P1 minus P2 will be what? It will be just rho 1 G H2 minus rho 2 G H1, and you can go for the subsequent calculation of the density, or I should say the pressure difference in terms of whatever fluid you can go for. Like if rho 1 is the fluid that you want to scale the pressure difference, then you can write this as P1 minus P2 by rho 1 into G is equal to H2 minus rho 2 by rho 1 into H1. So inverted U-tube manometer is just a variation or inversion of the conventional U-tube manometers, and then we can use very light manometric fluid or at least manometric fluids having density lower than the working fluid density. Now there are two ways we can increase the sensitivity of these manometers, because we know that the sensitivity in manometers is always given in terms of the change in elevation or elevation of the liquid column divided by the pressure difference. And so if we want to increase the sensitivity, somehow we have to increase the elevation of the liquid column, one way of doing this is to change the manometric fluid density, but that may not always be most practicable one, and therefore we can go by just modifying the design itself. We can change the sensitivity of the instrument, or rather increase the sensitivity of the instrument. So, I shall be quickly discussing about two of the methods. One is to use the inclined tube manometer. It is the well type configuration, or quite similar to the well type configuration. You can see here, the instead of having a vertical tube, we have inclined the tube to some angle. This angle is B. Now, this is supposed to be the initial datum level. This is the initial datum. In both well and the inclined tube, the fluid was at this particular level. Now, because pressures P1 and P2 have been imposed on this, which are different to each other, P1 greater than P2, then there is a reduction in the water level, or fluid elevation in the well. So, this is the reduction in the elevation level of fluid, which let us say is delta H. Corresponding to this, there is an increase in the elevation of the fluid. So, let us say this is a datum, this is the final position, and so there is a change of H, elevation H between the two. Then how much is the total net difference in this? So, net difference, if we if we take this as our working section, and if we take a pressure balance, then the same way we can write that on the left hand side your pressure is just P1, on the right hand side your pressure is P2, plus how much is the height of this? Height of this column is rho m g into height is h plus delta h. However, this h plus delta h, actually in this diagram this h is shown as this, let us call this L, where L refers to the length of this column along the tube or in the inclined way. Now, h plus delta h is the total elevation difference between the fluid level. However, L is the length along the inclined tube from this location up to the tip of this. So, what is their relation? So, we are getting a triangle something like this. If we draw the triangle properly, then this is what we are getting. This one is our L, this one is h plus delta h, and what is the intruder angle? The intruder angle between them, this particular angle is given as B. So, this particular angle, let us say this angle is A, and A is 90 degree minus B. So, what is the relation between them? So, h plus delta h divided by L is equal to sine of A, that is cos of B. So, if I put it back here, so it will be equal to P2 plus rho mg into L of cos B, and by changing the value of B, therefore, we can keep on changing the value of L or this particular ratio itself. Definitely the value of L will be much larger compared to the value of h plus delta h, and it will be much easier for us to identify the length of the liquid column in the inclined tube. Even for much smaller value of pressure difference between P1 and P2, we can easily calculate this. The other way of increasing the sensitivity is the use of micromanometer. In case of micromanometer, we are still using an U-tube manometer, but here both the edges or lengths of the tubes are connected to one large dimension tanks or some kind of bulbs, and here we are using a second fluid which is also known as the gauge fluid. Now, see here carefully, here we have three fluids. We have a manometric fluid rho m, which is this shown by this hatched, is the manometric fluid. Then we have a gauge fluid which is shown by these dots, which is having a density rho g, and now we have the working fluid which is just by the white space. Initially this was the level of the fluid, this was the initial level, this was the initial level of the gauge fluid in both the tanks. On top of that we have the working fluid having density rho w, and this was the initial level of the manometric fluid. Now, as soon as we are putting a pressure difference P1 and P2 between the tank, or P1 minus P2, then there is a delta Z amount of reduction in the gauge fluid elevation on the left hand side. Correspondingly, both these tanks are actually having same cross section area. So, a cross section area of capital A. Now, because their areas are same, so there will be the same amount of change in the elevation or increase in the elevation of gauge liquid level in the other thing, other height or other bulb. But because of that, there is a, as the delta Z amount elevation difference is happening in the bulb, there is a much larger change in the height of this gauge liquid column in this, which is given by this y by 2. Correspondingly, there is y by 2 amount of increase in the elevation on the other side of the manometric fluid. So, now along this cross section PQ, if we take a pressure balance, then what we are going to get? On the left hand side we have first P1, which is the pressure which is acting here. Then we have the working fluid of density rho W. So, we have rho W G into how much is the height of this? Height is H plus delta Z. So, H plus delta Z is the height of the working fluid. Then we have the gauge fluid. So, how much is the height for the gauge fluid? It is rho G into G into how much is the height? Its height is, if you see, Z is the height from the initial between the two initial levels, initial level of the manometric fluid and initial level of the gauge fluid. So, let us put Z. There is a reduction in this. So, there is a minus delta Z minus y by 2, oh sorry, there is a plus y by 2. So, this much is the total height. See, from this point to this point it is Z minus this small delta Z, and now this is your y by 2. So, rho G into Z into this particular elevation is on the left hand side. Now, what about the right hand side? On the right hand side we have P2 plus a column of the working fluid rho W G into how much is the height of the working fluid? There is an increase in the height of the gauge fluid by of amount delta Z. So, that much reduction has taken place on the working fluid side. So, that is H minus delta Z. Then we have the column for this gauge fluid. It is rho G into G into how much is the height for this gauge fluid? It is Z plus delta Z minus y by 2, plus we have the manometric fluid rho m into G into how much is the manometric fluid? It is just y. Now, as all the fluids are incompressible in nature, so there is a delta Z amount of reduction in the gauge fluid height in the bulb. So, change in volume is capital A into delta Z, capital A being this area, and then corresponding increase of elevation in the other arm on the left hand side. How much is that? Small is the cross section area into y. This much is the change that has taken place, or I should not say y, actually this is the initial level. So, y by 2 is the change that has taken place. So, delta Z is small a by capital A into y by 2. We can take it back here. So, P1 minus P2 is equal to rho WG into H minus delta Z minus H minus delta Z. So, that corresponds to rho W plus the gauge fluid this is on the left hand side, and we are taking from the on the right hand side we had this is coming plus rho mgy. So, delta Z goes off, that is rho wg into for this was I shouldn't have struck this out, h minus delta Z minus h minus delta Z, actually h goes off. So, 2 delta Z remains, and this 2 delta z can be converted in terms of areas as small a by capital A into y plus for the gauge fluid rho g into z. So, here z goes off, but 2 delta z is there, which again becomes small a by capital A into y minus y plus rho mg into y. And if we now take this g into y as common, which is generally done, what we have? We have rho m on one side plus how much coming from rho g. So, small a by capital A being smaller, we can write this as 1 minus small a by capital A into rho g plus, or it is also negative. So, small a by capital A into rho w. So, we have the expression for this pressure, and when this small a by capital A tends to 0, then we have P1 minus P2 is equal to rho mg y. Okay, sorry, this nearly equals to rho m minus rho g into g into y. When this area of the cross section area of this capillary is extremely small compared to that of the bulb. And now, if the difference between the manometric fluid density and gauge fluid density is smaller, then y will also keep on increasing in proportion. Therefore, by suitable choice or suitably combining this manometric liquid and gauge liquid, we can get much higher sensitivity using this micromanometer, and therefore we can easily use this for very small delta P measurement as well. So, this is the way we can increase the sensitivity of manometer, and overall there are several types of manometers that we have discussed. In the next lecture, we shall be solving a few numerical examples to see the application of these concepts in practical fluid pressure measurement. But so far I would like to complete today's work here. If we just take a quick recap, we have started with the difference between pressure and stress. Then we talked about the concepts of static and dynamic pressures, absolute and gauge pressures. Then we first talked about the deadweight tester, which is generally used for calibration of pressure gauges. Then we talked about manometers, generally two broad level of classification, well type and U-tube manometers. And we have also discussed about the barometers as a variation of the well type one, and the inverted tube manometers, which is actually an inversion of the U-tube manometers. And then we discussed about the sensitivity enhancement of manometers, two different mechanisms. One that is inclined tube manometer, which is generally more relevant to well types, and other is the micromanometer, which is more relevant to the U-tube ones. So just go through these lessons before we start the next lecture, and therefore I would like to sign off from here for today. Thank you very much till the next lecture.
Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the lectures until now, we have studied model analysis of undamped and damped systems. We looked at how to obtain model characteristics of a system from its spatial model. The spatial model will consist of the mass, stiffness and damping matrices of the system.
However, the experimental model analysis is based on analysis of responses or response model of the system. This response model consists of frequency response functions in the frequency domain and impulse response functions in the time domain. So, experimental model analysis basically analyzes these FRFs and IRFs to determine the modal characteristics of the system, that is the natural frequency, mode shapes and damping factors. So, in the later lectures we are going to study how to measure the frequency response functions and impulse response functions and how to analyze them to obtain the modal characteristics. In this and the next lecture we are going to talk about characteristics of FRFs, okay, and in this particular lecture we are going to focus our attention on characteristics of FRFs of a single degree of freedom system. So, we are going to talk about FRF characteristics, right, and focusing attention on single degree of freedom systems. A brief outline of the lecture is as follows. First, we are going to define different types of FRFs, and then we are going to look at how FRFs can be presented graphically. Then we will look at the FRF characteristics of a single degree of freedom system with viscous damping, right, and then we are going to also study the concept of stiffness line, mass lines, and how to identify mass, stiffness and damping of a single degree of freedom system from the FRF. So, the first thing we are going to talk about is FRF types. As we defined earlier, the frequency response function is basically the ratio of the response of the system in the frequency domain and the force applied causing the response in the frequency domain, right. And the response now can be described either by the displacement of the response, velocity of the response or acceleration of the response, and depending upon which parameter is used to define the response, there are three types of FRFs. So, the first is what is called as receptance. This receptance FRF is denoted by often by alpha omega is ratio of the displacement response of the system in the frequency domain and the force applied on the system in the frequency domain, right. Then we have what is called as mobility. This mobility, often represented by y of omega, is ratio of the velocity of the response in the frequency domain, that is v omega, and the force applied in the frequency domain. And because these quantities are defined in the frequency domain, they are at a certain frequency, right. So, each frequency basically refers to a harmonic force acting on the system, and the response corresponding response is also harmonic, and therefore the v of omega can also be written as I omega times the displacement of the response at that frequency, that is I omega into x of omega, right. And therefore we see that I of omega into x of omega upon f of omega can also be written as I of omega into alpha of omega. So, this shows that the mobility is basically related to the receptance of the system, right. So, if we multiply the receptance by I omega, we get mobility. Another FRF which is defined that is called as inertance FRF or accelerance, and this is denoted or maybe we can denote it by A omega, and this is ratio of the acceleration of the response and the force causing that acceleration, both defined in the frequency domain, and the acceleration can be written as I omega times v omega, right, because the motion is harmonic. So, we can do that, and therefore, we can also write the expression as I omega times y of omega. So, if we have the mobility and if we multiply it by I of omega, we get the inertance of the system, and because y of omega is nothing but I of omega into alpha of omega, we can also write this expression as minus omega square alpha of omega. So therefore, we see that the receptance, mobility and inertance, they are related right by these expressions, and if any one of them is available, the other two can be determined. Now there is also something called inverse descriptors of the FRFs, right, referred as inverse FRFs. These inverse FRFs are basically defined as ratio of the force applied on the system in the frequency domain and the response of the system in the frequency domain, right. And again, depending upon how the response is described, whether by displacement, velocity or acceleration, there would be three types of inverse FRFs, and the first one is named as dynamic stiffness. Okay, often denoted by Z of omega, and this is nothing but the ratio of the force applied in the frequency domain and the response in the frequency domain, right. So that is nothing but the dynamic stiffness. Then there is something called impedance, right. This impedance, if we denote it by I omega, is ratio of the force applied on the system in the frequency domain and velocity of the response, right, in the frequency domain. And then we also have what is called as apparent mass, which we can denote by say MA, and it is ratio of force applied on in the frequency domain divided by the acceleration of the response in the frequency domain, right. So these are the three inverse descriptors of the FRFs, and we see that for a single degree of freedom system, the FRFs and their inverse counterparts, they are related by reciprocal relationship. Okay, so for single degree of freedom systems, the FRF and inverse FRFs are related by reciprocal relationship, right. So therefore, if I want to know dynamic stiffness, then I can determine the dynamic stiffness Z omega as reciprocal of the receptance, right. Similarly, if I have the information about the mobility, I can determine the impedance as reciprocal of the mobility. So however, this reciprocal relationship will not be valid for a multi-degree of freedom system. That is something we will study in the next lecture. Okay. Let us now study how we can present the FRFs graphically. So we are going to talk about graphical presentation of FRFs. So the first plot which is widely used to present the FRFs graphically is Bode plot. Okay, and this consists of a magnitude plot, okay, in which the FRF magnitude in decibels is plotted, right, versus plotted against frequency. And FRF magnitude in dB is basically given by 20 log to the base 10 magnitude of the FRF, right, that is the FRF magnitude in dB. And then we have the phase plot, in which the FRF phase in degrees or radians is plotted against frequency, right, and the frequency axis can be either linear frequency axis or logarithmic frequency axis. In model analysis, often we use a linear frequency axis, but however, if the frequency range of measurement is very large, then we may use a logarithmic frequency axis to show the or compress the frequency range and see the variation over that whole range, right, in a single plot. So this FRF magnitude plot may look something like this, that we have this, we are plotting here the magnitude in decibels, and the plot may look something like this. And similarly, we may have the phase plot, which may, for a single degree of freedom system, it may look something like this. That is a phase in degrees. Right. So this is basically the body plot. So advantage of this plot is that from the magnitude plot we are able to see the magnitude over the whole frequency range, that what is how the magnitude of the FRS is varying when the excitation frequency varies, and the phase plot shows the information about the phase at different frequencies. Another plot which is used is absolute magnitude plot. So in this plot, the absolute value of the magnitude or the absolute magnitude is plotted against frequency, right. So this plot may look something like this. So we have the absolute magnitude, that is delta alpha absolute or alpha magnitude, as a function of frequency, and this plot may appear like this. Correct. So for a single degree of freedom system, it may look something like this, and we see that here, because the absolute value magnitude is plotted, the peak magnitude dominates the whole plot, right, and the variation of the FRF over the frequency range or over the frequencies which are away from the resonance region, they are completely eclipsed by this peak in the plot, right. And therefore, if the objective is to just see what are the peaks, what are the frequencies at which the peak response occurs, then this plot can be useful. But if the objective is to see the FRF variation over the whole frequency range, then the body magnitude plot is preferable, right. Another plot which is used is plot of real and imaginary parts, right. So plot of real and imaginary parts versus frequency. So in this case, in the first plot we plot the real part of the FRF as a function of frequency, right, and this plot may look for a single degree of freedom system something like this. And the other plot consists of imaginary part of the FRF being plotted on the y-axis with frequency on the x-axis, and this plot for a single degree of freedom system may look like this. Okay, so real part of the FRF may look like this. Something like this. Another plot which is used to present FRF is what is called as Nyquist plot. Right, Nyquist plot. Nyquist plot is a plot of real part of the FRF versus imaginary part. Right, so this plot may look like this. So real part, so imaginary part we have on the y-axis imaginary part of the FRF, and the real part of the FRF we have plotted on the x axis. So, so different frequency points will be there like this, you know, and these points together, you know, when they are joined, they result into what is called as Nyquist plot. Something like this. Okay. So, in the Nyquist plot, the frequency variable, it appears only implicitly, right. Okay. So, however, we can see the variation of real and imaginary part, you know, against each other. That is the, you know, advantage of the Nyquist plot. Let us now see and study the characteristics of FRFs of a single degree of freedom system with viscous damping. So, now we are going to talk about FRF characteristics of a single degree of freedom system with viscous damping. So, we already have studied and determined the an expression for the frequency response function for such a system, and that expression is we are going to look at the receptance now, receptance of the system. So, receptance alpha omega we obtained is 1 upon k minus m omega square plus I omega c, where c is the viscous damping coefficient, right, and k and m are the stiffness and mass of the system. This expression we can also, you know, if we divide by k in the numerator and denominator, this expression can also be written as 1 by k 1 minus omega upon omega n whole square plus I 2 zeta omega upon omega n, where zeta is the viscous damping factor. We can also now determine the magnitude of the FRF, which is you know, which can be obtained as follows. We can, you know, multiply the numerator and denominator by k minus m omega square minus I omega c, right, and if you simplify, the magnitude would turn out to be 1 upon under root of k minus m omega square whole square plus omega c whole square. Similarly, for this case, the magnitude would be 1 by k upon square root of 1 minus omega upon omega n whole square, square of the bracket, plus 2 zeta omega upon omega n whole square, right. So, that is the magnitude, and of course, we can also determine the phase, right, which I can write as phase lag phi is equal to tan inverse 2 zeta omega upon omega n upon 1 minus omega upon omega n whole square, right. And for a with single degree of freedom system with viscous damping, we have got this, you know, magnitude and phase. Graphically, if I plot them, if I plot here, let us say the magnitude in dB, right, then and then frequency on the y axis, x axis, then this plot would look something like this. Right, and this is the location of the undamped natural frequency omega n. So, we see that for this system, as we have studied earlier, the peak in the FRF occurs slightly to the left of the natural frequency. Similarly, the phase plot looks like this, the phase lag here, right, and so this plot would look something like this, right. So, here the at omega n, when excitation frequency is equal to omega n, the phase is around 90 degree, is 90 degree in fact, and starts from 0 degree, and when the excitation frequency is very large as compared to the natural frequency, the phase tends to become equal to 180 degree. So, this is the basically magnitude and phase of single layer of Adamson viscous damping. Let us now try to study the behavior of the magnitude plot, right, in the low and high frequency range. Okay. So, based on this behavior, we are going to now define two asymptotes of the FRF, which are called as stiffness line and mass line. So, stiffness line and mass line, correct. So, we are basically going to study in the low frequency range how the FRF magnitude can be approximated. So, if you look at excitation frequencies which are very small as compared to the natural frequency of the system, right, that is when omega upon omega n ratio is very small. Okay. So, let us see how we can approximate the FRF magnitude. So, the FRF magnitude, we let me write that expression again here, 1 upon 1 by k in the numerator, and then we have 1 minus omega upon omega n square whole square plus 2 zeta omega upon omega n square, right. So, if omega upon omega n is very small, right, then what is going to happen? Delta alpha magnitude can be written as 1 by k, right. It can be approximately 1 by k, because in the denominator, when omega upon omega n is very small, basically the denominator tends to become equal to 1, right. And now if you write this in the dB form, then we have 20 log 10 alpha is equal to 20 log 10 1 by k, right, and which can be therefore written as minus 20 log 10 k, right. So, what we see, this is the dB magnitude of the FRF, okay, and this dB magnitude, we see that it basically is not dependent on omega, right, and therefore it represents a line which is parallel to the frequency axis, the x axis, okay. So, it means that the magnitude of the FRF can be approximated by a line which is parallel to the frequency axis and which makes an intercept of minus 20 log 10 k on the y axis. And this line, because it is dependent only on the stiffness of the system, this line is referred as the stiffness line, right. So, if I show it graphically, then what we have got? We have this FRF here, FRF magnitude in dB, right. This plot is going to look like this, the FRF magnitude plot, right. And now if I show the line we got, then this line is a horizontal line which is parallel to the frequency axis, right, and it makes an intersection on the y axis at minus 20 log 10 k, and this line is called as stiffness line. So, this line very well approximates the behavior. So, if I look at in this region, right, this we can roughly mark as the low frequency region. So, in this region, this stiffness line is able to approximate the magnitude of the FRF reasonably well, right. So, this is called basically the stiffness line, and it basically forms an asymptote of the stiffness line. It basically forms an asymptote of the FRF magnitude plot, right, in the low frequency range. Okay. Let us now study what happens in the high frequency range. So, in the high frequency range, when omega is much larger than the natural frequency, right. So, this means that omega upon omega n is much larger than the 1, it is very large value. And if you look at the magnitude plot, magnitude of the FRF, which is 1 by k divided by under root of 1 minus omega upon omega n square whole square plus 2 zeta omega upon omega n square, right. So, if we take this limit when omega upon omega n becomes very large, then this magnitude of the FRF can be approximated as 1 by k in the numerator, and in the denominator the term omega upon omega n square, that is going to dominate the rest of the terms, right. And therefore, we can approximate that as omega upon omega n square. The denominator we can approximate as omega upon omega n square. Therefore, this can be further written as 1 by k into omega n square upon omega square, 1 upon 1 omega n square is nothing but k by m, right. And therefore, what we get is that the magnitude can be approximated by the expression 1 upon m omega square, right. So, that is what we are getting as the equation that can approximate the FRF magnitude in the high frequency range. If we take now again 20 log 10 on both sides, so that we convert the FRF magnitude into decibels, then we get 20 minus 20 log 10 m, right, minus 20 log 10 omega square, which can further be written as minus 20 log 10 m minus 40 log 10 omega, and this is nothing but the dB magnitude of the FRF. So, what is the conclusion here? The conclusion is that this equation, so what is the conclusion here? From this equation we see that this equation is essentially equation of a straight line if the frequency axis is logarithmic, okay. So, on the right hand side we have log 10 omega term appearing. So, if we treat that as the variable, right, which means that if we plot the dB magnitude on a logarithmic frequency axis, then it is basically in the high frequency range basically the FRF magnitude can be approximated by a straight line, right, and that straight line will have a slope of minus 40 dB per decade, right, and it will have it will make an intercept of minus 20 log 10 m on the ordinate, right, at omega is equal to 1 radian per second. So, let us try to represent this on the graph. So, if we plot here the alpha in decibels and here we plot the frequency, and if this is the magnitude plot, right, and also we are plotting this on a log scale, that is log 10 omega, that is what we are plotting on logarithmic frequency axis. Then what we see that in the high frequency range this magnitude plot can be approximated by a straight line like this, okay, and the slope of this line is minus 40 decibels per decade, okay, and it makes an intercept of so if I show here the ordinate at omega is equal to 1 radian per second, then this line makes an intercept of minus 20 log 10 m on this ordinate, okay. And this line is basically dependent only on the mass of the system, and that is why this line is called as mass line. It is called as mass line. So, the mass line approximates the FRF magnitude, right, in dB, right, in the high frequency range. For a single degree of freedom system with viscous damping. Okay. Also, this slope of this line is minus 40 dB per decade. Slope of the line is, the slope is minus 40 dB per decade. So why that is so? We can understand this in this manner. If I take, say, omega is, let us say 10, right, and if I look at the magnitude of minus 40 log 10 omega, this term, then this magnitude will be minus 40, right, dB. And if I increase the omega by a factor of 10, that is, I make it 100, then this would be minus 40 into 2, that is minus 80 dB. So this means that when we increase the omega by 1 decade, that is a factor of 10, then the magnitude of the FRF drops by by 40 dB, right. So change is minus 40 dB or drop by 40 dB, okay, and hence we say that the slope of this line is minus 40 dB per decade. So therefore, now the stiffness and mass lines can be used to identify the mass and stiffness of a single degree of freedom system with viscous damping from its FRF plot. Okay, so we can identification of mass and stiffness from FRF plot. So if the FRF plot of a single degree of freedom system with viscous damping is available, then we can determine the mass and stiffness of the system from this plot using the concept of stiffness and mass line. How can we do that? Let us quickly make the plot here. So this is the FRF plot, and then we are plotting it on the logarithmic frequency axis, log 10 omega, and here we are plotting the FRF magnitude in decibels. So now to find stiffness, what we can do, we can draw the low frequency asymptote of the FRF, right, which is nothing but a straight line in the low frequency range, and that should be asymptote to the FRF, that is almost tangent to the FRF, and then we can read where does it intersect on the y-axis, that is minus, that value would be minus 20 log 10 k, and therefore we can determine the value of k from the dB magnitude, right. So so let us say if that value is if I call that as say alpha naught, right, then I can write this as alpha naught, that is alpha naught decibels is equal to minus 20 log 10 k, right, and therefore the k would be simply equal to alpha naught upon 20, right, 10 to the power this. So that basically becomes the value of k. Okay. Similarly, if I want to know the mass of the system, then we can determine it from here. So we draw a asymptote. We draw asymptote to the FRF, that is a line which is at a slope of, which is tangent to the FRF curve, and it is at a slope of minus 40 dB per decade, right. So so therefore if I show here the frequencies which are going to be there on the y axis, they will be 1, then 10, then 100. So this is basically going to be the different decades of the frequencies, right, 0.1, 1, 10, 100, 1000. So now we can plot here asymptote which has a slope of minus 40 dB per decade, and let us say that asymptote is this, okay, and then we should see where does this intersect, where does this asymptote intersect on the ordinate at omega is equal to 1, right. So, if I extend it and right, so let us say this value is alpha dash, right. So, then I can say that alpha dash dB is equal to minus 20 log 10 m, right, and therefore m would be simply equal to 10 to the power minus alpha dash by 20, that will be m, right. So, of course, we should remember that this line has been drawn with a slope of minus 40 dB per decade, right. So, that is how we can identify the mass and stiffness of the system from the FRF plot of the system. Can we identify viscous damping coefficient from these mass and stiffness lines? Estimation of viscous damping coefficient, right. So, if you look at the stiffness line, so if I represent stiffness line magnitude by alpha SL, right, SL representing the stiffness line, then at omega is equal to omega n, right. So, at omega is equal to omega n, this value is 1 by k, because anyway it does not matter at what frequency you write this magnitude, because stiffness line is not dependent on omega. The magnitude of the mass line, if I represent it by alpha ml, which is equal to 1 upon m omega square, then at omega to omega n, that magnitude would be m omega n square, and this would be again equal to 1 by k. And if I look at the magnitude of the FRF alpha itself, then that would be 1 by k divided by square root of 1 minus omega upon omega n square. So, that will be 1 plus 2 zeta omega upon omega n will be 1 square, right. So, this becomes 1 upon 2 zeta k, right. If I take the ratio of alpha and magnitude of the stiffness line, that is alpha, right, then this will be equal to 1 upon 2 zeta k upon 1 by k. So, that is 1 by 2 zeta, right. And if I take 20 log 10, then 20 log 10 alpha minus 20 log 10 alpha SL, this is equal to 20 log 10 1 upon 2 zeta, right. And the left hand side basically represents the difference in the dB magnitudes of the FRF and the stiffness line. So, if I represent, let us say this by delta alpha, then I get the relationship that 20 log 10 1 upon 2 zeta, isn't it. And if I further simplify this, then I can write this as 1 upon 2 zeta is equal to that should be equal to 10 to the power delta alpha upon 20, right. And if I take reciprocal, then that becomes 10 to the power minus delta alpha upon 20. Therefore, zeta is equal to 1 upon 2 10 to the power minus delta alpha upon 20. And because we know that C upon Cc is equal to zeta, I basically get from here C as twice under root km, right, into 1 upon 2 10 to the power minus delta alpha upon 20, which basically reduces to under root km 10 to the power minus delta alpha upon 20. So, this is the expression we get for the viscous damping coefficient. Let us see that how do you determine now the delta alpha, right, from the magnitude plot. So, let us make a plot of this first. Okay. So, here we are plotting the magnitude in dB versus log frequency axis. Let us first of all make the let us say this is the stiffness line we have, and we have, let us say, the mass line, right. Okay, and we know that they intersect at omega 0 to omega n, right. So therefore, what we do, we determine first of all the magnitude of the FRF at this frequency, and let me overlay on this the FRF like this. It's going to be like this. So now